Welcome to Lesson 8, Go Routines. This is where we're going to learn our mechanical sympathies about how the operating system scheduler works and the Go scheduler works. We're going to learn those internals. We're then going to start learning how to create Go routines and manage their life cycle. We're going to start learning a little bit about Go routine orchestration in terms of how we create them and manage them. All right, we're going to start talking about concurrency, and what I want to do right now is give you the mechanical sympathies of the Go scheduler. I want you to get an understanding of where the sympathies are and why Go is going to be able to do the things that it can for us, which is really reduce a lot of cognitive load that we used to have when we were writing multi-threaded software directly with operating system threads. But Go can't take off all of the cognitive load. In fact, I don't think there is a single language we could even invent that can do that. We're still always going to be responsible for understanding our workloads. We're always going to be responsible for what I call synchronization and orchestration. We're going to start talking about what these things are. But let's start right from the beginning and get a general representational level understanding of how the operating system schedulers work. Now, an operating system scheduler is what we call a preemptive scheduler, which basically means that when the scheduler at the operating system is making a decision about how to schedule threads, we cannot predict what the scheduler is going to do, especially if all things are equal. They are preemptive, which basically means undeterministic. Now, when a program starts up on your operating system, I don't care what operating system it is, Windows, Mac, or Linux, what's going to happen is the operating system is going to create a process. I always like to think of that process as a container for the resources that that running program is going to need. This word container's got a lot of baggage around it, so don't be thinking about Docker and all that other stuff just right now. Just think of it as a process, as a way of maintaining and managing the resources for that running program. And there's two big key resources. There's lots of them, but there's two big key resources that we are talking about all the time. One is memory, and if you remember, that process has been given a full memory map based on the 64-bit or 32-bit architecture of memory. Now, that process thinks it's real, but we know it's virtual. But there's another thing that process is given, and we call it a thread. In fact, it is the main thread. And it's the main thread because when the main thread dies, guess what? The process is shut down. Now, if a process is like a container for the resources, then I want you to consider the thread to be the path of execution. That's what I like to think of threads as, paths of execution. Remember, you're writing code. That code turns into machine code, and machine code is always going to be executed in a linear fashion, right? Do this instruction, that instruction, that instruction, that instruction. Even if there's a jump statement, that instruction says where to jump to next. Do this, do this, do this. So it's always this linear execution, or this linear path of execution. And it's the job of the thread to manage that linear path of execution. We have what's called an instruction pointer, or sometimes we see it as PC, the program counter. You'll see that in stack traces. The PC is telling us what that, at the hardware level, like what that instruction was that we had to execute next. Okay, so we have these paths of execution. And the schedulers at the operating system don't care about processes. All they really care about are paths of execution. Now, we're going to keep things simple and clean and representative, and we can maintain these visual mental models of things. We don't have to really get complex. From our perspective, a path of execution, or a thread, can be in one of three states. A thread can be executing, or you'll hear me say running. It's actually been placed on a core, and now whatever the next instruction is for that thread, its next program counter, right, that next instruction pointer, wherever it is pointing to, that's the next instruction that's now going to get executed. And that path, or that thread, will get to keep executing its instructions until the operating system, in a non-deterministic way, decides that that thread is no longer allowed to run on that core, and then performs a context switch. A context switch is when we have a thread executing on some core, and it's pulled off the core, and the new thread is placed on the core. Now, a thread can only be placed on the core if it's in a runnable state. That's the other state. So we had running, then we have runnable. So the operating system is going to look at all of the threads that are in a runnable state. It's going to choose that next one, however that is. It's undeterministic. And now that thread gets to execute its path of execution. Now, a context switch in the operating system is very, very expensive. Okay? The operating system really doesn't know what these threads are doing. It knows that they're in this now state that they want to run, but they don't really necessarily know what it's doing. So a tremendous amount of information has to be saved out of that core that the thread is running on. So when it's placed back on the core, it can be done so in a way that the thread had no idea that it ever really stopped. So this concept of saving state and replacing state is very important, and it's very expensive. Remember also that threads have a 1 meg stack space. That also makes threads very, very expensive. Okay, the third state that a thread can be in is, we'll just call it the waiting state. There are many sub-states when it comes to waiting. That's not important for us. What's important is that the thread's now in a waiting state. And from an execution standpoint, when a thread is in a waiting state, I like to think of it as in the matrix. It's gone, it disappears. It disappears from view. And it disappears from view until it moves back into a runnable state. There's lots of reasons why a thread could go into a waiting state. It's waiting for something from the operating system, most likely. We're waiting for disk I/O, network I/O, something that you've done that says, you know what, we don't need to schedule this thread right now because it doesn't want to run. It's not in that runnable state. So we've got running, runnable, and waiting. These are the three states that the scheduler is going to be managing all the time. And we've got the context switch. Now, in the early days, it wasn't really a complicated problem. In the early days, we had one core. So imagine we've got this one core right here. Here it is. This is our execution unit. And let's imagine that we have one core in our piece of hardware. And that core, and again, we're going to keep things very, very, very simple. That core, even today, can only execute one path of execution at a time. Even though there's multiple hardware threads in there, from our place here, that core can only execute one operating system or path of execution at a time. So if I got one core, no matter what, we're only going to be able to execute a single thread. Now, back in the day, let's say that you had 10,000 of these threads, 10,000 threads or paths of execution that want access to this execution unit. Now, one of the jobs of the operating system is to make it seem, perceive, that all of these paths of execution or threads are executing at the same time. We know that that's not physically possible because we only have this one core or execution unit. So what the operating system scheduler has got to do to create this perception that everything's running at the same time is give every one of these threads a slice of time on the core. Now, when we only have this one core, this is not necessarily a very complicated problem. All we got to kind of say to ourselves is, I'd like to create the perception that all these threads ran within a certain amount of time. So if we take that time and divide it by the number of threads, well then each thread will get that amount of time to run, come off, run, come off, run, come off. And if any of these threads go from a running state into a waiting state, well then we'll take, they'll execute less time, which will now give another thread, that opportunity to just get on the core quicker. And operating systems have the idea of priorities. We can prioritize these threads, but we don't need to really go to that level of complexity right now. The idea is that if there's more threads, like 10,000 threads, then each thread's going to really get less time because we've got to create this perception that they're all running. But what if there was only 1,000 threads, not 10,000, 1,000 threads? Then we get the idea that each thread's going to get more time because there's less threads that we have to worry about scheduling within that amount of time, right? So everything that I've been talking about, and especially everything here in multi-threaded software development, is going to be this idea of less is more, we've got to keep that in our head all the time. Less is more. More threads mean more load on the operating system scheduler. It's got to make more scheduling decisions. There is more chaos, which means more scheduling decisions, more context switches. And understand that when a context switch is happening, your paths of execution are not running, right? Operating system code is running to pull this off and to push this back on. We can consider a context switch application latency, because for that brief amount of time, even if it's just nanoseconds, right? That's nanoseconds of time, clock cycles, where your code is not executing. And it's really, at the end of the day, creating a little bit of chaos for everyone. So less is always more. But something interesting happened in 2004. In 2004, we started seeing multi-core processors become mainstream in the marketplace. In other words, it got to a point where you couldn't buy a server that you were going to rack in your data center that didn't have multiple cores. Now, that sounded really exciting. Wow, I don't have just one execution unit, I now have two, which now means that if I've got two execution units, that means that I can now execute not just one thread at a time, but two threads at a time, which means now I can run threads in parallel. Look, concurrency really just means managing a lot of things at once. When we're in our single core environment, the operating system is managing concurrency. It's trying to execute all of these threads one at a time on this core. That's concurrency, right? The perception that things are happening all at the same time, but we got to manage all of these paths of execution. Once we are up to two cores, okay, in this scenario here, we now have what's called parallelism. And that means doing a lot of things at once. We're executing two threads in parallel, right? These paths of execution are happening at the same time. And when this started happening, when we started getting hardware with multiple cores on it, the academics started doing research, and they started identifying that the operating system schedulers didn't know really how to efficiently handle this situation. What they saw were threads in a runnable state, right, with core that was idle for nanoseconds to microseconds at a time, and those threads not being scheduled. This is a nightmare if we're really trying to leverage that second core to run faster. And there's a lot of complexity that we'll talk about before we're done here about how multi-threaded software, especially on a multi-core processor, can get very complicated very, very fast. But we come back here, and what that meant was in 2004, the scheduling problem opened back up. We had to come back in and rewrite the schedulers to take advantage and be smarter about our multi-core processors. Now, I want to show you a little bit of why the scheduler really is a very complex, at least I consider it, a complex algorithm when it comes to efficiency, especially when the scheduler doesn't really know what the threads are doing. I mean, let's go back to our i7-900 core processor here that we were looking at earlier in the class. And if you remember, hopefully you haven't skipped to this section. If you have, look, if you've skipped to this section because all you care about is concurrency, I'm going to just really beg you to stop and go through this video from the beginning, because I've laid down a huge amount of foundational knowledge so we can have this conversation right now, and you can have it with the full breadth of knowledge that I'm about to go in. So I'm going to assume already that you've gone through that arrays section and you've looked at the mechanical sympathies around data. This is what we're doing, and if you haven't, I really urge you to stop and go back and look at that stuff. So remember, we talked about that we have our 4-core processor. Here it is. And that these processors, these cores, have an L1 and L2 cache, right? L1, L2 cache. We also talked about the L3 cache here in main memory. So remember something here. The scheduler's got to be very intelligent about how the hardware works, about how the hardware is laid out in order for it to be efficient. I mean, processors like this, you know, these cores, we talked about this as well. These cores talk to each other, right? They talk to each other. And in order for them to be able to talk to each other, right, there are pathways, physical pathways there. And we can notice here that these two cores are closer together than these two cores, right? These two cores are closer. They could talk to each other much faster than these two cores can. The hardware wants to know about this stuff. And what gets really interesting to me is when we start getting into these like 24 core processors, we can't use these rings anymore, right? The distance between any two cores can be quite great. And the hardware is starting to deal with, these matrices where we're putting these cores, right, on a matrix here to try to reduce the largest path between any two cores. These cores have to talk to each other. Throwing more cores at a problem doesn't mean it's going to get faster if you're not mechanically sympathetic with the way caching systems and processors work. But the processor, the schedulers have to know all of this stuff. So I want you to think about this for a second. Let's imagine that you started a process, and it starts on core 1. So that means that the main thread for this process, now the operating system says, we're going to execute this thread here on core 1. Now, as this path of execution is going, it's going to need data. Everything's a data problem. We've talked about that. And so what happens is the cache lines start coming in to L1, L2, and L3, right? They're all coming in from our main memory, right? This application is working with data. It's coming in. Now, this becomes interesting. Let's say that the main thread decides to create a second thread, thread 2. We're going to start a second path of execution here with the idea that I'm on a multi-core processor. We should be able to run these in parallel. But we're probably maybe on a very, very busy machine. And remember, our caching systems are a way of reducing those cache line and TLB misses here within our processor. So this is always an interesting question if you were to be writing an operating system scheduler. Should the operating system scheduler, knowing that these cores are busy already, okay, doing other work, should the operating system scheduler consider to pull or to stop, right, put into a runnable state again, the main thread, so thread 2 can start running on core 1 with the idea that the chances that the data the main thread is using is going to be the same as thread 2, right? A family of threads are probably working with the same data. And since the data is already cached in C1, wouldn't it be more efficient to say, OK, you know what? Let's pull you off of this core. Let's put you back on this core here because the data you need is already there. This is complicated. But what if this core 2 right now is about to become idle? Wouldn't it be better to run thread 2 on core 2 and get that executing, even though we're going to have to probably take some cache line misses, even though we're going to be duplicating data across these particular cores from a caching perspective, right? Wouldn't that be better too? I'm not asking you to answer this question. What I'm trying to tell you is these are decisions that have to be made. And decisions have to be made about how close, any particular two cores are too. This is cool stuff. But I will tell you this. If a core is idle, it's going to be used. We're not going to wait there, right? We want to get things executing, if it means that we have to bring in that data. But what we want to do, and what the operating system is going to try to do, is create what are called run queues. So anytime a thread is in a runnable state, what we're going to end up doing is putting these threads in a run queue. And we could have these run queues at a core level. We could have run queues at a processor. There's a whole tree or hierarchy of these run queues. And the operating system is taking these threads and they're placing them in these run queues so the operating system can eventually get these threads in as efficient manner as possible executing. And the Linux operating system is brilliant at this stuff, even on our multi-core processors today. All of this is going on underneath. We don't have to necessarily worry about it, except we do have to be mechanically sympathetic with the operating system, because if we're not really going to get the performance we want, and we could be not only just thrashing through memory, but thrashing through context switches of latency. None of that is really going to help us. So we have two responsibilities here as a multi-threaded software developer. we've got to understand our workloads. We've got to understand when to use synchronization and orchestration. When I talk about understanding our workload, what I'm talking about is there's really two types of workloads that we have to think about. There's CPU-bound workloads and there's I/O-bound workloads. And CPU-bound workloads are workloads where those threads are never going to move from a running into a waiting state because they're not going to be asking for anything I/O related, let's say, to move them into a waiting state. What gets interesting is if we have CPU-bound work, then having more threads than there are cores are going to just cause more pain than good because the context switch is pure latency, right? But if you have I/O-bound work, that means the threads are moving from running states to waiting states to runnable to running to waiting. And I/O-bound work could be making a database call, disk I/O, any sort of thing that would cause the path of execution, the thread, to have to wait for something. Now, in those scenarios, having more threads per core can be really, really great because that means that as a thread moves from running to waiting, a core becomes available for more work. And we want to keep those cores as busy as possible. See, you've got to understand your workload to be able to understand how many threads you could really throw at a problem. You can't just throw an unlimited number of threads either. And historically, the way we did this for multi-threaded software development was to use thread pools. Thread pooling was kind of our way to be able to say, what is the maximum amount of threads that give us the best throughput? And I did a lot of multi-threaded software development on Windows prior to 2013 when I decided, or my company had to move to Linux, and I needed the Go programming language for this. And really, Go helped me out with a lot more than just moving to Linux. But when I was on Windows, what we had was a thread pooling technology called IOCP. And Linux has the ePoll, and we've got K-Event. We've got other thread pooling tech in the other operating systems. But IOCP, which stands for I/O completion ports, was Windows' solution to thread pooling. And so if I was writing a multi-threaded software like a web service, what I'd have to do is create an IOCP thread pool where as requests started coming over the wire, we would post those requests into the thread pool and let a family of threads in this pool process it. Here's the problem. How do you know what to size the thread pool? And if you've got certain amount of cores, we would really want to make sure that the pool, right, is configured for what the hardware is there. At the end of the day, what you really need is this. You need a situation where as the number of cores increase, your throughput increases, but in a linear fashion like this. If you have a situation where you add more cores to an algorithm, and you've got charts that are doing this, you've got a mechanical sympathy problem, right? Adding more cores should give us that linear growth. And if not, then we're doing something bad in our algorithms, maybe on our hardware, something bad on our systems. Now, this is something that I learned about the Windows operating system. I can't say that it would apply to the other operating systems, but I learned this. Let's say I set up this IOCP thread pool. Now, the IOCP thread pool had 3 parameters. Min number of threads, let's say we set that up to 2. Max number of threads, let's say we set that to 24. And it had a concurrency value, which you always set to 0. This is interesting, it had a concurrency value. Now, you set it to 0 because what it meant was if there are only, let's say, 1 core on your system, then only allow 1 thread to be active at any given time. Because if you've got more threads active than cores, you're just adding latency and workload. But that always made it interesting to me. Why could I set the min and max values to be larger than the number of cores when I've just said I only want to use 1 core? At 1 thread should only be active for 1 core, right? Why would I be allowed to use more? Because you got to understand your workloads. I keep saying this. So look at what happens in this scenario. Requests start coming in. Let's say this is it. And let's say we are on a 2-core system. So let's say that we're on a 2-core machine, which means we got 2 threads that can run in parallel. I've set that to be 2. I've set 24. Only 2 threads can be active. So how does this work? Watch this. we turn the server on, requests are coming in, we start throwing them into the pool. Now the very first request that comes in, there are no active threads, so no big deal. The operating system says, okay, you thread, you're going to take it, right? Right now we have, we can have up to 2. We start with 2, we can have up to 24, and so we say, you go active. Brilliant. Now another request comes in, right? So this one here. Another request comes here. Hey, no big deal. You go active. Now these requests are being processed. Now, a bunch more requests come in. They're coming into the pool. Request, request, request. But guess what? Those 2 threads are active. We're not allowed to have any more active threads. This work is now piling up. But remember, this is I/O-bound work. These threads are probably going to make a database call. It's a request. Databases are involved. And when this makes a request, what's going to happen is this thread's going to go from this active state, right, to a waiting state. And now this thread, once it goes into a waiting state, how many threads do we have active? Just 1. OK, we can have up to 24 threads in this pool. Create a new thread. And now that we've created this new thread, guess what? Activate it for this piece of work. And now eventually, this thread goes into a waiting state, which means now that that's in a waiting state, we can add another thread to the pool. And now that we've added another thread to the pool, let's let it do this work. Look, at some point, depending on the amount of time or latency it takes these threads to process the work and the latency on the database, you could end up with 22 threads in here in a waiting state and 2 threads that are active, even though we only have our 2-core machine. So this is why you have to understand your workload. And maybe when we have 22 threads active, we've put such a load on the operating system in our work that we actually don't get it done faster. More threads do not mean faster work. So this is the thing that I kind of learned about Windows with these kind of web request type of software with databases involved. There was this odd, like 3-to-1 ratio that I identified. So in other words, if I only had 1 core, then I never wanted to have more than 3 threads in this pool at any given time, because this 1-to-3 ratio meant that I could get that work done faster. In other words, if I threw 100,000 requests at the server, and I only had 1 core, and I used 3 threads, it got done the fastest. If I used 2 threads, it was slower because I had more idle CPU time. But if I used 4 threads, it was slower because I had more context switches of latency. I had more work. So if somebody said this wasn't fast enough, you know what I would do, right? What I would do is just say, give me another core, which means I can go to 6 threads. I'd get this linear growth. I could go faster. Hey, that's not fast enough? No problem. Give me 4 cores. I can now go to 12 threads. If I do less or more than 12 on a 4-core machine, I'm not going to get the work done faster. This is how these thread pools would help us. We could identify how many cores are on the machine, set up the thread pool based on what we know is our best throughput, and this is how we could do some stuff. But this is cognitive load for us, and we have to run stuff through our servers. We've got to monitor this, and you know how traffic patterns can change over time. So this isn't really perfect, but it gave us, over time, a good even throughput, and it allowed us to take advantage of the hardware was there and try to create this linear growth. Whew. Stuff is complicated, okay? And we would have to do these same things regardless of the operating system we're on. But this is one of the things, as I'm going to show you, that Go is fixing for us in terms of our cognitive load. We still have to understand our workload, but we don't necessarily have to worry about managing our own thread pools anymore. The Go scheduler is going to start doing all of that stuff for us. So now that we have a good understanding of what's happening at the operating system, our threads are our path of execution. They can be in a running state, a runnable state, which means they're in a run queue looking to go, or they could be waiting. We understand now that we have to understand our workloads. There's CPU-bound workloads. There's I/O-bound workloads. We want less is more with the threads, and all things are going to dictate how we architect, design, and throw work at our machine to get it done as fast as possible. So the next thing that we've got to learn now that we've kind of looked at the operating system is how the Go scheduler works, which sits on top of it. All right, so we just went through the operating system scheduler mechanics and the aspects of that we're going to be sympathizing with in Go. Now, I showed you a little bit of this when we were talking about the garbage collector. We're going to go deep into now how the Go scheduler works and sits on top of the operating system. So when your Go program starts up, it is given a logical processor that we call P. This is modeled very much after the operating system, like the Linux operating system and the things that I showed you. That logical processor P is given an M, which stands for machine, which represents a real live operating system thread, or the operating system path of execution, which the operating system is still responsible to schedule on some core, everything that we just talked about, okay? Then there's two data structures here. There's the global run queue, and every P has a local run queue. Remember we talked about run queues at a core, at a processor level within the operating system, because a Go routine, just like a thread, is a path of execution, which means a Go routine also can be in one of three states: running, runnable, or waiting. It's all the same stuff. So when a Go routine, like the main Go routine, when your Go program starts up, you get the main Go routine, right? We could show that the main Go routine is executing on our context right here. Okay, there it is. We might even just maybe want to draw it like this to make it a little bit more clear that our Go routine, our main Go routine, is now executing on the M, right, on the context, because it belongs to this P. And maybe this main Go routine goes ahead and creates a couple more Go routines. So those Go routines end up finding themselves in a local run queue because they're in a runnable state, right? This is executing. There it is. These are in a runnable state. There they are. Now, sometimes a Go routine that's in a runnable state might find itself in the global run queue because a P hasn't taken it yet. This is a work stealing scheduler. We'll talk a little bit more about that. So Go routines could end up in the global run queue. This P pulls in and says, hey, I'm stealing this work. I'm going to take it. Ends up in the local run queue right here. And we've got this Go routine, and it's executing a runnable running state right there. So this is it. And if you've got multiple Ps, because I've got multiple cores, remember you're only going to get a single P or thread per core. Think about what that decision is. What we're saying is that we don't need more threads than we have cores because we don't want to put more load on the operating system. We, at the Go level, will manage these paths of execution. And I'm going to show you where all those sympathies are. But if we have this situation, then you could have two Go routines running in parallel, and you could have Go routines, in the local run queues across these Ps. So you're starting to see this. Now, let's just start here with some basic scheduling. The Go scheduler runs up in our user mode or in our user space. So understand that the processor can be switched into different modes. There's two classic modes we talk about all the time: kernel mode and user mode. And kernel mode basically tells the processor that whatever code is currently executing, it can do whatever it wants, right? So when you're executing operating system code, like you make a system call and now the operating system's servicing that and executing on the core, that processor switched to kernel mode. And this is why drivers can cause havoc, right, or bring your operating systems down, because the drivers run in kernel mode, and kernel mode means this code can do whatever it wants. Don't just let it go. But when we're executing our code, right, our code here, our Go code, it's executing in user mode, which puts the processor in a protected mode. And it tells the processor, look, this code's not allowed to do whatever it wants, and if it's about to do something we don't like, then fault the application but protect this house. Since the Go scheduler is built into the Go runtime, and the Go runtime is built into your Go application, that means the scheduler runs up in user mode. And since the scheduler runs in user mode, we now have to say that the Go scheduler is not a preemptive scheduler, but a cooperating scheduler. Now that's really like a four-letter word for us dinosaurs who coded on cooperating schedulers 20 plus years ago. Because cooperating schedulers mean that the application developer has to do the cooperation. In other words, if a piece of code, right, got time on that core through its thread, then the application developer has to cooperate and say, okay, I'm willing to give up my time slice. I'm willing to give up my time slice. I'm willing. But the reality is if I'm an application developer and I get a chance for my code to run on that core, I ain't giving it up. And we didn't, right? We were very, very selfish. So when I think about a cooperating scheduler, I start to cringe because there isn't really a lot of good concurrency around it because we're asking developers to make decisions. But Go has kind of changed the game here with the cooperating scheduler because it's not the developer who's having to cooperate. The Go scheduler is doing all the cooperation. And because of that, what's brilliant is this app user space, right? User space cooperating scheduler looks and feels preemptive, just like the operating system scheduler. And so I want us to put into our head that the Go scheduler is a preemptive scheduler because when all things are equal, you have no clue what the scheduler is going to do. It is as undeterministic as that operating system scheduler is. So technically cooperating, but it has this semantics of a preemptive scheduler, and when all things are equal, it is undeterministic, and we do not write code with the idea that we're going to predict what the scheduler is going to do. You have to control it, right? And that's when we start talking about synchronization and orchestration later. So this is our model. Now for the runtime scheduler to make a scheduling decision, a cooperating scheduling decision, the events have to occur in the code. And these events happen through function calls today. They are looking in 1.11, which is in beta right now as I speak, to find statements that can also be used to help make scheduling decisions, where we're not going to be stuck in tight loops where function calls aren't going to be made. But I need to understand how complex it is to be able to do statement level context switching like that, because things have to be atomic, right? And the runtime and the schedule has to guarantee that statements are atomic. It's very complicated stuff, amazing stuff that I can never work on, but some of it is coming. So as of 1.10 today, everything happens through function calls. Now there's 3 classes of events that are going to allow the scheduler to make a scheduling decision. There is the use of the keyword Go. And this is how we create Go routines. We're going to add a new path of execution. Any function or method in our code can become a Go routine or a path of execution by using the keyword Go in front of the function call. You also have garbage collection. Anytime garbage collection kicks in, there's going to be a lot of scheduling decisions being made because the garbage collection Go routines also have to use the Ps that are available. A lot of chaos. Number 2, system calls. System calls. There's system calls happening all the time. Anytime you call log or func.print, that's a system call. So there's lots of availability of the scheduler to make these cooperating scheduling decisions. 1, 2, 3. And really, let's just put it into a list of blocking calls. So anything that could cause that Go routine to have to go into a waiting state, like the use of a mutex or an atomic instruction, something like that, look, we're going to end up having. And these things are happening all the time. And therefore, this scheduler, even though it's cooperating, can look and feel very, very preemptive. Now let's talk about system calls because this is really interesting. We are fortunate today for the majority of us, that our production system, operating systems, have the ability to do asynchronous system calls. And what we try to do in Go is leverage these asynchronous system calls for as many things as we can. We use it today for a lot of our networking calls. We use it today for a lot of disk I/O type of calls. And we try to leverage this as much as possible. And this is kind of why. Let's say that this Go routine right here wants to make a system call. Remember, we're on a single-threaded Go program. Anytime we have 1P, we're single-threaded Go program. This Go routine wants to make a system call, wants to open up a file. How long can that take? Dude, that could take seconds, right? I mean, it could take eternity. So if we allow this Go routine to block this operating system thread, then for that amount of time of latency, we're not getting any other work done. We are basically in a stop the world situation. We can't have that. So what Go has is a really special data structure here, a system that we call the network polar. And this is leveraging that thread pooling technology. So on Windows, it's using IOCP, K-event or epoll on Linux. And this has a thread. And what we do is when that goroutine wants to make a system call, well, then what that happens is this goroutine is context switched off of the M. There it is. It's placed over here in the network polar. There it is. It's now in a waiting state. And its request, its operating system request, gets posted into the network polar. And we handle the system call asynchronously. This is great because we just freed up the M to do more work. And that's exactly what's going to happen. This goroutine that's in a runnable state now moves into an execution state. It's running now. Went from runnable. Now, again, when these goroutines are, when all things are equal, we don't know which one it's going to choose. It's choosing that one. So look at what we've done here. Even though we are a single-threaded Go program, this thread here, part of the network polar, is now servicing the asynchronous system call. Once the net polar comes back, or the operating system comes back with the system call, then we can take this goroutine and move it back into the local run queue, where it sits back into a runnable state. And eventually, what we'll end up doing is another context switch. And maybe this main Go routine now comes back and is executing. This goes back into a runnable state. How cool is that? The concepts of an asynchronous system call at the operating system level really give us high levels of efficiency here, because we can still just really maintain a small number of threads for an entire Go program. One thread per core, and this thread for our network polar. Again, if that Go routine is going to be doing any sort of networking, it's going to move here. So anything we can do asynchronously to keep this thread busy is what we're going to want to do. Now, there may be times where you're on an operating system that doesn't support asynchronous system calls, or there's some system call that we can't deal with asynchronously, or you're dealing with CGO, where you've got a C library that no matter what we do, we're going to be blocking that thread. When that happens, the following thing happens with the scheduler. Now, we don't want this to happen, but and most of what you're doing won't do this, but watch what happens. This Go routine wants to make a call. It's now going to block this M. There's no way to do it asynchronously. There's no way to move it to the network polar. So what the scheduler is going to do is going to detach that M. There it is, and the G. It's going to detach it off the P, let it block, right? This is blocking calls right here. So we're now blocking that M. And what the Go scheduler is going to do now, right? This is gone. It's going to come in and bring a new thread in. Here's M2. We now have an extra thread in our Go program. But guess what? We're still a single-threaded Go application, because now that Go routine is in that executing state. There it is. And we're still processing the run queue, even though that other thread out here is blocked. Now, by default, in this scenario, you can have up to 10,000. You can have up to 10,000 of these threads before your Go program faults. That really shouldn't be happening. I mean, if that happens to you, you reach out to me. I want to see that, okay? And maybe about once a year, I see it on the mailing list. But eventually, the blocking call is done. The Go routine is over here. Our main Go routine goes back into a runnable state. And then this thread is put on the side for later use in case it happens again. Again, this is not the normal scenario. The normal scenario is we're using the network polar to handle asynchronous system calls to keep that just one thread in our system. This is the situation where the scheduler identified that that M was going to block, in which case we've got to replace it to keep things going. Very, 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 very cool stuff. And like I told you before, that this is a work-stealing scheduler. So the other idea is that if we are in a multi-P environment, right? We're in a multi-P environment. And let's say this P now has no more work. One of the first things this P is going to do is look in the global run queue to take in some work. It found that. It's now executing this. It might even decide, hey, you know what? You're overloaded over here with Go routines in a runnable state. I've got no work to do. I'm taking this Go routine now, and I'm going to put it here. So there's a special stat in the scheduler trace that shows when a M on a P is spinning. We call that spinning. So anytime in the scheduler an M doesn't have goroutine work to do, but it's looking for goroutines, then that M is going to be spinning. Ideally, we want to keep the M busy at all times because we don't want, from the operating system point of view, the operating system to say, hey, you know, there's an M on my core and it just went from an executing into a wait state. Let's pull it off and context switch. The more we can keep these M's busy, the more time they get, the more work we can get done. This is one of the mechanical sympathies here around the Go scheduler. The idea is that we want to keep these threads busy. Let me show you a scenario here that hopefully should bring this home for us. Imagine we were writing a traditional multi-threaded piece of software. Let's say we're using C. We're using real operating system threads. And let's say that even if we're on a multi-core machine, here's thread 1, here's thread 2. Even if we're on a multi-core machine and these threads could run on their own core, let's say that these two threads need to pass messages back and forth. This is I/O-bound work. OK, no problem. So what we're going to do is wait for a context switch. We get it. We're now executing on the core. We do a little work. We send a message over here. And once we send the message, we're going to have another context switch because during this transition, we're going to go into a waiting state, right? We're now waiting. Now we're waiting for a context switch because this thread was in a wait state. It now is signaled somehow that it's got a message waiting for it. So we get a context switch. There it is. It can now get the message, process it. It sends a message over. Now we get another context switch, another context switch, context switch, context switch. Every time these two threads want to pass a message or do any sort of orchestration, we're going from waiting to runnable to running to waiting to runnable. And these threads are coming on and off these cores. Remember, I told you this context switch is very, very expensive. But imagine that we're not dealing with operating system threads directly. Let's say that we're in Go. Let's say we're working with goroutines. In fact, let's say that we decided that we're going to run on a single P. Let's say that we decided what we're going to do is run on a single P. We're single threaded. Now, this chart doesn't change. We need a context switch to run. But our context switch is happening on the M, which also is super lightweight because a context switch in Go is faster because the scheduler knows what the goroutine is doing, and therefore it can save a lot less state than the operating system does. So goroutines are not just lightweight, but they're also much faster in terms of their context switch on the M. So look, we get a context switch, no problem. Now this comes off. Now this comes on. Now this comes off. Now this comes on. Now this comes off. This on. But we still have all of that same sort of kind of I/O happening with the goroutines. But what I really want you to understand is this. During every single context switch here in Go, in our application, from the operating system perspective, that thread never went into a waiting state. From the operating system's perspective, that thread is always busy. It's always in a running or a runnable state. What Go has done, what the brilliance is of this scheduler, is Go has turned I/O-bound work into CPU-bound work. And when you have CPU-bound work, more threads than cores can only add load because we don't need the extra context switches. Those cores will never be idle to do other work because this thread has always got work to do. Think about it. Go has turned I/O-bound work into CPU-bound work. Oh my God, how brilliant is that? It really is. It's just this brilliant piece of engineering. And what we're going to find out is that this P also takes a huge amount of cognitive load off of us because I don't have to think about thread pools or goroutine pools anymore to figure out throughput and efficiency. In many cases, we can do one of two things. We could just throw a lot of work at the scheduler and let it distribute that across our Ps and do that efficiently. Or we could still take the ideas that let's just leverage a small amount of Goroutines, maybe one per P, and keep them busy on that end. There's tons of little things we can do. We'll talk about this stuff. But I really wanted to show you here how the mechanical sympathies of the Go scheduler, how it sits on top of the operating system. We don't want to rewrite the operating system schedulers. Schedulers are complex. They understand hardware. They understand how that hardware is laid out. They understand NUMA. They understand a bunch of things. And the Go scheduler is able to sit here. And again, the real magic is that the Go scheduler turns IO-bound work into CPU-bound work, which means it minimizes or reduces a full amount of load off the OS. And we manage our concurrency and our parallelism here in Go. So now that we've reviewed how the operating system schedules work and the Go scheduler works and how it sits on top, we now want to start learning how we manage concurrency in Go. But I want you to understand something here. Go routines are chaos. Look, I've got 5 kids. When I tell people I have 5 kids, usually what happens is the person bends over and goes, oh my God, you got 5 kids, I got 1. How do you do that? And I always say I just travel a lot and get out of town, right? I get out of town. Well, you can't get out of town when you're dealing with managing concurrency and multi-threaded software in Go. You're in town. You're in the house. You've got to deal with the chaos. I always like to think of Go routines as children, right? And if you don't have children yourself, I'm sure you've got nieces and nephews, right? And you know that children are chaos. Like one's running out to the pool, one's running up the stairs, one's running across the street, one's about to pull off their diaper. Which one are you going after? Like, I'm going after the diaper, man. I know that is a big mess. But the reality is you only get one. You only get to go after one of those kids when they're running in parallel, right? And there's only one of you. So really what we're going to be talking about for the rest of this section is really what I always say, a parenting class. I've got to teach you how to manage your children. Every time you bring a Go routine into your program, you're bringing a child into this world. This is now Parenting 101. And I've got to teach you how to keep these children safe. I've got to teach you how to keep the house from burning down, because multi-threaded software development is complex. Now, I told you there's 2 aspects to this. There is synchronization and there is orchestration. And there's tons of rules around managing concurrency, like this one. You know, you're not allowed to create a Go routine or bring a child into this world unless you know how and when, right? You're not allowed to create a Go routine unless you can tell me how and when that Go routine is going to be terminated before the Go program shuts down. My equivalent to that is you're not allowed to lock the house up at night till you know that those Go routines, those children, are safely tucked away in their beds, okay? You've got to be managing this. You've got to have known control over everything that's going. Synchronization, orchestration. So what I'm going to show you right now is some basic orchestration using a wait group, and to show you how we are going to keep our programs running until we know that the Go routines or these paths of execution are done. This is basic orchestration using wait groups, but we'll also learn how to create Go routines. After this, though, we've got to learn about data races, and we've got to start learning about synchronization and eventually orchestration, because without it, you're going to have some really nasty code, complexity, bugs. But here we are. Let me do my best here to try to get you where you need to be so you can start really being successful here where the less is more, less complexity is more attitude. So let's start with this program right here. Now, on my Mac here, I have an 8-core machine. And I want to run some of this code as single-threaded. So what you're seeing on line 17 is me calling the GoMax procs function from the runtime package, telling it to knock my P's from 8 to 1, single-threaded. And it's capitalized because it represents an environmental variable that this can override. And we used to have to use this back in the day because prior to 1.5, your Go program only came up single-threaded or 1P, regardless of the number of cores. From 1.5 since, we match P's to cores that are identified on the host machine. Okay. Now, what you're seeing next on line 23 in the main function, and again, I apologize, this is being done in a init, so it happens before main, In the main function here on line 23, what you see is the wait group. In fact, we are creating a value of type wait group set to its 0 value, naming it the variable WG. And we're calling WG.add2. I don't want to see you calling add1, 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 add1. In other words, the wait group is a synchronous counting semaphore. We're going to keep a count of all the existing goroutines that we create, so we know that we're not going to shut down until that count goes back down to 0. So I want to do add one time for the number of goroutines we're going to create. If you don't know how many goroutines you're going to create, stop. You're going down a very bad path, and we're not going to call add one as they get created. We call add one time up front. There it is. So now we know we're going to be creating 2 new goroutines in this program, and I don't want this program to end until those goroutines are finished doing their work. And this is where we get the wait call on line 42. The wait call is a blocking call. A wait group has 3 APIs: add, wait, and done. Add is adding to the counting semaphore, done is decrementing, and wait will block until the count goes from 2 to 0. Again, we don't want main returning until we know those other goroutines are done. And what you're seeing now on line 29 and 35 is the declaration of a literal function, then the execution of that literal function. Remember, literal means unnamed. These are unnamed functions. And then the use of the keyword go in front of the function call. This is essentially going to define, call, and then execute this function as a goroutine, a separate path of execution. I also want you to notice we're using closures. I like closures. I think it helps simplify how these literal functions access data. You can pass it in. We're going to have to do that at some point today. Closure bugs can be nasty, but the GoLint tool, which you should be using, can detect closure bugs, and you'll be okay. So what these 2 goroutines do is call a named function called lowercase and uppercase. These functions aren't doing anything special. They're just displaying the alphabet in lowercase or uppercase letters 3 times. So look at the full structure of this Go program. Orchestration with the wait group. We're going to create 2 goroutines. 2 goroutines. Go ahead and create the first goroutine. Have it execute lowercase, and then through our closures, call done to decrement the wait group from 2 to 1. Then you run uppercase, decrement the wait group from 1 to 0, and you wait here until those goroutines report they're done by decrementing the wait group. Understand, when all things are equal, we do not know what the scheduler is going to do. There is no predictability on whether this function is going to execute first or this function is going to execute first. They're both going to be essentially created within a very narrow set of nanoseconds of time here. So by the time the main goroutine goes wait, okay, which is going to force a context switch, we don't know what the scheduler is going to do, whether it's lowercase or uppercase. All right, let's run this program. I'm going to go get the path of this program from the repo. I'm going to come over here to the terminal window. I'm going to call go build, and then I'm going to run it. What I want you to notice is that the second goroutine that we created, this one here that runs uppercase, the second one we created is the one that ran first. So you can see that this is a concurrent program. It didn't run in the order that we put things in. The scheduler turned around and did that. Now I could run this a million times and maybe it runs the same, maybe it doesn't. Again, when all things are equal, the scheduler is going to look and feel preemptive. It's undeterministic. Okay, great. So we've seen this. But what happens if I turn around and I forget to call wait? Look, I forget to call wait. I pull it out. Let's see what happens here. Go build, run it. There's no output. Start waiting, terminating. What happened? Well, this time when I pulled the wait call out, the main goroutine got to finish its time slice, which meant main returning, which meant this program terminated. These 2 paths of execution that we created never got a chance to run. This is almost a race condition too, because we're racing to see if this program ends before the scheduler makes a decision. Now, I got to understand that orchestration and synchronization must be guaranteed or it doesn't work. It might appear your program is working, but without the guarantee, real guarantees of synchronization and orchestration, that you're just getting lucky. I want to show you this idea of luck by using a function called goSched. Now, I don't want you using the goSched runtime function in your production code. This, however, can be brilliant when running or building tests that have to create chaos, because what goSched does is it makes a cooperating request. It is telling the scheduler, I'm willing to give up my time on the M. But the scheduler doesn't have to listen. The scheduler can do whatever it wants. This is a request. It's not a demand. Wait was a demand. Wait said, I want to wait here. I demand that we wait here until the semaphore count goes to 0. goSched is a request. I request that you let some other path of execution run, but it's not a demand. Now, let's see what happens when I add it. It looks like the program worked. It looks like our request to run the other Goroutines were taken. But I understand something. There's no guarantees here. The scheduler, I could run this 1,000 times, and the scheduler can make any decision it wants at any given time. So don't think this program worked because it didn't. We got lucky. This is why multi-threaded software development is complicated. We need the ability to know what we need, when we need to demand, and when we don't need to demand. And demanding comes from synchronization and orchestration. Right now, there is no orchestration going on here. This is purely a request. However, again, we could create a huge amount of chaos in our Go tests by causing the Go scheduler to just, in our kind of requesting way, randomly make context switches. We don't do this. There's no guarantees here. That was bad code. Let's go back to this. Now, what happens if I forget to call done? This happens in Go programs, right? I forget to call done. I forget this program, this Go routine, forgets to report that it's done. I don't know. Let's build it again. Let's run it. Notice this time that I have a deadlock situation. Yes, I have a deadlock, and the stack trace is going to tell us that our deadlock is on line, let me bring this out a little bit here, on line 42. Let's go look on line 42. The deadlock is on the wait. It's absolutely right. The wait group can no longer get to 0 because we no longer are calling done. Now, the Go runtime has a very simple deadlock detector. It's simple because all it can identify is when every single Go routine is now in a waiting state and can never move back into a runnable state. If you have one Go routine that can continue to run, we walk away from this deadlock detection. So we want to try hard not to create Go routines in our services that kind of spin on a timer. You're walking away from some of this deadlock detection. Yes, it is simple deadlock detection, but it is there. You're seeing it. This is bad. The same thing can happen if we don't set the wait count appropriately. I mean, look at this. Let's say I set the wait count to 1. That means as soon as one of these Go routines finish, the wait group will go to 0. Again, we're going to have some chaos because we're not really managing concurrency. We're not waiting for both Go routines to finish. Look, the Go routine doing capital letters just finished, and we don't see the next one run. This is all bad races. This is not proper orchestration. Synchronization orchestration is about demands around guarantees that things happen in the order we need, or we're waiting for things to finish before we move on. So the wait group is a great way of doing orchestration when we don't need anything back from the Go routine. We just need to maintain the semaphore count. Now, let's add a little more complexity to this piece of code here. And what I'm going to do is spell example, right? And what I'm going to do is come in here and look at this next example. OK, brilliant. Example 2. Now, we're going to take the base pattern again of wait group orchestration. Notice I'm knocking my piece down to 1. I've got my wait group. We add 2. Wait group orchestration here. I've got my 2 Go routines being called and run as an independent path of execution. And then on line 42, we wait. Brilliant. But this time, we're going to do a little bit more work. This time, we're calling print prime. And the print prime function identifies prime numbers from 2 to 5,000 and displays them on the screen. There are lots of system calls going on here. And this work is going to take a lot longer than the other work. What's nice about this program is we're going to be able to see context switches and see that we're not able to predict when the context switch is going to happen. So let's build this program. Here it is. We build it. I run it. There's a bunch of output. I'm going to go to the top. And you can see the second Goroutine started again. That's, from my perspective, random. And what I'm doing is I'm looking to see when a context switch happens. And it looks like B is getting a really good run here. And I'm going to keep going. Oh, there it is. OK. So we now have a context switch after the A Goroutine. After the A Goroutine got to prime number 3833. Let's write the right one here. 3833. Then that A Goroutine, or the B Goroutine, now contexts to A. Now if I keep scrolling, what do we see? What do we see? What do we see? Does the A Goroutine get to finish? Nope, it doesn't. There it is. Here's another context switch. A went to, what is that again right there? 3041. 3041. There's a context switch. Then B picks up right where it left off. B finishes, and then A finishes. So then B finishes, and A finishes. So we did see some context switches. What I want to really show you is that these context switches are not predictable. I'm going to run this again, and it's not going to be 3833, okay? In fact, I have no idea what it's going to be. It's really not possible to predict the output of this program. So let's run it again. Let's scroll to the top. B started again. That's fine. And here's our context switch. And where did it happen? It happened at 3691. So this time it happened at 3691. Again, I couldn't even predict that. And if I just look to see if A gets to finish or not, look at what we're doing here. Oh, there it is right there again. And I see that we're at 4159. 4159. Look, A got a much larger run on this run here. I imagine that it's going to finish. It finishes, it finishes. OK. So my point here is that even though this is a cooperating scheduler, OK, because the scheduler is doing the cooperating and not us, it looks and feels preemptive. When all things are equal, it is undeterministic to know when the scheduler is going to make a scheduling decision. I just showed you that with this piece of code. I have no idea, if I even run it again, where this is going to happen. And I've run this before where I see even another set of context switches before it finishes. But let's now bring this completely full circle and go to one more example. This time, let's go back to the original program we had, but just make two minor modifications. One, let's run this now in parallel. Let's use two Ps, which means two threads. At this point now, what we're going to have is not just one P per thread, but two Ps, P1, there it is, M, P2, M, and since I'm on a multi-core machine here, these two M's are going to be able to run in parallel. In fact, our Goroutines are going to be able to run in parallel. So maxprox2, wait group orchestration. We're going to create two Goroutines. There it is. I'm using a full literal function this time to do all of the work. There it is. Do the alphabet in lowercase 3 times, then report that we're done. Second Goroutine, do everything in alphabetical uppercase letters. Sorry, then report that we're done. And then we have the wait. So in this case, these two Goroutines, they're going to be running in parallel, making system calls, which means now the operating system is going to be handling synchronization on the system calls. We should see a mix of output when I run this program, which we didn't see before. If I run this enough times, we should see, I'm going to look down here, you should see here that we now have a mix of output. This one's a really nice one. We see a good mix of output right here on this line right here. You can see lowercase, uppercase, lowercase, uppercase. We're running in parallel now. And this has almost nothing to do with the Go schedule at this point, It's the operating system allowing these threads to run in parallel, and their system calls are now being synchronized. So you could see here that now that we've went from one P or thread to two, we're now a multi-threaded Go program. Goroutines can run in parallel, and this is where synchronization orchestration really become important. See, Go made it super simple to create these paths of executions or Goroutines, but you still have the burden, and no language can take care of this. No runtime can take care of this. You still have the burden of synchronization and orchestration. I've shown you weight group orchestration. So the next thing I really got to show you is how to deal with synchronization in the language. Welcome to Lesson 9, Data Races. This is where we start learning important topics around synchronization and orchestration, but we're really going to focus around synchronization here. These are the two things you have to worry about as a multi-threaded software developer: synchronization and orchestration. And data races are one of these places where it is the nastiest bugs you ever want to have. This is when we've got at least two Goroutines where one's doing a read and one is doing a write at the same time at the same memory location. This is bad. So I'm going to show off some data races. I'm going to show off the race detector tool. I'm going to show you ways using atomic and mutexes to fix those data races, and we're going to learn a little bit more about our mechanical sympathies for how the hardware works. Okay, we're now about to talk about data races. And what a data race is when you've got at least two paths of execution, like two Goroutines, accessing the same memory location at the same time, where one is doing a read and the other is at least doing a write. I mean, they both could be doing writes too, and that would be a data race. And that is bad, okay? You cannot be mutating memory against two paths of execution at the same time. We're going to have data corruption. And this is where synchronization comes in. There's two things here. There's synchronization and orchestration. We're focusing on synchronization right now in this data race section. The best way to think about synchronization is if you were to Starbucks, okay, and you got in line because you want to get some coffee, and now you're in line, you're waiting for your turn to get up to the counter. Anytime Goroutines have to get in line, that is a synchronization issue. But once you get to the counter and you start talking to the person at the register, you now have an orchestration issue. We're having a conversation, we're exchanging money, there's data going back and forth. That is orchestration. And we have these two problems, synchronization and orchestration. And your biggest job is to know when it's a synchronization issue, when do we have to get in line, and when it's an orchestration issue, when is there a workflow going on. Now, again, a data race is when you have two or more Goroutines where one's doing a read and one is doing a write to the same memory location. That is really bad. We cannot have that. But we have some other really special things also happening at the hardware level. We really have value semantics at the hardware level. We've got to appreciate this when we start writing multi-threaded software, because it can really hurt our performance. Our caching systems, though they're helping us try to reduce latency to main memory access, we could actually be thrashing memory as well if we're not careful. Now, I am praying that you went back and watched this entire video, that you didn't start here in concurrency, because in the arrays section in data structure, we really talk about cache lines and how these things work, and it's going to be very important for you to watch that stuff before you come here. I'm going to assume that you've seen all the array and cache line stuff as we get going. Now, let's talk about the cache coherency problem and how these value semantics could come in and hurt us. And then we're going to talk about something even more interesting to me, which is fault sharing, all around this idea, again, of the cache coherency problem. So let's start with our 4-core processor. Now, let's say we have our 4-core processor. Here it is. And we've got our core 1, 2, 3, and 4. And we know that every one of these cores has its own L1 and L2 cache with the shared L3. Now, I said that the hardware has these value semantics because remember what I told you. Value semantics means that we're always operating on our own copy of the data. So imagine this. I've got a global variable in a sense. We call it counter. Starts at 0. and I decide to launch 4 goroutines. Okay, let's call this goroutine 0, goroutine 1, goroutine 2, and goroutine 3. And these 4 goroutines are going to run in parallel. We're going to get them to run on their own P, on their own M, and therefore they're going to execute against their own individual core. Now, we have if we want every goroutine to be read, modifying, and writing C, we now have a synchronization issue. We've got to make sure that only one goroutine reads, modifies, write at the same time. This is where we're going to need things like atomic instructions, which are at the hardware level, and mutexes, which are just above that, okay? We're going to show you soon how to leverage your atomic and your mutexes to create these atomic instructions or make multiple statements atomic. But let's get back down to the hardware for a second. I want you to remember something here. If every goroutine is going to take an opportunity to read, modify, write C, then a copy of C has to be brought in to each core. There it is. That's our copy of C, right? The cache line that C is on, wherever that is going to be brought in. Now, this is where things get interesting. Let's say we're going to use our atomic instruction, since it's a counter here, to do synchronization. That's fine. That means that when goroutine 0 decides to perform a read, modify, write to turn this from 0 to 1, then through the magic of hardware, the hardware is going to say, OK, G1, G2, and G3, if you plan on doing this, I'm going to put you on hold, OK, because G0 on core 1 is doing its thing, and we're going to make sure that that happens. But look at how we're also going to be able to be thrashing memory here. If we go ahead and increment this cache line to be 1 to 0, then once we modify this cache line, through the magic of hardware as well, through these snooping protocols, we're going to be marking these cache lines dirty because we've now just updated this one. We're going to probably, those results will go back there in main, but we've updated this. This is now really the current right state of what C is. C isn't 0 anymore, C is 1. But our copy of the cache line still has the representation of 0, and we've marked it dirty. So now when goroutine 1 gets a chance, right, through synchronization to modify C, it's going to identify that the cache line that it has is dirty. It's not the true. It's going to have to go out into main memory to go get a copy of the current one. And now this isn't going to be dirty anymore, right? And then it's going to increment this from 1 to 2, which is brilliant, right? And we're going to have synchronization too. But once we do that, it's going to mark that cache line dirty, and it's going to mark this cache line dirty again. Whoa. Now remember, these increments are probably happening across nanoseconds of time. So as the synchronization is in place, which is still a cost, right? We're going to be constantly thrashing through memory on every single increment, that 107 clock cycle latency hit to bring this back in, because we have shared this value across all 4 cores. And if you've got a 36-core processor, this is going to be even worse, especially if you've got multiple processors in there with multiple cores. All of that processor communication that we're talking about internally here also has to happen outside. This is very, very nasty. We have to be very careful about global variables and global counters in a multi-threaded situation, because we're not really just referencing this one value and updating it. Remember, we've got value semantics at the hardware level to reduce access to main memory costs. And therefore, as we share data, right, accessing data like this across these cores, we've got some other problems. But there's also something here called false sharing, which is super interesting. And false sharing occurs when you don't really have a synchronization problem, but we still have the cache coherency issue. Imagine we said, OK, I don't want to increment the same global variable across all my cores. Let's bring our processor back into play here. So here's our processor again. Here it is, core 1, core 2, core 3, core 4, L1, L2, and our L3. And this time what we say is, even though we're going to be running a goroutine across goroutine 0, goroutine 1, goroutine 2, and goroutine 3, we're not going to have them increment the same counter. What we're going to do is have them increment their own counter, 0, 1, 2, 3. Let's just say we did it like that. Now, we don't have a synchronization issue anymore. The address for index 0 is completely independent of the address of index 1. So I don't need any atomic instructions or mutexes. When G0 wants to increment its counter from 0 to 1, it shouldn't affect what G1 wants to do, which is from 0 to 1. It won't affect necessarily what this wants to do, 0 to 1, because they're all accessing their own independent memory location, and we don't have a data race. We don't have two goroutines trying to read and modify, right, the same memory location at the same time. However, remember our value semantics at the hardware level. Just because we don't have a synchronization issue, again, doesn't mean that our cache coherency problem doesn't exist. This array is still going to fall on the same cache line, that 64-byte cache line. So even though the address for 0 is not the same as address 1, well, the cache line for the entire array is going to be duplicated across all of the cores. And so though we don't need an atomic instruction when G1 wants to do a read, modify, write against this, or G0, and G1 wants to do a read, modify, write against that, even though I don't need the atomic instructions anymore, right, or the mutex, however one we choose. However, what's going to happen is when G0 read, modifies, write index 0, it's still going to mark all of these cache lines dirty. In fact, every one of these increments will continue to mark these cache lines dirty, and we're going to have to come back out and come back in. So we're still going to be taking the thrashing of the memory because these counters are sitting on the same cache line. Multi-threaded software is complicated, especially when you've got data that you're working with that is next to each other, even though you're not necessarily conflicting. That's the fault sharing, where you've got data access patterns to memory that is next to each other, even though they are unique, but they fall on the same cache line. Look, we essentially are sharing the data. So as we continue to learn about data races and synchronization and orchestration, and as we start moving into the tooling and we do some more live coding, I'm going to bring this stuff back, because anytime you have a global variable, we've got to worry about synchronization, because if we got multiple paths of execution, you can't have a read and a write happening at the same time. But we also have to worry about data access patterns, even if the data is unique, that is next to each other, because we don't want to deal with either fault sharing like this is, or we don't want to deal with cache coherency problems where all we're doing is thrashing through memory because copies of that data is being leveraged, modified, really that's our problem, across all these cores. So we're going to bring back the cache coherency and the fault sharing issues as we continue in this class. I'm going to bring them up because, again, when we're writing multi-threaded software, we've got to be able to see that type of linear performance growth as the number of cores increase. We want to see this type of growth in our performance. If you start seeing things like this, whatever that is, that means we're not being mechanically sympathetic. It could be our cache coherency issues where we're thrashing through memory. So I'm going to keep this stuff in mind as we continue. And one of the first things we're going to do is just look at a very simple data race and look at ways that we can correct the code to make sure that we have no synchronization issues. OK, so we finished talking about the cache coherency and fault sharing issues, which are really interesting when it comes to multi-threaded software. But what I want to do is start off with a very simple data race problem. I think if we can look at a simple data race, then you'll get a better understanding of what we mean about synchronization here. So in this piece of code, what we're going to do is we're going to have a global variable right there on line 16, and it's called counter. So there's my counter variable. It's my global counter, right? And what I want to do is launch two Goroutines. Goroutine 1 and Goroutine 2. And what these Goroutines are going to be doing is incrementing this local counter, right? I now have a synchronization issue. You get to go, you get to go, you get to go, you get to go. This is not orchestration. They're not talking to each other. They need to get in line and take a turn in incrementing the shared state, which is counter. OK, great. So I go ahead on line 21. I define a constant of 2 for two Goroutines. I use my wait group orchestration mechanism, because we're going to have two Goroutines. I'm going to manage that. Once they're done, then we can shut this program down. So we add 2. And then in the loop, I go ahead and I use our literal function, okay, literal function construction here. I call the function down here, right here, and we put the keyword go in front of it. There it is. I now have my Goroutine 1 and Goroutine 2. There it is, right there. And then these Goroutines do 3 operations here. It's a read, modify, write. There it is, read, modify, write. So basically, the Goroutine comes in, it does a read, does a modify, writes it back, right? Read, modify, write it back. Then this can come in, do a read, modify, write it back, read, modify, write it back. So every time we run this program, we should get the answer of 4. So let's navigate to where this program is real quick. And we're going to do a go build, and we're going to run it. Now, every time I run the program, we see exactly the output that I'm expecting. We have the read, the modify, and the write, just like we drew it here. 2 Goroutines doing 2 increments. The answer should always be 4. The answer should always be 4. And every time I run this program, we get the answer of 4. I'm happy. This program's working. We put it in production. But we've been running on bare metal. And one day we decide we're going to move to the cloud, which are much noisier and busier machines. And once we do that, things start to change. Because understand that there's nothing atomic going on with these statements. And to prove it, what I'm going to do is just add one more line of code. I'm going to add a print statement here, which is a system call, to display value, the local variable, before we write it back to our global state. Watch what happens just by adding this one line of code on line 38. Let's build it, and let's run it. Do you notice that the final counter is no longer 4, it's 2? And do you notice that this doesn't say 1, 2, 3, 4, it says 1, 2, 1, 2. How is it that just this line of code here has suddenly changed the behavior of this program, and for the worse? How is it, and how would that affect us? How could, when I said we went from bare metal to the cloud, it's a noisy machine, how am I really trying to simulate that? Let's go back to our chart here. Okay, let's do this all over again, now with the print statement in place so we can see it. Okay, brilliant. So what do? We again do our local read. There it is, read 0. And we do our local write. There it is. But when it comes to the print statement, remember that is a system call. And now what we're seeing is the scheduler going, oh, you want to make a system call? Well, we're going to now move you from a running state into a waiting state. Guess what we just got? Context switch. This Goroutine comes off the P. Which now means that this Goroutine gets to run. No problem. It reads the global state, 0. It modifies its local variable, and then it goes to print, and the scheduler goes, OK, context switch. Now, once we've done the context switch, this system call's probably done, and the scheduler chose G1 again, which now means that it's time to write it back out, which it does. But this Goroutine has no idea that it stopped running. These Goroutines are kind of blind to that, right? They have no clue. So it does the write, it comes back and does the read, does the modify, and then what happens? Well, we've got another context switch, which now means we're back here. Now remember we talked about how at the hardware level in the caches, once one core changed something, it marked those cache lines dirty. Well, guess what? I don't have any special snooping protocols here to tell the Goroutine that its copy of the global state has changed. We have nothing here indicating to the Goroutine that what it's working on right now is dirty. In fact, this Goroutine doesn't even know that it stopped working. So what does it do? It goes ahead and writes back 1. Then it reads it, modifies it, and then we have another context switch. So this is why we're seeing some very nasty behavior, because this Goroutine here has no idea that the global state has changed, and we start in this situation where only one Goroutine is really doing the modification. Now the print statements can happen almost in any order. You're seeing 1, 2, 1, 2. Don't read into that with what I did on the board, okay, because now we're dealing with running really in parallel. I am running against 2 P's. Each one of these Goroutines is running on its own M, which is really running on its own core. And we've got other synchronization issues with the output. Don't read into that. What's important here is that print statement caused a context switch in the middle of these 3 lines of code. And therefore, these 3 lines were no longer atomic the way they were before. But we were getting lucky before. There were no guarantees. Remember, I told you synchronization orchestration requires that we demand, right, the synchronization there. You have to demand it. You can't just ask for it or hope it's going to happen. We've lost it. And I need you to understand that no line of code in Go is atomic either. You see this plus plus, which is a read, modify, write. A read, modify, write operation. I've kind of simulated a larger scale, but value plus plus is also at read, modify, write. You have to understand there are 3 lines of assembly language code behind that. And even at the operating system level, any one of those 3 lines of code can be context switched. And then that assembly into machine code could even be broken down into more like lower level instructions that any sort of preemptive context switch can happen. There is no one line of code, not even the one I've highlighted here, that is atomic. You have to demand the synchronization by coding it. That is your responsibility, all right? So we've got this logic here, and what I want to know then is how do we demand that these 3 instructions, or at least the increment of the counter, happens synchronously, okay? Especially in our multi-threaded environment where we're running on multiple cores. Now you've got 2 choices here. You can either use the atomic instructions or you can use mutexes. Now, atomic instructions are your fastest way to go because they're at the hardware level, okay? Well, the hardware takes care of synchronization, but they're limited to just 4 or 8 bytes of memory. They're great for counters like we have here. When you really have multiple lines of code that need to be synchronized in an atomic fashion, that's where our mutexes are going to come in. So let's start with the atomic instructions to clean this up. Start with the atomic instructions to clean this code up. Now, if I want to use the atomic instructions, I'm going to be using the sync/atomic package, the atomic package under sync. And the atomic package has a really nice API. I'm going to show it to you. But when we use the atomic package, we need precision-based integers. We can't just use int anymore. We've now got to specify specifically, are we using 64-bit or 32-bit integers? It has to be consistent across every platform that we're working on. That's just a constraint of the API. So I've moved counter now to a 64-bit integer. And we still got our constant of 2. We got our wait group for our orchestration there. But notice that I've taken all 3 lines of code out of the program and reduced it down to 1 call to add in 64. Now, if you've worked with the atomic instructions before in other languages, this API should look familiar. Look, add a 32 or 64-bit, or add an address, compare and swap. What that does is it compares 2 values atomically. If they're the same, then we swap the values out. Load is purely just for reading. Store is for writing. And the swap is a swap regardless of the compare. Basic atomic API set. And the way synchronization works here is by accepting an address in the first parameter. And all synchronization is at the address level. So if you've got multiple goroutines like we're going to have, calling add-in64 for the same memory location like we're going to have, then these two goroutines get in line. We have synchronization, they get in line. But if these two goroutines called the same add-in64 for different memory locations, they can continue to run in parallel. So it's the address, right, that the hardware is going to pick up on and then cause everything to go in line. This is our fastest way. But what if we really wanted to maintain our logic as before? I wouldn't necessarily do that here. This is the best way to do that counter work. But let's say we did have those 3 lines of code. I wanted to maintain the 3 lines of code, and I had to make sure that nothing interrupted those 3 lines of code. They had to run one after the other every time without any interruption. All right, this is where your mutex comes in. Now your mutex is going to allow you to create a block of code or multiple lines of code and treat that as one atomic operation. So this time we're just going to use the sync package, and since we're going to be making lines of code atomic, I can go back to my int32. Now I've made this mutex as a global variable here. We don't really use global variables. I'm just showing you mechanics right now. Most of the time a mutex should be a field in some struct, and once you have a mutex as a field in the struct, that struct can no longer be copied. Okay, a copy of a mutex creates a new mutex. This is all value semantics here. So make sure that we never make copies of values that have mutexes inside of them. But you see it's usable in its 0 value state. So this mutex creates either what we call a critical section of code that is atomic. Let me kind of draw out a visual of what I mean by a critical section of code that is atomic. I like to think of mutexes as creating rooms in your code. And so I could use this mutex and say these lines of code, whatever they are, these lines of code, right? Multiple lines of code. We have to make sure that they always run atomically, one after the other with no interruption. So we're going to put these lines of code in this room. And the scheduler kind of acts like a bouncer, just like if you went to the bar. All of these goroutines or people are coming to this room. They all want in, but only one goroutine or person is allowed in the room at any given time. Because if we allow multiple people in the room, we're going to have our data race, right? We're going to have our situation where you cannot be modifying, read and or modifying the same memory location at the same time. Or in this particular case, we can't let 2 goroutines execute these 4 instructions at the same time. So the scheduler acts as a bouncer. Now when you get to the room, what you're going to do is ask the scheduler, hey, I want a lock, 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 I want a lock. And that lock call is going to be a blocking call. And only one goroutine can get the lock at any given time. So eventually the scheduler is going to go, OK, you goroutine right here, I'm going to give you the lock. You get the lock, you come in, which means all of the other goroutines are now waiting their turn. Now, don't assume that a goroutine that gets to the room before another is going to go first. There are algorithms here to try to make things fair. But just because this goroutine got here before this goroutine doesn't mean this goroutine gets in the room first. It's just like when you go to the club, somebody shows up in a fancy car and they get in ahead of you. It's all the same. It is not deterministic which goroutine, when all things are equal here, is going to get into the room first, though the algorithm is doing its best to keep things fair. Now, once you're in the room, you're in it, you get to do these 4 things, and then you have to leave the room. And once you leave the room, this is when you call unlock. We're going to say unlock. That's going to free the scheduler at that point to come in and let another goroutine in. Again, we only allow one goroutine in the room at a time. So the mutex is giving us the ability to create a critical section of code to make sure this code executes atomically, no matter how many instructions. But there's a real cost to mutexes. We have to be aware of this, and that's latency. And the more goroutines that are waiting to get in, and the longer this goroutine takes to get out, the longer the latency is. This is technically back pressure internally inside your software. And we're going to want to be able to measure this back pressure, and you've got to reduce it. You've got to make sure you do the least amount of work that has to be atomic, because if you do more work that needs to be atomic, you're putting more latency or back pressure inside the system. But you've got to make sure that it is atomic. I've seen lots of code where they've tried to cut some corners on latency, and then these instructions end up not really running atomically. I'll try to show you an example of that. This is your mutex. So look at what we do here. We've got our two goroutines. We've got our wait group. We add two. There's the two goroutines again. And now here's the call to lock and unlock. Now, there's something that I do personally. You're not going to see this probably in other people's code. What you might have noticed is I created an artificial code block with the curly brackets that does create a new level of scope. But what I love about it is it gives us a visual in the code of what instructions we're trying to execute atomically. In other words, it's able to create the room. I love this. This is really important because there's another rule here, and I'm going to put my foot down. The same function that calls lock must call unlock. You cannot separate these calls between two different functions. You're going to miss a lock or an unlock, and you're going to have a deadlock situation. Remember, this goroutine doesn't call unlock. You now have a deadlock situation. All these goroutines are stuck because they can't get in. So I want the lock and the unlock to always be together. Always be together, okay? And some people like to use the defer. Now, we haven't talked about defer. Defer says execute this piece of code after the function that you're inside right now returns. So it's have the function do its thing, return, call the defer. I can't use a defer here because I'm in a loop. But what you might see a lot in the beginning of a function, at the very beginning of a function, is somebody calling lock and deferring the unlock. But I would want to see this type of code as like the first two lines of a function. That will be fine, okay? But I'm inside of a loop. If I do this, I'm going to be in a lot of trouble. Because Go doesn't let the same goroutine call lock twice. It's something that, again, goes about keeping things simple. There are languages like C++, I've done it in C#, where the same goroutine, or in that case thread, can call lock multiple times as long as it calls unlock. That doesn't exist in Go. One lock to one unlock. So look what we've done. We've now said we're going to lock these three lines of code. These three lines of code have to run atomically. There cannot be a context switch to another goroutine that also wants in this room. And by doing that, what we're going to now get, example 3, if we do that and I run go build, now what's going to be great is I now back down to 4. I have 4. And if I put the funct call in here, print line value, like we did before, remember, if I do that and then I build it and I run it, now we're going to still see 4, because what we've now done with the mutex is said, I don't care that we're making a system call here. That is atomic now, so we're going to have to wait. We just added more latency to our software by doing this print here, because we got to wait for the system call to get service. This would be a case where I'm like, yo, don't do the print inside the mutex. You've just added extra latency costs here. We got to just do the bare minimum, So always inside of a mutex, you got to look to validate we're doing the bare minimum, but we're still maintaining a full level of atomic, right? Everything is still atomic. I can tell you this, if I do a code review and I see something like this, which people do, this is a really bad smell. I've seen people do this and say, you know what, Bill, I want to get out of this mutex really, really quickly. So I'm going to do the following. I'm going to create like a local variable out here. We'll have to do that, value int. And what I'm going to do is go into the mutex1 to read the value out, Bill. Then what I'm going to do is value ++. And then, Bill, what I'm going to do is use the lock one more time to write it back. And look what I've done, Bill. I've made my mutex lock and unlock very, very fast. No, what you've done is lost all ability to have these operations atomic. Because even though your read is atomic, guess what? Your write here isn't. And that means another goroutine can still come in and read a dirty value. So if I see code inside of a function that's using the same mutex like this, lock, unlock, this is a big smell that we really don't have an atomic piece of code. These are code smells that you can find. So we're going to have the one lock and unlock here. We've got to make sure we do everything that we need and only what we need to reduce the latency cost. This is going to be your death. Remember I told you performance comes from latency on networking and I/O, latency on that garbage collection, right? How much pressure we put in there. The next thing is how we access data, to hardware. This is also going to be a big cost, right? What kind of back pressure do we create inside of our software? Now we're dealing with algorithm efficiency issues, but with latency because we can hold those locks way too long. But we've got it here. Now, one other thing is the read-write mutex. The read-write mutex says the following. It is okay to read memory. Reading memory doesn't cause a problem. It's only on the mutation. And what if you suddenly need 10 Goroutines to read something at the same time? There's no reason to synchronize that. That would be a waste of latency or back pressure. We only need to stop the reading if we want to write. This is where the read-write mutex comes in. So here's our read-write mutex right there. And what our read-write mutex does is it allows us to have multiple reads across that one write. Okay, so here we are. With our slice of strings. There it is. A slice of strings is our core data structure here that we're going to be synchronizing. This is all synchronization. So here it is. There's our slice. Remember that your slice is a 3-word data structure. I'm drawing it horizontally right now, which is our pointer, our length, and our capacity. 3 words, 3-word data structure. And our rewrite mutex also is usable in its 0 value state. Now, on line 23, we have our read counter. Again, this is going to be a global variable to track the number of concurrent reads. Now, look at what we do here. I'm going to go ahead and launch a single Goroutine whose entire job it is to write to this 3-word data structure. In other words, it's going to be doing an append. And then I have another set of Goroutines. I've got 8 Goroutines, 8 of them, whatever I have here. And they're going to be doing reads. They're going to be reading this data structure. All of them can read at the same time. That is not a problem. It's the write that hurts. So look at what we do. There it is on the lock. Anytime we want to do a write, we have to lock. Need the lock, and then we're going to do the unlock on the write. What this is going to tell the scheduler is don't let any activity go against this data structure, or these lines of code in this case. And these lines of code are doing 2 things. They're reading the read counter, and it's doing an append on line 71 there to modify this data. And then what we have on the reader, which we've got multiple Goroutines, is it's asking for the R lock with the R unlock. What that is saying is allow these Goroutines to go ahead and do this length call at the same time, because we know it's not modifying behind it. If you ask for an R lock, you better just read. You start writing here, we're going to have synchronization issues. And we're using the atomic instructions for this because 8 Goroutines might want to increment, add in 64, that local variable. This is really nice. So the scheduler is doing the synchronization for us. When we want to write, we ask for the lock. And when we ask for the lock, then that Goroutine here is going to have to wait for all the read locks to call read unlock. The scheduler will not give out another read lock until the writing finishes. Once the write finishes, we can give out the read locks. So if we run this program here, example 4, what we're going to see on the output is this synchronization between reads and writes. So here we started off with a length of 0 on the slice. And you can see how many Goroutines are reading the slice length at the same time. There was all 8. But eventually, randomly here, a Goroutine wakes up and says, hey, I want to write to the slice. I want to append a value. Notice that all the reads stop. We do the write. The length is now 1. And then all the reads start up again. Look at this scheduler doing synchronization for us through the mutex, because every time we want to write, we stop all the reads, we modify, we start reading again. It's a really beautiful data structure for dictionaries and things where you're doing multiple reads, and then eventually you have to stop on the write. So this read-write mutex is another powerful data structure for synchronization. But the read-write mutex is a little bit slower than your regular mutex. So if you truly need pure synchronization for everything, you got to use this. If you can have multiple reads happening while there's no writing, then you want to use that read-write mutex. So we've got that atomic instruction, right? When we're dealing with data that's 32 to 64 bits, great for counters. You could do some level of signaling with that too if you really need high performance signaling. And you got your mutexes to make lines of code atomic. And you can use the same mutex across an API set too. So you can have multiple instruction sets across a program using the same mutex. But remember, mutex is creating latency. Latency is death. So we've got to really make sure that we're doing less than more inside those mutexes. All right, so we've gone through the cache coherency, fault sharing issues. I've shown you how to do synchronization with both atomic instructions and mutexes. I want to show you something that's incredibly cool, which is Go's race detector. This has been in the language, I think it's been around since 1.3. And what's really brilliant about the race detector is that when it was introduced, they ran it against the standard library, and they found races in the standard library. I love when the Go language team creates tooling, and they find their own problems. It was really brilliant stuff. And the race detector is built in to the Go front end. So when we do Go build, it's built into Go build. It's also built into the Go test. I tend to use the race detector more on Go test than Go build, but I want to show you how cool this is because finding data races can be impossible. I've been in shops before where it's taken like 3 years to find data races, and now with this tooling we can find it very quickly. So let's go back to the original program we had where we didn't make these 3 lines of code atomic. Remember, we've got the 2 goroutines. Each goroutine is incrementing that global variable twice. There it is. And remember what happened when I put the fumped print statement in here, then the race showed itself just because of the output, right? But if I come back here and build this code again, Go build, and we run it, we remember we're still getting the right answer of 4. There it is, 4, 4, 4, 4. We don't get any visual clue that there's a problem with this code, that things are not atomic until I cause some sort of synchronization issue right here. So we do build again, I run it, now we're getting that 2. So remember that from the first example. But this is the cool part. If I just do the following, Go build dash race, then what's going to happen is this code's going to be built with the race detector. This code's going to run probably 25 to 30% slower, but now what happens when I run it? The program stops. We get a data race stack trace, and now we know exactly what's going on. You can see the stack trace said that you launched a goroutine on line 29, goroutine 6 on line 29, and then goroutine 7 had a read while there was also a write going on by the other goroutines, line 33 and 39. In other words, we had a unsynchronized read and write between line 33 and 39. If we look at 33 and 39, there's our read and there's our write. So yeah, there it is. The race detector identified that we're going to have data corruption, and it found it for us. Now, if you get a race detection like this, and it's not obvious why that race exists, then I need you to cause pausing, because once the race detector finds something, it should be obvious to you, if you have a good strong mental model of the code and it's not too clever, how 2 goroutines could have came to that point at the same time. But I've written code before that's gotten so out of hand and complex on concurrency that the race detector fires and I'm like, oh my God, how did I get there? And usually that means that we're not going to try to fix it with a Band-Aid or just throw a mutex at it. We've got to probably refactor some of that code to simplify things. Even when they ran this against the standard library, they found some interesting code that wasn't obvious to anybody on how that data race was there. So this is really brilliant stuff, and most of the time I run the race detector on Go test. I'll say Go test dash race for those tests that I have that are going to be running in parallel concurrent, where we're going to have multiple goroutines. That's where I tend to run it. I have heard of companies that run like a web farm where you have multiple instances of your service, and they might run one instance of a binary with the race detector on. And the general rule is this: if the race detector finds a race, guess what? You have a race. Fix it, okay? You've got at least 2 goroutines where one's doing a read and one's doing a write to the same memory location at the same time. But If the race detector doesn't find a race, it doesn't mean you don't have one, it just hasn't found it yet, okay? And I've been in environments where on my Mac, the race detector doesn't find anything because the scheduler isn't creating enough, let's say, wacky concurrency or context switches. And then the code moves to CI on some Linux platform, and CI keeps failing on the race detection. And you really should be running your tests with the race detector on, especially if you're running multi-threaded software. So this race detector is very, very powerful. You've got to make sure you're using it when you're writing multi-threaded software in Go. So what most people in Go don't realize is that accessing a map is not inherently synchronous. You don't get that for free. You don't get anything for free when it comes to synchronization and orchestration. You're responsible for it. And because so many people have had data races with maps, the language now has built into the runtime data race detection for map access. Now, you might think, whoa, 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 whoa. That means that we've added extra code to our map access in order to detect races at runtime. Yes, we have. I've told you over and over again. Go cares about integrity over everything, and there's a cost to integrity, which is performance. But they've really made sure that this little bit of race detection with map access isn't going to hurt you. So let's take a look at how that works. Now, I've created a global variable again called scores. We shouldn't be doing this in production code. I'm trying to teach you some mechanics here. We're using the make function to make a map that's usable, right, in its zero value state. Now, I've got a wait group. It looks like we're going to launch two Go routines by looking at the add call on line 18. And we go ahead with a Go routine, a separate path of execution here that is going ahead and adding that right there, right? We've got scores A++, so look at that. So we're incrementing, right? We're incrementing the key at key A. We're incrementing, it's an int. So at the end of the day, what's going to happen is we're going to be able to increment this 0, 1, 2, there we go. But at the same time, okay, the integer for the key at B, we're incrementing that. ++, 1, 2, 3. I've got two separate paths of execution, accessing the same map at the same time and trying to do a modification to, even though it is its unique key, because the map is a complex data structure, it doesn't matter. These are two Go routines trying to write to the same piece of data technically at the same time. This is a concurrent write. This is a data race. Now, prior to the version of Go we're running on here, this code would have ran in production, and you would have had data corruption everywhere, and you wouldn't have known it until after the fact. But watch what happens here now when I run this code here. Let's make sure we're in example 5. OK, there we go. Build, no problem. And I run 5. Look at this. The runtime detected a concurrent map write between the two Go routines. Look at that right there. And we also get this stack trace right here. Look at what it's saying. Line 22. Let's look at what line 22 is. Hey, that's one of those map writes right there. And it's showing us right there on that line 22 that we've got that concurrent map write going on. This is some really powerful stuff. And what this is giving it to us at runtime and making sure that this program shuts down before it really causes damage to data. I cannot stress this enough, that integrity is our #1 priority. When your program loses integrity, that software must go down. You either call panic or you call OS exit. And this has become such an important part of Go that they've moved into the runtime the ability to detect these concurrent writes, right, or again, right, concurrent writes here, into the map, even if we were doing read and write, into the map where we have a data race. So yay for Go about really being focused on integrity, and I don't care about maybe the little bit of performance, the few clock cycles, whatever this is going to take to get it done, because integrity's got to be our #1 priority. So let's bring everything together with this really nasty program that is kind of more practical in how data races really end up in production, especially if you're not using the race detector. And in the past, how, without having something as beautiful as a race detector, data races could get into production level code. So imagine this scenario. Ben and Jerry are fighting with each other. They got into an argument that one thinks they're more popular than the other. Ben thinks he's the most popular. Jerry thinks he's the most popular. So they hire a marketing company to track likes. And they start this like campaign where they want to know who is more popular. So let's take a look at some code we might write to solve this problem. There it is on line 16. We have what's called the speaker interface, one active behavior, speak. And what we want is users to speak up when they like Ben or speak up when they like Jerry. Now, normally what we'd be doing here is incrementing a like counter, but I want to be able to detect our bad data races here. So we're going to do something a little different, but imagine that every time you call speak, we're really going to be speaking up and showing our support for Jerry or Ben. So the Ben data structure has a name, it's Ben, and what we do in the speak, instead of right now incrementing our like against the Ben value, what we do is we check Ben's name. Now if Ben is Ben, life is okay, but if we had a data race, we could end up in a situation where Ben is not Ben. Ben might end up being Jerry. We'll see that. And when that happens, we'll spit that information out and we'll return false so we can shut the program down. So there's Ben, and here's Jerry. And Jerry looks exactly like Ben. It just has a name, and the code is implemented the same, except Jerry's wanting to be Jerry all the time. So there it is. We have our speak, which traditionally would increment a like, but Ben is checking valid that it's always Ben, Jerry's always Jerry. Now, we start the program up, and I create my Ben value. Here it is. There's Ben. Here's Jerry, right? We're really going to have our likes in here. And remember that we have implemented the speak methods against these concrete data values. Now I start right out of the box with our person interface. And if you notice there, I'm storing, using pointer semantics, Ben inside of there. So when we call speak against the interface, we can either call speak against Ben or Jerry, depending on which data, in this case Ben, is in there. Call speak, we would be incrementing that to 1, right? OK, great. So we start this campaign. Now imagine this is really a web service, right, with tens of thousands of requests coming in from Jerry and Ben's support. And here's a Go routine that simulates maybe one request or a bunch of requests coming in. And you can see here that what this Go routine does is it loads Ben into the interface and then calls speak. So that line on 65 is our write. It's a 2-word write in order to get Ben inside the interface. And then the call on 66 is our read. We got a write, a 2-word write, and a read, OK? And then what we have on is another Go routine simulating other requests coming in that say, no, Jerry is the write, is who I support, which now means we got to do the 2-word write, which says Jerry, and then we can call speak. So I've got like a data race here, right? Now I want to show you how quickly this code suddenly has data corruption. Let's build it, and let's run it. It doesn't take long for the program to say, Jerry says, hello, my name is Ben. This is an integrity issue. And understand the code didn't blow up. The very worst thing that could ever happen to you in a data race is your code keeps running. We'll explain why this code doesn't blow up in a second. But for it to say Jerry says means that the first word says that there is a Jerry pointer inside the interface, because this word is telling us which concrete implementation to call, which is Jerry. But what's happened is only half this interface has been written to before the other Go routine calls speak. So the pointer was still pointing to Ben. Remember, it takes 2 operations here. You got to change out what type of data is in the interface, and then you got to change out the pointer to the concrete data. Only half of the write operation took place before the Go routine called SP or speak. And so now suddenly, guess what? Ben got a like for Jerry. We wouldn't see this in code because it didn't blow up. The reason it didn't blow up is because these 2 data structures that we're using are identical. They have the same exact memory layout. So nothing's going to cause this code to blow up. Incrementing here is going to be the same as incrementing here. In our case, the names are the same. So since the data models are the same against all the concrete types, guess what? This code doesn't blow up. It keeps running. And we wouldn't even know about it until somebody in marketing said, you know what? I like Ben as much as the next person, but there's no way Ben is that much more popular than Jerry. It just statistically doesn't make sense. And now you're being asked, hey, you got a bug in your program and I need you to find it. Yet there is no stack trace, there is no corruption. I mean, there's no like code blowing up. There's no way to indicate where the data corruption is. This is why data races are nasty, nasty. Now, if I build this program using the race detector, there it is. When you use the race detector on a build, you have to build the binary and then run it. You can see how quickly the race detector identified that there is a race, right? Goroutine 7, Goroutine 6, and there, in this case, was 2 writes that happened at the same time that were not synchronized, line 76 and line 65. So we're seeing here that line 76 and line 65, we could see here that these 2 calls happen to happen at the same time on these passive execution. Yay for the race detector. Now you might say, well, Bill, you know what? Forget about the race detector. I would have found this regardless. And I'm going to say to you, no, you wouldn't have. What if I use go max procs to only use a single core? I am now a single-threaded Go program. Maybe I'm running this stuff in Docker on my local machine, and I've restricted my containers to just use 1 core because I'm trying to use resources cleanly, and I've put this all into my Docker containers. Now, I've run the race detector, which is really funny. Notice that the race detector still found a race with this. But let's do something. Let's rebuild the binary, okay, without the race detector. Do this again, and look what happens. The race is technically never happening because, since we're running on 1 thread, all of these reads and writes are happening in a synchronous way, but it's an accident. It's an accident. We're getting very lucky that every one of these 2 calls are happening atomically right now when I'm single-threaded. We don't see anything. Our tests are working in a single-threaded environment. Our code is working in a single-threaded environment. But probably what's going to happen is when this code moves to production, then we really start having a problem, because in production we're not doing single-threaded, maybe we're doing multi-threaded. So without the race detector, we're going to be in a lot of trouble here. And this, again, is a very classic historical way of how data races have entered production code and how nasty they are to find. Why it could take years to find a data race because there's no indication in the code. There's no indication from like stack traces or things blowing up. It's purely a problem of data corruption, and it becomes very difficult to find data corruption sometimes just by looking at code. Welcome to Lesson 10, Channels. This is the lesson you probably want to jump into first, and I'm going to ask you not to. Please look at all of the other lessons before you get here. It's going to help you tremendously learn about channels. Channels are how we handle orchestration in Go. And I'm going to teach you the signaling semantics around channels. I'm going to show you some very base signaling semantics. We're going to go to some higher level semantics. And then I'm going to show you how we bring it all together. So I'm going to give you new ways to think about channels around the idea of signaling. We're going to start learning about channels, and channels are a way of doing orchestration in our multi-threaded software. As we talked about, there's 2 things you have to worry about: synchronization and orchestration. And we've seen orchestration already with wait groups, when we just have to keep account of things and wait for Goroutines to finish. Then we started and we looked at the atomic instructions and the mutexes around synchronization. Remember, synchronization is about getting in line and taking a turn. Orchestration is about the interaction. And the wait groups really are not synchronization, it's orchestration, because we're waiting for a bunch of Goroutines to report that they're done, and the result there is just a decrementing of a counter. Channels are going to allow us to move data across these Go routine boundaries, and again do the orchestration, which is not in line, but finally an interaction. But before we can look at any channel code, I want to set your mind to the way you should be thinking about the behavior of channels, the semantics, is really going to help us then look at code, because I'm going to bring this stuff back. Because too many people look at channels as a data structure, a queue, a synchronous queue. And it's one of the first things I want you to get out of your head. Don't think about channels as a data structure. Don't use channels necessarily as a data structure first. We want to look at behavior. And the behavior we want to talk about is signaling. I always want to focus on the signaling behavior first, and then how the channel lets us implement that signaling behavior. Because remember, mechanics can teach us and help us how to debug things, how things work underneath, but it is the semantics that let us understand how a program is going to behave. Semantics teaches us the impact our software is going to have on the machine, with the mechanics underneath giving us the rest of that. So when it comes to channels, we're going to think about one word and one third only. We're going to think about signaling. Signaling is the semantic. Remember, pointers are for sharing and channels are for signaling. The idea is that a goroutine is going to send a signal to another goroutine. Now, when we start talking about signaling semantics, the very first thing that we have to talk about are signaling guarantees, guarantees of delivery. The idea is, do you need a guarantee that a signal being sent by one goroutine has been received by the other? This is the very first question we should always be asking ourselves when we need this type of orchestration. Does the sending goroutine need a signal that that sent signal has been received? Remember, if you listen to me, I'm using send and receive. I'm not using read and write. This is not I/O. This is signaling sends and signaling receives. Now, if you need a guarantee, we're going to be using the unbuffered channel. And if you don't need guarantees, then we can use a buffered channel. But I want to teach you where these guarantees come from first. So imagine the following scenario. I have a friend of mine, a colleague on my team, okay? And a lot of times I ask my colleague, can you do something for me because I've got some other things to do and you've got some free time. Hey, can you take care of this task? And let's say I gave them the task right here. Maybe this is a piece of paper with the instructions on it. Okay, so what I want to do is signal to this peer of mine, right, this buddy of mine. I want to signal with, the piece of paper, hey, can you get this task done? Now, I do this all the time, right? I'm always going over, let's call him Jack. I always go over to Jack and I say, Jack, can you do this? And Jack always does it for me. But last week, something bad happened. I asked Jack to do something for me. I gave him the instruction sheet, and he didn't get it done. Not only did Jack not get it done, when my manager came to me and asked me, has it gotten done? And I said, yeah, I gave it to Jack. My manager turned around and said, well, guess what? It didn't happen. And when I go to Jack about it, I find out that Jack really just threw me under the bus. He denied to my manager that it ever even was handed to him. So in this situation now, I have to make sure that I always get a guarantee that if I hand something to Jack, that he has it. This is key, right? If I hand something to Jack, I need the guarantee. And again, this is what we talk about signaling with guarantees. So how does it work? So this time, on this particular morning I come in, I've got work for Jack to do. Again, I've got to have a guarantee that Jack is going to gets this work, so he gets it done. And I walk into Jack's office. Now, this particular morning, Jack is not there. But I have a critical situation here. I cannot move on with the rest of my day until I hand this to Jack. And Jack is not here. And I have no idea when Jack is going to get in. So now I am stuck in Jack's office waiting for Jack to come in. No idea when it's going to happen. Eventually, Jack walks into his office, thank goodness. And when I see Jack there, I go and I hand him the piece of paper. Now, when you see me doing this, I am now in a sending situation. I'm signaling to Jack here, I'm sending. Now, in order to get the guarantee, what's going to happen is I'm performing the send, and now Jack is going to come in and perform the receive. Here's the send, here's the receive. And the guarantee comes from the fact that the send and the receive are now happening exactly at the same time on that, in this case, our piece of paper. Now, we get the guarantee because in this case, the receive happens before the send. The send came in, the receive came in, and Jack basically pulls this out of my hand. The receive happens before the send. Nanoseconds before the send, but it happened. And now what I can do is look in my hand and go, oh, look, it's gone. Jack must have pulled it out of my hand. Jack took it. I now have a guarantee that the signal that I'm sending has been received by Jack because the receive happens before the send. There's no way Jack can throw me under the bus. I have the guarantee that he has it. Now, Jack's got to go off and do some work, and in this time, I need the results back from Jack. Again, I cannot move on until Jack finishes this work. So I come back into Jack's office, and I'm like, Jack, let me have the results. And Jack's like, I'm not done yet. Now, because Jack's not done yet, guess what? I'm stuck waiting once again for Jack. Eventually, Jack finishes it. Jack performs his send. I come in for the receive. The receive happens before the send. Jack can go, oh, look, it's out of my hand. Bill took it, and the signaling is done. So understand something about the guarantee. We want guarantees. Guarantees are about what we talked about, right? That we have to demand guarantees. Things have to be atomic. Synchronization, none of this can be a guess. So guarantees are very, very important because they create consistency in our apps. They allow things to be predictable. Guarantees are important. In fact, if you don't really want guarantees, I got a ton of stuff I can sell you, right? Like, just think about that. I'm about to say I'm going to sell you stuff without a guarantee. You're like, whoa, 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 whoa. I mean, that's how important guarantees are. So the benefit here of this signaling with the guarantees is we get the predictability. We know what's going on. There's nothing random, nothing guessing. But there's a big cost. Remember, engineering is about knowing the costs, and nothing is free. And the cost of signaling with a guarantee is unknown latency. Remember, I had to wait in Jack's office for him to show up. I had no idea how long that was going to take. And then after Jack started working on it, I was stuck in his office one more time waiting for him to finish. I didn't know how long that was going to take. So if you want the benefit of guarantees, which, you know, we have to look at the problem we're solving, and we really do want to get guarantees as much as we can, then you've got to live with unknown latency. Now, let's say I can't live with the unknown latency here, and there's a good chance I can't. I'm tired of waiting for Jack. I'm tired of waiting in his office every morning while he finally gets into work. I'm tired of waiting for him to finish this thing so I can move on. So Jack and I have made up. Jack has agreed he's never going to throw me under the bus again, and I'm going to, I don't know, I'm going to buy Jack lunch every Monday for the next year, right? Like, I need this. I cannot wait. The problem now is I cannot deal with this unknown latency because I have to be a little bit more efficient. So we agree. So now this time when I come in the morning, as usual, Jack is not there. He's not there in his office. But I'm going to walk away from the guarantee. What I'm going to do now is have that buffered channel, which has some space. Basically, Jack's going to leave room in his office for me to put that piece of data on his desk. So now what we've done is I put the data on Jack's desk. I put it there and I walk away. Now, the reason why we no longer have the guarantee is because in this scenario, the send, the signaling side of the send, happens before the receive. I walk away never knowing when that's going to be received. I hope it's going to happen, but I don't know. This piece of data is technically in limbo, right? And I'm still responsible for it in a sense. Eventually, Jack will come in, he'll perform the receive, and he'll work on it. He'll perform his send back into the buffer channel where I can come in, and once the data is there, then I can pull it. Now, if I walk in to perform this signal with data, right, and there's no room on his desk, I'm now blocked waiting for him to make room. Well, if I come back in to get the results and they're not there yet, he's not done, then I'm going to block. So there's still potential blocking even if you don't want the guarantee. But the idea of walking away from the guarantee is to reduce latency, right? So if you walk away from the guarantee, and we're going to walk away from the benefits of that, less risk, predictability, all that, the idea is that we're trying to reduce the latency, right, the back pressure that we're creating on our app. Remember, we talked about mutexes need to be doing things very, very quickly, just the bare minimum to reduce the latency and the back pressure. There are times where we don't want the guarantee because that back pressure or the unknown latency is going to cost us more. Engineering is about understanding cost. Now, one of the other things I was sharing with you is the idea that we can signal with data or without data. And if you're going to signal with data, that's only a one-to-one exchange between one Go routine and another. What's nice about signaling without data is we can do a one-to-many if we want to do that. Many Goroutines can receive a signal without data, but when data is actually in flight, we're making a copy of data, it's a one-to-one. Now, when we talk about signaling with data, again, if you need the guarantee, we can use the unbuffered channel. If you don't need a guarantee, we can use the buffered channel. And we have concepts of like delayed guarantees, where a buffer or one could allow the wheels to just keep moving in a process where we're reducing latency, but as soon as we identify that there's a problem, we stop. I mean, how does something like that work? Well, imagine a situation where I'm in an orchestration mode with Jack, okay? And the idea is I'm going to pull a box right off the floor, and then I'm going to give it to Jack to do what Jack has to do with. So if I pull a box off the floor and I turn around to Jack and he's already done processing the last box, I can just give it to him. I can keep doing this. I can keep the wheels moving. There's no latency between my signaling on the send and his receive, because every time I turn around to send it to him, he's ready and he's available. That's great, right? And what we're going to do, though, is what happens if he's a little slower than I am. Then I'm going to be pulling boxes and I'm going to be waiting. Then he finally turns around and I hand it. When we get the next box, I turn around, I'm waiting, and then finally he turns around and he's hand it. If I want to reduce all of the latency, what I can do is stage a buffer of one. In other words, I can get that box, turn around, put it on the floor, maybe in front of him, right? There's only space for one box on the floor. If the space is empty, I put the box on the floor, and then I turn around. Now, two things are going to happen when I get the next box. If I turn around and the space is empty, I know Jack took it. I know life is good. I'll put the next box on the ground. But if I turn around and the box is still there, now I have to stop. This is important. We don't want to add pain to the problem. If that box is still there, then something bad has happened with Jack. And software development is not about when life is really going good, it's about when going bad. What we got to do, and what orchestration can do quite a bit, is identify back pressure or identify problems in our software, and we can start putting the brakes on things and try to figure out where can we recover to get this flow back, right? To reduce these latencies again. What is going on? Maybe a database crash. Maybe something bad happened to Jack and he's not there. The last thing I'm going to do is put a box on top of a box on top of a box. Buffers really don't help with performance so much. We want to use small buffers that help us identify when there's problems, but reduce enough of the latency when life is good to keep the wheels moving. So a buffer of one is a great way of being able to reduce large amounts of latency on orchestration, but at the same time identify problems incredibly quickly. Now, when it comes to signaling without data, we're really talking about state changes here. And we're going to really use signaling without data as a way to do cancellation and deadlines most of the time. And so we get into the idea now of a channel having a state. Now, a channel that's set to its zero value, this is a reference type, right? We should be using value semantics. But a channel set to its zero value is considered a nil channel. And if you try to perform any sort of channel operation, any signaling, sending or receiving, you're going to block. You might go, Bill, why would I ever want to do that? You might be in a situation where maybe you're processing a network or queue, and the idea is that you want to do some sort of short-term stoppage or some rate limiting. That might be a case where you're in an event loop, you're receiving on signals, and eventually you're like, you know what, for a few iterations, I don't want to do anything. You might put those channels into a nil state, and then on some new iteration, put them back. Now, you got to make a channel to open it. So a channel that's usable is going to be in its open state, and this is where the built-in function make comes in. You can't use literal construction for a channel because you can't pre-populate a channel with data during construction. And once a channel is open, then sends and receives are absolutely allowed, as long if we're dealing with guarantees, the send and the receive comes together, or if we're dealing with buffers, there's either space for the send to complete or there's stuff to receive, but it's allowed. And finally, a channel can be closed using the built-in function close. And it kills me a little bit that we have a function called close because there's so much baggage around that function. But you don't have to. You don't have to close channels. Closing a channel is a state change. It's not a memory cleanup situation. And so we want to close a channel when we want to change the state from open to close. And that's how we're going to do a signaling without data. Think about the idea of closing a channel like turning off the lights. If I have a room of 1,000 people and I turn the lights off, everybody can see that state change. The problem is once a channel is closed, it can't be opened up again. In other words, if I shut the lights off, I can't turn them back on, at least not from that switch. All right, so we got to remember that. And if you try to send on a closed channel, guess what? You're going to panic. That's an integrity issue. But you can always receive on a closed channel because that's how we do the signaling without data. So as we continue to move forward, everything that I talk about is going to be around signaling mechanics. I'll never teach the internals of a channel because the mechanics of a channel can only hurt us. They can't help us. Everything about multi-threaded software development has to be around behavior and understanding the semantics. So a channel can exist in two different ways, right? With signaling semantics, we can signal with data, we can signal without data. Signaling with data is a one-to-one, one goroutine to one goroutine. Signaling without data can be a one-to-one. It can also be a one-to-many. We also want to understand our guarantees. Does the goroutine sending the signal need a guarantee that the signal has been received? If the answer is yes, and we want to get that kind of predictability in our software, then we got to live with unknown latency. If the answer is no, then we could reduce those latencies, but without guarantees, there's always going to be a little bit more risk. And buffers don't provide performance. We're not going to use very large buffers to try to deal with performance. We want small buffers that are helping just reduce latencies, right? Just enough to keep the wheels moving, but big enough to keep the wheels moving, small enough to be able to identify when there's a problem upstream so we don't continue to add to it. And then we're just going to remember about our states, our nil, our open, and our closed. We're going to use all of these signaling semantics that we just talked about to start being able to read some channel code. All right, now that we have our signaling semantics in place, what I want to share with you is the three basic channel patterns that everything else is built on top of. Then we're going to look at more advanced channel patterns. Look, I cannot teach you how to be a expert multi-threaded software development. This takes time and practice. What I can teach you are all the basic mechanics and semantics and continue to stress to you is don't add this complexity until you need it. So I want to go through these basic channel patterns. We'll go through some higher level patterns, and then we'll start looking at more code as we continue through concurrency and tooling that leverages everything here. And I would almost make an argument that if you're doing something that goes against the grain of these patterns I'm going to show you, doesn't necessarily mean it's wrong, but you're probably adding a lot of extra complexity to your software that maybe you don't need. There are exceptions to everything, but maybe you don't need. So this is the very first basic channel pattern around signaling, and it's called wait for task. And wait for task pattern is that base pattern that we're going to use for higher level patterns like pooling, goroutine pooling. We'll leverage a wait for task type of pattern. Now, anytime we look at this type of code, what we want to do is, I like thinking about goroutines as people. It allows me to visualize the orchestrations that are going on. And I always like the idea of a manager and an employee. There's somebody who's in charge and somebody who's doing work for that person's in charge. Because usually if we're doing signaling, it's because we want someone out on our behalf to do something for us, either while we can do other things or so we can potentially stop or correct that person if things are not going right. So this is our wait for task. We're going to see it again when we go to some higher level patterns like pooling, and this is the way it works. The very first line of code you see on line 34 is the built-in function make. Remember, we can use make for slices, we can use make for maps, and we use it for channels, those three particular reference types. And there's no other way to initialize a channel and put it into its open state other than make, because you can't pre-initialize data inside of a channel during construction, so literal construction doesn't exist. Now, when we make a channel, we're going to use the keyword chan, and then the type of data that we're going to be using through this channel. Data is always typed in this language, so a channel is also typed. Now, what you're seeing is an unbuffered channel. I know it's unbuffered because I don't have a number here. There's no number. Now, this would be a buffered channel of 10, but we don't have that. This is a unbuffered channel. But what I'm really going to look at on line 34 is the following. When I see this make call, what I see is we are creating a channel where we want guarantees that the signaling sending is being received. We want guarantees that the send has been received. And right now we're going to also signal with data where the data is string. You see, I'm putting everything within the scope of the semantics that we talked about, moving away from the syntax and moving into the semantics. So this code is saying we want guarantees, and we're going to signal with string data. Perfect. Now, the channel is nothing more than a pointer variable to a very complex data structure underneath. Again, we're going to be using value semantics all the time. Now, wait for task. So here's the idea. I'm going to go recruit some human being, some employee, to go ahead and do some work for me. And that's representative of the literal function and the function call and then the keyword go. Here it is again. I've gone off and I've launched a Go routine to do some work. So we can imagine the following scenario. I want you to always consider yourself to be the manager. This is our path of execution, right? So here it is. Here's the manager. And now we go off and we say, OK, we want an employee to go help us do something. So here we are, and we go launch a second path of execution right here on line 36. This is our Go routine right now that's executing this function. That's us. And now this is the employee Go routine on line 36. Now I want you to look on line 37. On line 37, what you see is a channel receive. It's a unary operation. If the arrow is attached, the operator arrow is attached to the channel variable. Unary operation, and this is a channel receive. And so what we have right now is this receive on our channel. And this is a blocking call because we want guarantees. We're blocked right here. We're basically saying, hey, employee, come here. Let's get involved. Here you are. You now exist. You're moving. But I need you to wait. We're basically saying here is wait for us to tell you what to do. How long is the employee going to wait? It is unknown. Remember, we have unknown latency here because we are going after guarantees. We want to guarantee that this employee here is going to have received our signal. So you wait. You don't know what to do yet. I'm going to send it to you. You wait. Now that means that at this point, this Go routine is blocked, waiting for us. In the meantime, we get to continue to run in parallel. And what we do is we get to line 41. And line 41 is simulating some work that we have to do. This is on line 41. Some work we have to do to prepare the work for our employee. How long are we going to wait on line 41? We don't know. I've even tried to simulate the unknown latency here with the time.sleep function and a random number generator for duration. So we have no idea. They have no idea how long they're going to wait for us because we have no idea how long this work is going to take. Eventually we get past line 41 and now we get to our signaling, our send side of the signaling, which is right here. Notice sending is a binary operation. Receiving is a unary operation. And it's binary because we're going to signal with data, with string data. So our work is now prepared. And now what we're going to do is we're going to take this work, right? We're going to take this work that we have here, and we're going to be sending it. We're going to send it to this other employee. So they're waiting right here on the receive. We're going to do the send. Notice the syntax looks like this. It's the channel, and it's the same arrow operator where we're showing that the data is being placed into the channel. So we're going to do the sending here. Now, remember we wanted guarantees. So this is blocking, waiting for a corresponding receive. This receive is in place. Now what we have here is the send. And with the send in place now, right, we come here, and what we now have is the send and the receive together finally. Now, again, to get the guarantee, the receive happens nanoseconds before the send. But we're both kind of in a blocking situation here. We are. Okay, this Go routine is now in a block state, in a wait state. This has been in a wait state. And the only way to keep moving now is to let this channel operation finish. So what we're going to see here is that the receive is going to happen nanoseconds before, and the receive is going to start first. So this is going to happen first, and it's going to be able to move on. Once the receive is done, then we're going to move on second. So this is going to happen first. That's going to happen second, nanoseconds. And what we're going to get when we get to line 43 is we're going to get a guarantee that the receive has happened. Now, once this goroutine gets the data that we're sending over this channel, they get to do their thing. Right now, we're just displaying information, and they finish, and then we just move on, and we're running in parallel. Now, this stuff gets confusing because the only thing that's atomic, is this operation here. That is the only thing that's atomic. Understand that. I've got two goroutines. Goroutine 1, goroutine 2, each running on their own core in parallel. They both are put into this kind of wait state when we get here, because they've got to have the guarantee. That's what we asked for. After that, these two goroutines are running independent of each other on their own thread from an operating system perspective. What does that mean? It means that these print statements can technically happen in any order. There's no guarantee that the print statement on line 38 is going to happen before the print statement on line 43, because the only thing that's blocked here within nanoseconds of a time is the channel operation. And this is why it makes it very hard to use print statements to determine order, because the only thing guaranteed is the receive is happening before the send. Now, if I try to build this program just running wait for task, which I've set up here, you can see on this run, it's showing you that the send happened before the receive. If we don't realize what I just told you, that the receive happens before the send nanosecond, we would think by the output that the send happened before the receive, but that's not what happened, because this is only happening within nanoseconds of time apart. Both goroutines really kind of start just running again at the same time. Now, if I ran this a few more times, we might get lucky and see the receive output happen before the send. There's no guarantees that this will happen. But the fact that we're seeing, oh, there it is right there. Beautiful. Look right there. Suddenly now the receive looks like it happened before the send. This is why so many people get confused with concurrency, because they're looking at the order of things, and the only order is atomically at that actual send and receive. After that, all bets are off. So you cannot be using print statements to look at ordering. I've left the print statements in here to prove that to you. So when you're working with and learning concurrency, remember your print statements are not going to help you. They're going to really confuse you. Now this is our wait for task. All right, and again, we're going to use this type of pattern for pooling. So our next basic pattern here is wait for result. It is the opposite of wait for task. We're going to use this pattern in things like drop patterns and fan out patterns. So let's walk through this again. Now, we're going to go again, use that idea of a manager and employee. We're the manager, we're going to hire some employee, but we start on line 53, and again we see the unbuffered channel. Again, what I see is signaling with guarantees and signaling with data. So we want guarantees, and we're going to signal with string data. Now this time we go launch. Here we are, we're a manager, there we are. We're starting our path of execution on our own core, and then we go off again and we start the employee path of execution. That's what you see on line 56 with the literal function call and the keyword go. But this time, the employee already knows what they're supposed to do. They don't have to wait for us. We're going to be able to reduce some latency here because the employee already knows the task at hand. So that employee begins to do their work. They're doing the work immediately. The question is, how long does it take to do this work? The reality is that the time it takes to do this is unknown. The time it takes to do this is unknown. Okay, so while that employee is doing their work, we continue to move down, and we get to line 62. And line 62 means that we are now blocked again, right? That is the channel receive. We're blocked. There it is, the unary channel operation. And what we're really doing is waiting for this employee to finish so we can get on. So we are now blocked right here. We're blocked right here on the receive. The question is, how long are we going to be blocked for? Again, that is unknown. It's unknown. We don't know how long that work is going to take. Now, eventually, what happens here? Eventually, what happens is work gets done. The work gets done, and then on line 58, the employee signals with data, the data being maybe a piece of paper, the result back to us. And so remember now, we're in this channel receive here, right? We're blocked. We're in a channel receive. We're waiting for this data. Actually, I should probably, yeah, we can do it this way since I'm on this side. We're in that unary operation, right? We're in that channel receive right here. And now what happens is this is going to be the send. So we've got the send here now coming in. We were already in the receive. The receive was waiting. There it is. We have the send. And now we've got the send and the receive coming together again, right? Again, the send is on line 58. The receive is on line 62. The receive came in place first. We're waiting. The work gets done, line 58. The send comes in. And now we have a guarantee that the send happens because the receive happens first on line 62, which means that we get to move first. So we come in and we get to move first. Right, nanoseconds before the send finishes, we have our data, and then this employee knows, this is the second it gets to move next, and the employee knows that we've received the result. There's guarantee, and there's no way I can throw the employee under the bus because we have guarantees that the send happens before the receive. Again, we're coming in, we're blocked on the receive, some unknown amount of time it takes to get the work done. We don't know how long we're going to be waiting. Then finally the work is done. The send and the receive come together. The receive happens first. The send happens next, nanoseconds, but whatever. We can't use those print statements to look at order. And then we're able to move on. So look, wait for result. We're going to use this again for drop patterns and fan out patterns. This is going to be another very powerful base pattern. And these are two of the really core patterns we just looked at. Wait for task and wait for result. The next core pattern is going to be ideas around signaling without data, where we're going to really use those around cancellation and deadlines. We're going to call that wait for finished. So our next basic and our last basic channel pattern here is wait for finished. And wait for finished is going to show us how we can signal without data. Now I just want to make it clear that what I'm showing you would really be better served with a wait group. A wait group again is a way of kind of doing a signaling without data for that type of orchestration, and it would be cleaner here. But I'm going to show you and walk through this code just so you can see the mechanics. Again, I want to stress that a wait group would make this code cleaner, but I need to show you the mechanics so later on we talk about cancellation and deadlines with the context package. It will give you a little bit more sense. Now look on line 75. We're using the make again, channel empty struct, and it's unbuffered. So we have an unbuffered channel, which means guarantees, except that the data type is in string here. It's the empty struct. And we're going to use the empty struct to denote, from a code readability, signaling without data. Since the empty struct's about no data, we're going to use this. And that basically means that all we're going to really be doing is closing the channel. And there's no real guarantees with this as I'm going to show you. But anytime you see a make chan empty struct, now we're going to be thinking signaling without data. We're going to turn the lights off. Now, let's go back and look at what we're doing. We are the manager. Here we are. And we're running in our path of execution. And right away we go and we launch that employee path of execution, a goroutine. And once we do that again, we're asking this goroutine to do some work. So they already know what they're supposed to do. So now we come back and end up right there on line 83. Notice again on line 83, we're doing a channel receive. This is very similar to what we were just doing before, right? And here we go on the channel receive, which means we're now in a blocking call, right? We're right here blocking because we're in our channel receive operation. Now, I want you to notice something about the channel receive operation. Up until now, all I've done is allowed you to see that we can receive the value that's being sent. But when we talk about cancellation and deadlines or signaling without data, there is no data to receive. And that's why what you're seeing is the second form of the channel received. You can always get data out of it if you are signaling with data, but we can get a second flag, which is a Boolean flag that I use WD for with data. This is my with data flag, and it's part of the signaling mechanics. And what it's telling me is if I receive successfully off this channel and the with data flag is true, then I have data. We signaled with data. But if the with data flag is false, then we received because the channel is closed, because the lights are out. Now, I don't really need to store this variable. I just wanted to display it on the screen if you decided to run this. Ideally, in these scenarios, we're probably doing nothing more than this, which is just, I'm just going to block on the receive, and I don't care what comes out of it. But what we're doing is I'm showing you the with data flag. So here we are, right? Like we talked about here. I'm blocked right now, waiting. How long am I waiting? I don't know. It's unknown because we're signaling, even if it's signaling without data, we're signaling with guarantees here, right? I have no idea how long we're going to be waiting. Eventually the work finishes, and this time what happens is, once the work finishes, we don't signal with data. On line 79, we close the channel. What we now do here is close the channel. We're turning the lights off. Now, when we close the channel, that close is going to happen nanoseconds before the receive. It's kind of like the send happens before the receive. This time the close happens. So the close is going to complete first, and then we're going to be able to move on second. So that channel receive will immediately unblock once the close operation is done. So the close is going to happen before the channel receive. But what we've kind of done is just said the work is done and you don't need anything, so turn the lights off. Oh, we've seen the state change. Now we get to move on. This is still better done with wait groups, and I would ask us to be using wait groups here. When we start talking about cancellation and deadlines, I'm going to show you some examples of that. We're going to be really using this idea of a unbuffered channel where the data is the empty struct, where we're really saying here that what we're going to want to do is signal without data, and we want to be able to do that to many, many goroutines. If I had many, many goroutines at one point all sitting on this same channel receive, if I had all of these goroutines blocked on the same channel receive at the same time, then basically on the close, all of these would then be able to unblock immediately and keep running. Okay, so this is our wait for finish. So we've looked at our wait for task, which is going to be really like pool related, right? The goroutine gets launched. It's now waiting for us to tell it what to do. Then we had the wait for task. Then we're going to have to wait for result. This is like a fan out pattern or drop pattern where we launch these goroutines. They know already what they have to do. We're waiting for them to reply back with whatever the result of their work is. And then we have this wait for finished for cancellation and deadlines, where we're going to use this to be able to tell a goroutine, hey, stop doing what you're doing, or be able to like indicate at a wide scale that maybe we should be shutting down. So let's take a look at that wait for task pattern in a much more practical way around goroutine pooling. Now, I do want you to hesitate when creating pools of goroutines because, as I told you, the Go schedule is very intelligent, and those Ps are kind of like pools of goroutines already. So we don't have to worry about managing our own pools of goroutines, though there may be times where you have a limited a resource that has required limited access to something, and you might need to limit access to something through a pool. All right, so let's go through this code here. Right out of the box on line 95, we're saying we want to have guarantees, and we're signaling with string data. Pooling, and the whole idea is you've got goroutines waiting for work to do. So the work is going to be string-based, and we want guarantees. You absolutely want guarantees with pooling, because later on we want to be able to apply deadlines or timeouts when a pool is, let's say, under load and not responding fast enough. Can't do that with buffered channels. Now, look at what we do here. I've got a loop of 2, and we're currently going to create 2 goroutines in our pool. So what we can imagine is I'm going to create this pool of goroutines right here. There it is. And we're going to end up with two paths of execution in the pool, goroutine 1, goroutine 2. And they're both going to be here in this waiting state. What makes them wait? What makes them wait is the for range. I want you to look at what we're doing. We are ranging over the channel. When you range over a channel, you are basically in a channel receive. So I've got two goroutines blocked on the same CH channel. We're using closures there, by the way. And we are now blocked in a channel receive. Now, order better not matter, because once data comes into the channel, the scheduler can choose any goroutine that it wants to do the work. OK, how does the for range terminate? Well, that's going to be through a signaling change. We're going to go from open to closed. That will terminate the loop. I'll show you that. So look at what I got here. Two goroutines in my pool. They're both blocked on the channel receive right here. And now we go off, right? We go off. We got the pool in place. And now we go off right there on line 108. So here we are, right? We're on line 108 right here. Or here's our main goroutine. This is where we were. This is where we created that pool. So we create the pool of the two goroutines right there on line 98. This is all on line 98 right there. And now we come down and we get to line 108. Now on line 108, what we do is we end up in this work loop. We're going to end up in this work loop where what we're going to do is pass work into the pool, 10 pieces of work. And that's why you see on line 109, we're going to be sending the work into the channel. Remember that channel send looks like this. Channel send that data right here. Now, in order for the send to complete, we needed a corresponding receive. And again, the scheduler now has to choose a goroutine. Which goroutine is the scheduler going to choose? I absolutely have no idea. When all things are equal, it is undeterministic. So let's just say on the first iteration, this send right here, maybe it ends up binding to that receive. Now I've got a send and a receive coming together. This goroutine gets the data. It starts doing work. Then what happens? Then we iterate and we do it again. Maybe on the next channel send, maybe on the next channel send of data, maybe because that one's busy, the scheduler says, OK, I'm going to allow this one to bind to this. Now that work is getting done, right? Now, if another, on the third piece of work, here we go again. We're going to have the third piece of work, right, with the data. But this time, I don't have a single goroutine to perform the receive. We have guarantees. So now this is blocked. How long is this going to block? It's unknown, the guarantees. We have to wait for one of these goroutines, right, to finish their work, come back in and say, I'm ready to do more work. Then the scheduler can come in and go, OK, brilliant. I finally have a goroutine for you. Let's get going. So in this particular case, we're going to try to pass 10 pieces of work into the pool. But with only two goroutines, this goroutine is going to have some latency. There's definitely going to be some signaling, sending latency here, depending on how fast these goroutines complete the work. If we want to reduce that latency, we've got to add more goroutines to the pool. But you can see here that we're doing this. Why we want to use the guarantee is we could later on in code put a timeout here. We might say, hey, you've got 1 second. That's it. 1 second for this send to complete. And if not, we're going to move on. And that's a way of being able to say, hey, you know what? We might be under load and we don't want to wait. When you're running multi-threaded software, you've got to deal with back pressures and latencies. And one way to deal with back pressure and latency is timeouts. Timeouts are everything. And so we may eventually want to put timeouts on these channel sends to make sure that we're not blocking here forever, depending on what happens in the pool. So this is how you're going to do that. On line 113, I'm simulating a program shutting down. If you notice on this channel, we're both signaling with data and without data. While the program is running, we're signaling with data, pushing data into the pool. Eventually, we want to shut the program down. We call close on 113. That causes these receives now that are based on the for range to terminate. And then these goroutines can then eventually terminate, and we could shut our program down. So a very cool pattern for pooling. This is your base pattern mechanics. You may want to add to this one day, adding some sort of program counters around like metrics, around back pressure. You can do that kind of stuff. But this is the base pooling pattern, leveraging the wait for task. So now we're going to look at the base pattern around a fan out. And fan outs allow you to take a piece of work and to distribute across n number of coroutines that can run in parallel. And we're going to use that wait for result as our base pattern to build this the higher level pattern. But I need to stress to you very quickly that fan out patterns are dangerous patterns, especially in web services where you might already be having like 10,000 coroutines already running in the service, and suddenly you have some coroutine fan out another n number of coroutines. And those things can multiply very quickly. So I get afraid of fan out patterns in like long running apps like services, but for background applications that run on cron jobs in certain intervals, and for maybe CLI tooling, it's great. I mean, I had a guy from Cisco one day come up to me, he's all excited, and he says, Bill, man, Go is amazing. You got to see what I did. I made some software run incredibly fast by using a fan out pattern. And I said, what are you talking about? And he said, Bill, I've got this web service, man. And this request comes into the service, so we know that that's going to be an independent path of execution. It's a Go routine. And I had to hit a Mongo database, Bill. And what I did in the process of this request is I had 500 independent database operations that I needed to do. So Bill, I went ahead and created 500 Go routines that went out and hit the database, Bill, all of them independently doing their thing. Man, Bill, you should have seen how fast that work got done. Go is amazing. I started to cringe because I asked him very quickly, how many requests did you run through the server when you launched these 500 Go routines? Because there's a 1 to 500 ratio here. He said, no, Bill, just this 1 or 2. You should have seen how fast it was. I said to him, well, what's going to happen when you do 10,000 Go routines times 500? I go, that is a large number of Go routines. Plus, you're not going to be able to get that many connections to your Mongo database. What you're doing is putting a huge amount of load on the scheduler and huge amounts of unknown latency just to get resource access. And he got very, very sad. And I just said to him, look, it's okay, but you've got to ask yourself the question, did we get these 500 transactions done fast enough on one Go routine? Because if we did, now we can scale. You got to think about scale when it comes to fan out patterns. That's why they scare me. So be very, very careful when you're fanning things out, especially in an environment where there could be hundreds of thousands of Go routines, tens of thousands of Go routines that want to fan out all at the same time. Now, if you notice on line 126 and 127, we are now using a buffered channel of 20. And anytime we're going to use a buffered channel, the number cannot be random. It has to represent something measured or real. And in this case, what we're going to do is launch 20 Go routines in our fan out, which now means that the number 20 is going to represent, or we're going to add a buffer for every Go routine that we're going to fan out. That's a very real, measurable number. There's no like, let me use 10,000. No. Anytime I see a buffer channel and the number doesn't seem reasonable, practical, or tied to something real, we're going to have to stop and pause because we've got to start to consider what are we doing. I want you to remember that buffers don't provide performance. Don't use them as a way of saying, I'm going to get performance because I'm going to reduce latency between sends and receives. Because when you're using buffer channels, one of the other questions we're going to ask is, can the sending Go routine on this channel ever block? In other words, can the buffer ever get full? In a fan out pattern, we've sized it so there no signaling on the send side could ever block because we have a 1-to-1. And anytime a buffer channel can get full, we've got to ask ourselves what happens when the signaling and then the send blocks. And if you can't, you've really put your server in a very, very bad place. I've seen too much software go, I'm going to use a buffer of 10,000 because I don't want any send to ever block. Maybe they're pulling data off of a network. Eventually, the system grows big enough where 10,000 isn't enough. It never really was enough. Maybe they keep growing that buffer. They're really causing themselves pain because they're not really getting orchestration. They're guessing that they have enough capacity for everything. We cannot guess. There are no magic numbers. You can't guess. So we're going to have a buffer for every Go routine that we're going to create. Remember, that's the key. A buffer for every Go routine. That's what's measurable. So here we are. This is us. This is us. This is our Go routine. Here we are, M, our manager. And then we get over to line 129. And on 129, we launch our 20 Go routines. So we're in a loop of 20, and we launch these Go routines. Remember, this is that like wait for a result pattern, right? So we're going to go off here, and we're going to launch 20 Go routines at this point in time. And every Go routine knows what they're doing. On line 131, we're simulating the work that we know these Go routines have to do. They all know what they're doing. Remember, we've set up a buffered channel of 20, which means that when the work is done by any one of these Go routines, when we get to line 132, and that's the signaling with data, every one of these Go routines has their own slot in the buffer. So if this sends first, brilliant. It goes right in here. And there's no latency between the send and the receive. Remember, we are now blocked here. What are we doing? We are in a receive here. We're in a blocked receive. What we're doing is trying to say, when data gets placed into the buffer, this is what's on line 138, we want to pull it out. And there's no latency between the send and the receive because the send happens before the receive. So if this is the next Go routine that finishes, guess what? It gets to go boom. If this is the next one, it gets to go boom. If this one is the next one, it gets to go boom. And at the same time, we are really going in the other direction. We're pulling this away, we're pulling this out, we're pulling this out. And we know that this send and this receive, there's no real latency. However, two of these Go routines could finish at the same time. Maybe this finishes at the same time this finishes. Now there is blocking latency between the two sends because only one send can happen at a time. So in this type of pattern, if we were looking at some blocking profile, we'd probably see more latency on the send side than the receive. And that latency isn't between send and receives. It's between multiple sends. So you can see all of these Go routines went off to do their database work. They send back their result. And now we have our own little local counter, which acts like a local wait group. And we just sit here and we loop 20 times. We perform the receive. If we get a piece of data, we decrement the work count. How long are we going to be waiting here? That is really unknown. This is still unknown latency. We still are kind of getting guarantees here, even though we're using a buffered channel, because we're kind of guaranteed that we're not going to move on until all of the data comes back, right? This is orchestration. Remember, we're not going to return from main until the wait group goes down to 0. We're not going to move on until we get all the data back. So there's no guarantee in knowing which Go routine is going to finish first. There's no guarantee in knowing when all that's going to happen. But here we are. We're going to get all 20 back first. So this is a classic fan-out pattern that we're going to use when it is safe to launch multiple Go routines for a situation like this. Again, I want to avoid this in our web services. But in our CLI programs and background programs that maybe run on cron jobs, Lambda functions written in Go, this can be a very powerful pattern. So there's another version of the fan-out pattern that we call the fan-out semaphore. And what this does is it says, let's fan out n number of Go routines, but we don't necessarily want all of the Go routines to be able to run at the same time. Let's limit how many Go routines in this kind of dynamic pool we've just created can literally run at the same time. This is another way of being able to reduce latency in terms of Go routine creation, but at the same time limit the impact that these Go routines are having on another resource. So this is the fan-out semaphore pattern. So let's go through this. So I've got my buffered channel of 20 again, because we're going to launch 20 more Go routines. We're going to signal with string data, and there's going to be 20 Go routines. So we're going to reduce the latency on the sends between the send and the receives. Now, here's my semaphore channel. and I've set it to 5. And what I'm saying here is I only want 5 out of the 20 goroutines to ever be actually executing at the same time. Again, we're going to save some latency by creating all the goroutines we need up front. There is some cost in goroutine creation. We're going to limit how many goroutines can literally be executing at the same time. The rest will be in a runnable state. So here I go again on line 160. Here I am. And I go ahead and I launch my 20 goroutines. There they are. Same thing as we did before, all 20, except the following. Look on line 162. Now, even though we've launched all of these goroutines, that call on 162 is a channel send. It's a channel send on a buffered channel, but it will cause all of these goroutines to block, right? Like we're going to be in this blocked state. Blocked, 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 blocked. And really why we're blocked here is because we have to perform the channel send. And that send will only complete if there's enough room in the semaphore buffer. Right now, what we've done is we've opened up 5 slots. So imagine what's going to happen right now. Let's throw some more goroutines at our problem here. More goroutines at our problem. In fact, just for the board right now, well, let's just do the following. Let's just pretend that our semaphore count is 2, just because of the room we have on the whiteboard. So we launch all these goroutines. Which goroutine gets to run first? I have no idea. That is, we cannot predict it. So let's say that the scheduler chooses this goroutine first. Now, it wants to perform a channel send, right? So let's look at it this way. We've launched all these goroutines. There they are, right? They're there. They're all in their runnable state. They're all in a runnable state. And now this goroutine turns around and says, OK, you're going to get some execution time. You want to perform a channel send on line 162. Now, the only way the send can complete is if there's room in the buffer. Is there room in the buffer right now? Yes, there is. So beautiful. We perform that channel send. We get the send. It completes. And then this goroutine can move on and do their work, which basically means now that our semaphore count went from 2 to 1, right? The whole idea here is that we sent data into the channel. Brilliant. It gets to move on and do its thing. Now another goroutine gets selected to run. Maybe it's this one. It's going to perform the channel send. And there's room in the buffer, so it's able to put that data. In this case, it's just a Boolean flag. And guess what? This goes to 0. Now another goroutine gets to run. Maybe it's this one. So this one moved on, right? This one moved on. It's doing its thing. Life is good. Now this goroutine wakes up. This goroutine wants to do a channel send, but it can't. There's no room in the buffer. The buffer is full. So guess what? It blocks. It blocks. It blocks. It blocks. It blocks. It blocks. We're all blocking. Now what we're waiting for is the code right here. Right here. We're waiting an unknown amount of time. Remember, we got through that. Now there's work, an unknown amount of time. But eventually when the work is done, okay, we send it back to the caller like we did before. But look at the channel receive. What the channel receive is going to do now is it's going to say, OK, let's pull the data out of that channel, which is now going to open up buffer space and increase that buffer back down to from 1 to 2. Now suddenly, 2 more goroutines can become unblocked, unblocked, unblocked by being able to come in and go, OK, there's my data. There's my data. We get this back down to 0. So you see what's happening here? Before a goroutine can actually do the physical work it has to, it's got to be able to send a piece of data into the semaphore channel. If it does, it gets to move on. And when it's done, it's got to go and pull it back out to give room for another goroutine to come in and then do that work. So there's a cost to creating goroutines, right? But we're able to create them all up front. They're all ready to go. They're all blocked on this particular channel send. And as room opens up in the buffer, the scheduler chooses randomly, from our perspective, any one of these goroutines to be able to complete their send, get their work done, pull it back out, and we keep removing and putting work in there until eventually all of the goroutines finish. We really want to use this pattern when again, you might have a resource that is limited. If we have 20 goroutines hit at the same time, we could have a problem. But having 5 goroutines hit it, guess what? We won't have a problem. But remember, this pattern here is adding extra latency cost to everything we're doing. So you got to weigh out the engineering costs between the latency cost and the system that we're hitting, and understand that back pressure that we're creating over scale. Now let's look at another pattern that can leverage a buffer channel. This is the drop pattern. Drop patterns are very, very powerful patterns. Again, helping us reduce back pressure when things are going bad. They can help us actually identify when things are going bad and reduce back pressure. A good example of a drop pattern could be if you were writing a DNS server. I mean, what are the chances of that DNS server getting attacked? Nah, it's never going to happen, right? Yeah, it's going to get attacked all day long. The whole idea of that DNS server attack is to flood the server with so many requests that it drowns itself trying to process everything. So you can't. What the drop pattern tries to identify is what our capacity is, right? What is the maximum number of pending anything, requests, tasks, that we can take in before we have to say no? Look, it's easy to say yes. You got to learn how to say no in life. And at some point, you have to know what is your maximum capacity and then just say no. In a drop pattern, we say, I'm sorry, I can't handle your request. I'm at capacity, and I'm not going to go down for you. And it's going to take integration tests and load testing usually to figure out what your capacity is. And it might also be based on how much memory you have and your CPU capacity. It could be dynamic depending on the system you're running on. But drop patterns are very, very powerful. They help us identify failures quickly. They help us stop the bleeding. And then they help us move forward again when the bleeding has been, or when that wound has been healed. Let's take a look at a basic drop pattern. So here we are, got a constant of 5, and this time what I'm going to do is make a buffer channel of 5. This buffer channel 5 is our capacity. What we're saying is once we have at least 5 pending tasks waiting in our buffer here, we're at capacity. We're not going to go to 6. At that point, we're just going to drop the work on the floor. We're not going to take it. Taking any more is too much risk. Now, if you look on line 94, here we are again on our main. We've created our buffer channel of 5. That's our buffer channel of 5. That's our capacity. We go ahead and we launch a Goroutine. Now, this could have easily been a pool of Goroutines, right? And we're just keeping the code simple. We understand this could be one or many Goroutines. And there we are again on the 4 range. We are receiving on line 195, receiving from this buffer. In other words, what we're going to be doing on this one Goroutine is we're going to be in our receive, right? We're going to be in our channel receive, where the idea here is, here's our channel receive, that as soon as data comes into the buffer, then we want the corresponding set, right? It's a receive. So once data comes into the buffer, the send happens before the receive, but once we see it, then we're going to want to pull it out. More data comes in, we're going to pull it out. But this Goroutine is only operating on one task at a time. So once we receive it, we process it, we come back, we pull any more data. If there isn't any data, then we block on the channel receive waiting, right? That's the 4 range. Eventually, we close the channel, and the 4 range terminates. So here's the idea. Maybe we're reading some network device, right? Let's do that right there on line 201 for a second. Maybe what we're doing now that we've set this up is we're here, and maybe we're reading, right? We're reading some sort of network, and as we pull data out of the network, we just start moving it, right? We send it into our buffer. But once this hits 5, we know a couple things. Once it hits 5, we can't do this anymore. Now this data has to go from here, and we have to drop it. We can't add it, we drop it. We're not going to block. At the same time, it could mean that this Goroutine isn't running fast enough. It could mean that this Goroutine has a problem right now. It's not coming back into the receive. And so the health of our system is measured by our capacity. If this is working fast enough, then this buffer never gets full. But if something bad happens and the buffer gets full, we no longer block. We don't take blocking latencies. We drop. Now, in order for this to work, we've got to be able to identify when we're full without fully blocking. And I want you to see the use of the select statement here. So I'm in my loop here where I'm going to be simulating 20 network reads of data, and I'm in a select. Now, what's powerful about the select statement is it allows a single goroutine to handle multiple channel operations, whether they're sends and receives, at exactly the same time. So you can create like event loops here. But this is also how we're going to do cancellation and deadlines. And a drop pattern is very much like a cancellation. So look at what we do here. I've got the select, and we've got our first case, which is a channel send. Again, the idea is we've read some data off the network, and on line 203, we're trying to perform this send. We're trying to perform the send. Now, if we can perform the send, if we can perform this send, guess what? The data gets in the buffer. Life is good. We go back to 201 in the top of the loop, and we get the next piece of data, and we try to perform the send again. If the send is not going to block because there's room in the buffer, brilliant. But what if that send is going to block because we are at capacity? Remember, if there's 5 pending tasks in here, then it's going to block. We don't want that latency cost, right? So that's where the default comes in. What the default says is, if the send is going to block, guess what? Don't block. Move on, move on, move on. And we basically now decide what we're going to do with this data we read off the network. We're going to somehow drop it, maybe send back a 500, maybe send back that we couldn't do it. But we're not going to take latency costs. We're not going to create back pressure against this channel. Either we can do it or we can't do it. And when we can do it, brilliant, let's get it done. When we can't do it, it's a really strong indication that we have a problem in our server. So drop patterns are very, very important. They're very clean ways of identifying when we're at capacity, when we're having potential problems. They help reduce back pressure because this isn't necessarily timeout reduction, it's literally capacity reduction. And again, we're using the buffer channel to help us identify when there's failure. And eventually, when this buffer begins to be processed again, then we know that life is good again. So drop patterns are very, very, very powerful patterns. And another kind of core high-level pattern, along with the pooling, along with the fan-outs, that you'll be using to handle different types of orchestration in your software. This is the last basic pattern that I'm going to show you, and then we're going to start looking at some higher level code that uses all of these patterns, but it's cancellation. Cancellation deadlines are critical to software because a task or a request cannot take forever. Now, we're really going to use the context package that's part of the standard library for this. So I'm going to use this code to just show you some basic mechanics of how the context package does things, okay? But ideally, I wouldn't want to see this code in production. I'd want to see the use of the context package, and I'll show you that next. So here's cancellation. Notice that we're using a buffered channel of 1. We're getting some delayed guarantees here. We're still signaling with string data, but we're going to get some delayed guarantee, right? Not a full guarantee, but also we're not going to be completely blind to when things happen. Now, if we do this again, here we are. We are the manager. We've got our path of execution. We've created this buffered channel of 1, right? We've got a buffered channel of 1. And we go off and we, again, use that pattern of wait for result, right? We start this employee goroutine. The goroutine knows exactly what work it is they have to do. The key is that this might be work that one day we want to cancel. We might want to cancel this work. You see, if we do the work, then we can't cancel it. We can't because we're blocked waiting for it to get done. This is where we need another goroutine if we want to be able to cancel. We can monitor how well we're doing and then tell this other goroutine, dude, stop. So this is what happens. We do the work, and if the work finishes, then this goroutine wants to perform the send, right? We're looking to perform the send back to us, and that send can happen automatically because there's a buffer. So that data can go right in here. We don't need a corresponding receive. We've got a buffer channel of 1. So here we are. Let's imagine right now we're on this work piece right there on line 227. We don't know how long this work is going to take. But we've decided the following on line 232. After we created the employee, we set up the TC variable. And the TC variable says that this work has 100 milliseconds of time to get done. If you go back to line 227, I've simulated that this could potentially take anywhere from 1 to 500 milliseconds. Okay, so there's a good chance that this work doesn't get done in time. We're not willing to wait more than 100 milliseconds. If that happens, we've got to move on. I'm sorry. How do we set up that scenario? Well, we go back to the select, because the select allows us to handle multiple channel operations, both sends and receives, at the same time. So look at the first case. The first case is a channel receive, okay, off the buffer. So here we are blocked on a receive, where we want to receive off of this buffer. And as soon as some data gets in there, then we'll unblock. But the next case is a channel receive on our timer. I've got two channels right here, one trying to receive on this and one trying to receive on our timer. That call to time.after, what it returns is a channel. And it's a channel that the runtime will add the current time to after the duration of 100 milliseconds, in this case, is complete. So the runtime, okay, will come in. The runtime will come in on our timer. And this is our timer here. The runtime will come in on our timer and perform the send for us in 100 milliseconds. Or this send right here will add data to the buffer, which will allow this receive to unblock. Which one's going to happen first? I have no idea. That's the point. If this send happens within 100 milliseconds, guess what? We execute this case. If it doesn't happen within 100 milliseconds, then we're going to execute this case. Either way, we have a guarantee that we are going to move on within 100 milliseconds or less. Now, there's a big caveat to this pattern here I want you to see. There is a bug that we would be creating if I used an unbuffered channel. If I used an unbuffered channel, we would have a very big problem in this piece of code. Let's walk through a scenario where if I do not use my buffer channel of 1, life gets very bad very quickly. Okay, so here we are. We've got our Goroutine. Now the channel says that we want guarantees, right? Absolute guarantees that a signal being sent has been received. So we go off, and the employee is created. It goes off and does some work. There it is. Now, we are on there on line 234. We've got two situations again. Remember, we can receive, okay, we've got the channel receive from this employee, so we're waiting on a receive from the employee, or we've got our timeout channel, right, our timeout, where we're going to potentially receive directly from the runtime. We don't know which one's going to happen first, but let's say that the timeout happens. Let's say the timeout happens, right? If the timeout happens and we receive and send here, what happens to this Goroutine? This Goroutine then moves on. It moves on, which means that we're no longer in this receive anymore. We move on. And what happens when we move on? Well, eventually this work is going to get done. And when that work gets done on line 227, this Goroutine is going to want to perform a send. It's going to want to perform a send. But the send cannot complete without a corresponding receive. We're using an unbuffered channel where we want to guarantee that the signal being sent has been received. We are going to block forever. Why? Because there's no Goroutine anymore that's receiving on the channel. This blocks. Whew. This is a Goroutine leak. This is a classic Goroutine leak. Goroutine leaks are going to eventually cause issues around memory, right? You're going to start leaking memory. But Go is really good at cleaning things up. So sometimes these Goroutine leaks don't show themselves for hours, days, or weeks, because Go is very good at dealing with and minimizing memory. But understand that when we deal with these cancellation patterns, where the Goroutine here, us, M, could walk away from the goroutine here that's doing the work, and there's no way to tell that goroutine to stop directly. Sometimes there is through networking calls, but other times there isn't. We've got to make sure that that goroutine doesn't leak by using the buffer channel of 1. So this time, that send doesn't need a corresponding receive. We've got a buffer channel here, which means the send happens before the receive. Okay, so these are things we're going to look at. And if you can visualize goroutines as people and visualize this idea of manager-employee, put yourself always as the manager, think about these goroutines as doing work on your behalf, you can start visualizing this orchestration, right? The interactions between these goroutines, and you can start seeing whether or not you're going to block, whether or not you're going to deal with high levels of latency, where maybe you can reduce that. We can use the select case to deal with drop patterns. We can start doing a whole bunch of stuff once we start thinking about our signaling semantics and visualize the interactions these goroutines are going to have. Welcome to Lesson 11, Concurrency Patterns. This is where we take everything we learned in that channels lesson and start looking at some higher level applications, things that are more practical. We're going to go an exercise of fixing a program that has a concurrency issue and leveraging our channels and our wait groups and other things we've learned at that point to fix the problem and still maintain some level of simplicity in the code. The context package in Go is a very important package because it's really where we're going to implement cancellation and deadlines. Remember, your server can't take forever to do things. A request can't take forever. A task can't wait to take forever. Your database calls, your network calls. If you allow things to take forever, you are eventually going to crash when life is bad. Timeouts, 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 timeouts for everything. And the context package is the solution. But Go made it very simple to create these paths of execution, these goroutines. It didn't really make it as simple to cancel them. So we've got to learn how to use the context package. And I'm going to show you a little bit that any API that you have that does any sort of AI or any sort of I/O or eventually will do I/O should be taking context as its first parameter. Now, one of the other things that the context package has is a generic value bag. Now, I'm very afraid of the generic value bag because you don't want to be using it for like request, local, like what we used to call local thread storage, right? You don't want to be doing things like local request storage. You never want to hide data in a context. But putting data in a context can help for things that functions don't need. We'll talk a little bit more about that. So first I want to show you how to use the value bag, but we're going to be very careful about when we use this. In code reviews, if I see this being used, we're going to be very clear that we're storing things in there that aren't really necessary for the functioning of the app. It's more for secondary stuff like reporting, metrics, things like that. So the way the value bag works is data is stored inside the context with a combination of a key and then the value. But the key isn't just some value. It's also going to be based on type. So the key is a type-based system where then we, based on some value, and then we store the value itself on that key. I didn't explain that very well. I'm going to show it to you here. Let me show you. So here's the idea. I've got a trace ID here. I've defined this type called trace ID based on a string. This is the data that we want to store. Imagine we have a web service and we're generating a trace ID, a unique ID. That is something you probably want to put in the context and pass that around. So we've got a trace ID, it's a string, and then I've got a key. Now the key is based on an integer, but the type we're going to be using for a key is this thing called trace ID key. Now it's based on an int. We're going to be using this new name type. Now I go ahead in this program and I create my trace ID. There it is. There's my trace ID. It's my string. I can imagine here that here is that string value for my trace ID, and we're calling this right here trace ID. There it is. And I've got this value in here, which is really representing a UUID, right? There it is. OK, now I generate this key. But understand that the key that I have here, right, which is a constant, which is the value of 0, isn't really an int. It's really this trace, let's spell this right. It's really not an integer, it's trace ID key. Remember that. This value isn't an integer, it's a trace ID key. OK, brilliant. Now what happens? All right. If we're going to work with context, we need a context. And when you don't have a context, you've got to start with a parent context. Now, there's two ways to get to a parent context. We can use this function called background out of the context package, or you can use what's called to do out of the context package right here. To do, that's also another function. When would you use one over the other? When you know you need a context, but you're not sure where it's going to come from or how it's going to be initially initialized, use to do. It's a marker in your code to say, I've got to come back here and to do this, right? And a lot of times you don't really know what your timeout value should be yet. You don't really know how things are going to work with context, but you know you need it. You want to lay it in early, very early. So to do is something I probably use more than background. But background is your base parent context. You could think of background from our perspective as a value that's just kind of initialized and set up as an empty context. There's nothing in it. So this is our background context right here that we're using. Now, context uses value semantics, OK? We pass a context in, we make changes to it, we get a new context out. We use value semantics. One of the reasons we use value semantics with contexts is because a context can change throughout a function call change. In other words, we're at the root of any particular set of function calls. We might start with that empty background context. Then we're going to pass over these program boundaries. Maybe we make another function call. And in this function, even though it starts with the empty, maybe it adds some timeout information like 10 milliseconds. Maybe we pass this context around to two different Go-routines. Now we went from this one Go-routine to two Go-routines, right? We split this path of execution in parallel. And now things might be changing here. Now this side of the processing only wants to start using maybe 5 millisecond timeouts. So the value semantics are important because as a context is changing, we get a new context. And then the way cancellation eventually starts to work is if we cancel here, then we're going to cancel down both paths. But maybe we just cancel here, and we're only going to cancel down this path. Value semantics are critical here in making sure that things are consistent as we make these function calls and we move down these paths of execution, and even if they split. OK, so this program is starting with the empty context, our parent context. We pass it into a function called with value. With value is how you add state to a context. You give it a key and you give it a value. Remember, the key is based on a type. So remember what we did here. We started with the background or the empty context. And then what did we get back? We got a new context. This is our new context now. We don't care about the old one. And now the new context has everything the empty one has, which is nothing. And now what it has is our trace ID, right? And then here we're using value semantics again. So we've got a copy of that UUID. And it's based on this key, which is our trace ID key of 0. That's it. That's what we've stored in the context now. Now, to pull this data out of the context, we're going to use the value method off of this context, the value method. And the value method actually requires the key, but not the key value. It's going to want the key value based on the right type. So on line 33, I'm passing the key that we used, okay, based on our type. Trace ID is the type. The value is 0. And when I do that, I will get back a copy, okay, UUID. I will get back a copy. Again, we're all using value semantics here. A copy of this. We'll get back our copy. But if you look on line 39, if I just use the value of 0, which in this case is a constant of kind int, so if I use an integer, if I use an integer-based 0, this is an int, not a trace ID-based value of 0, but an integer-based value of 0 for my key, then that OK flag is going to be false. We're using the blank identifier in this case because I don't care. It's going to be false, meaning that we didn't get this back. If I did have a variable where the blank identifier is on line 39, then that would be set to its 0 value. So the only way to pull data out of this context is to not just have the right value, but have the right value in its right type. That's what this code here is showing you. And we've got to be very, very careful when we store data into this context. This is generic. We can't be hiding information in our software ever, ever, ever. So we've got to be very clear about what we're putting in there and then how we're taking it out. But this is how the value bag works with the with-value function call. And as we'll continue to see, everything here is value semantics with context. Now, let me show you another API here. And this one, what I'm going to show you is the wait with timeout. There's actually 4 with functions here that you could use: with cancel, with deadline, with timeout, with value, which we saw for the state. But when it comes to cancellation and deadline, we have cancel, deadline, and timeout. And they all kind of work the same. So I'm just going to focus on timeout, and you'll know already how deadline and cancel work. All right, and we'll explain that as well. So here's the idea. I'm going to have some Goroutine go off and do some work. And we're going to be using that cancellation pattern. So the idea now is that Goroutine only has so much time to get the work done. So let's walk through this code. I set a duration. Here it is. A duration of 150 milliseconds. That's what we're willing to wait. Okay? And then I go with context with timeout. Now we're going to use the context background as our empty base context. I pass the duration of 150 milliseconds, and we get back our new context. So let's think of this context now as saying that we have 150 millisecond timeout to get things done. In other words, in 150 milliseconds, this context would report the time is over. We've got to stop doing what we're doing. Now, it's very important that you look on line 26. Notice that with timeout, and this would be the same for the other 2 functions, with deadline and with cancel, you get back a handler function called, we call it cancel. You have to call cancel. It must be called to clean up resources or you will leak. And so this pattern of calling with timeout, with deadline, with cancel, and then deferring the cancel is critical. The Goroutine that creates the context with one of these with timeout, with deadline functions, with cancel, must also call cancel, and it's okay for cancel to be called twice. Anytime you called cancel, you're immediately timing this thing out. Like immediately we're timing it out. We're not going to wait the full time. So we're deferring the cancel. That's very, very important. Now, notice what we do next. I create a buffer channel of 1 because we want that delayed guarantee. And I go off and I create a Goroutine. So here we are again. Here's our manager Goroutine. Went off, created the employee Goroutine. This employee, again, is using that wait for request pattern. This is a fan out pattern in a sense where that employee knows that there's some work it has to do. This is like a fan out pattern, except we're only fanning out one Goroutine. Again, this Goroutine can't cancel the work on its own. It's going to require us. Okay, now we're saying that this work is going to be able to take 50 milliseconds in this particular piece of code, which is well under the 150 that's here. And then once this is done, it will perform its send on line 38 with the result, which is that data value, right? Result right there. Okay, brilliant. Now, while this Goroutine is off doing its work, it's in this case the 50 milliseconds of work, notice that this Goroutine here is in the select. Remember, the select lets us manage multiple channel operations, sends and receives at the same time. And if you look in the first case, we're now sitting in a receive, right? We're in a receive right here for the data that we're trying to get back from this Goroutine. We're in the channel receive. This is that send on the channel. This is the receive on the channel. Ideally, this is what we want. We want this send right here and this receive to come together. We want the send and the receive to come together. That's our send. The work is done. This is our receive. We want that to happen. But at the same time we're waiting for that, line 46 is very important. Notice that we're also on a receive. We're on a receive also for the done function on the context. So what we're looking at here is this function, this context, has a method called done. And we're also going to report here on done. We're going to say, OK, if the done function returns before the channel receive on line 43, hey, guess what? We've timed out. So basically, the context package is doing this. It's now sitting, we get into the select, we're now sitting in this timer. We're on this call to done. Once we call done, we're now saying we're going to wait 150 milliseconds, OK? And if in 150 milliseconds, you're not out of this done call, then we're going to move on. So at the time we call done, that clock is going to start, and we're saying we're going to wait here for 150 milliseconds, and if it doesn't, then we're going to send on that receive right there. We're going to do the send. We're going to now be able to move on. We are hoping, however, that this work gets done faster. Now, we've already guaranteed that in this code here. So if we come over and run this program, what you're going to see, change directory, go build. What you're going to see is that the work got completed. So what happened? Well, we sat in the select case. Either the work gets completed or we time out. Since this was only 50 milliseconds, we were able to perform this channel send with this receive, work completed. But what if we turn this into 5 seconds? What if it's 5 seconds? Now we run it. Look what it says, work cancel. So we now went to 5 seconds. What happens? This goroutine is there. This now, the done call started 150 millisecond wait. 150 milliseconds passed. We now received on this channel. The done returns a channel. That's why you see the receive is directly on the done call. You can see it returns a receive only channel. And now we report that this is done and we move on. Eventually this work finishes. The send has to happen or we leak a goroutine, and we're back to the idea of that buffer channel of 1. So this is our cancellation pattern, OK? This is how we do deadlines and timeouts. A deadline is when you don't give it a duration, but you give it an actual moment in time that you want things to happen. I tend to use duration-based timeouts much more than I use the deadline-based timeouts. But it's all going to be the same thing, OK? We're going to be waiting for the goroutine to finish its work, or we're going to give it, in this case, 150 milliseconds to finish the work. If 150 milliseconds hits, boom, cancellation, we move on. And if not, then we're going to get the data, and life is super good. OK, so this is our base use of the context package, both for storing values and for dealing with cancellation and timeout. Let me show you a more practical example using the standard libraries, HTTP and net packages on how we can do cancellations here using this stuff that I just showed you in a much more practical way. And this is stuff I do in production code all the time. So here we go again. Here we are in main. OK, you're going to see I'm using the HTTP package, time OS package, context package. Here's the idea. The idea is let's go and make a HTTP GET call against some external service like my web server that hosts the blog. But let's not wait forever for that GET call to come back. Let's give it a limited amount of time to work. And if it happens in the right amount of time, brilliant. If not, we cancel and we move on. So look at what I do here. This is our main goroutine, right? This is us again, our main goroutine. Let's talk about what's going to happen here. So the very first thing I do is I create that request. Here's our request. And the request says, OK, we're going to do a GET call. We're going to go after the blog, the RSS feed for the blog, no post data. We get back our request variable, and we're good to go. There's no error. Then I turn around on line 28, and I say, OK, let's do a context with timeout for 50 milliseconds. So now I create my context. There it is. And it's going to be for 50 milliseconds. This is how much time we're going to have to process the request. Now, the very next thing I do, look again, deferring the cancel. And notice that the parent context comes out of the request. This request has a context already. We want to use it instead of starting with background We want to use it. So that's beautiful. So we passed in this as our parent context, which now means that we got everything the request context had plus the 15 millisecond timeout feature. OK, great. So now what happens? OK, we come into this and we create a transport. So the next thing I've done now is created a transport. Now what the transport is, it's basically a pool of socket connections, okay, to some sort of resource. In this case, it's going to be a resource to the server that's hosting my blog. So there's some blog service here. Here's our beautiful cloud. And now what we can imagine is that we're going to be able to, whatever this transport tries to connect to, will maintain socket connections. This is also where you're going to set up your timeouts. So we're going to set up dial timeouts on how long we're willing to wait for a connection to be established, our keep alive, our idle, our handshakes, our reads and writes. Everything can happen here on the transport. I'm showing you the default values for transport, but we really at some point have to come back and measure it. So think about this. This is our pool of physical, say, socket connections to whatever resources that we want to talk to. And it's better to try to maintain a transport to a unique set of services. So these hot connections, in this case 100, can really give us a level of performance. Then what we have is a client. And what's interesting about the client is that it wraps, that client wraps our transport, and the client gives us an API to be able to go and use the transport to access all these resources. But the big thing here is now, if I allow M, our main thread, to do this work, I'll never be able to cancel it. I just won't be able to cancel it. So look at what we do right away. I create our buffered channel of 1. There's our buffered channel of 1 right there. Here's our channel, right? It's a buffered channel of 1. Again, because we're going to have a go routine, potentially walking away from, we're going to walk away from work. We really want to make sure that we don't leak go routines. And we go launch our second path of execution. So here we are. Here's our employee now, our employee. I'm going to use blue for this for now. And we have our second path of execution. And look at what that employee does. We're using closures to get to the client. So the employee has access to this client. And you can see that there's a method called do off of this. So brilliant. What is the very first thing our employee does? Uses the client, and it calls do, which basically means now on the call to do, okay, it's going to do a bunch of things. It's now going to have the transport go out and establish a socket connection that requires a DNS lookup, requires the socket connection. It's going to do all that. And once the socket connection is established and we're ready to stream data, client do will return. Now, if there's an error on client do, we're going to report back by signaling with data that this work has finished. Basically, what's happening is once we launch that employee, okay, we are now here. We're now here blocked, waiting. We're blocking here now, waiting for all that work to complete, right? We're going to be blocked on a channel receive here. You'll see that in a second. So we're going to be blocking here on a receive. Remember, this is that wait for result. OK, so we did the do. Boom, 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 we've got a connection. If there's failure, we report back on the send to the receive. Life is good. If not, we do what we have to do. We always have to defer the response body or we're going to leak memory as well. So we defer the close. So when we're done, that gets cleaned up. So we defer the close. And then we're using IO copy. What we're doing with IO copy next is streaming the data from our web server, okay, the response body, all the way to standard out, so we can see the results. So I'm just writing the XML for the RSS feed document to standard out on the copy. And once all that's done, the GoRoutine reports back by signaling, again with this nil data, because there's no errors. Our channel is based on an error. It will signal nil, and the send then and the receive should come together. So we'll have our send right here. And as we've seen, you have a send, right? You have the receive. They come together. And everything can actually, that was a big mistake, right? Forget about it. We have a buffered channel of 1. What does that mean? This doesn't have to come together. We've got to maintain our signaling semantics, Bill. Remember, this is blocked on a receive. All this is doing now is monitoring this as soon as there's something in it. The send doesn't have to wait for the receive. We're in a buffer channel. So guess what? The send can happen, then the receive can happen. The send happens before the send. So this is that order. That Goroutine's doing do, and then it's streaming, and then we're getting output, and we're now here. Now, look at what we do on line 69. We're back on our main Goroutine here. We're blocked on the receive. In fact, we're actually blocked on two different cases. We're either waiting for this Goroutine to tell us it's done, or there was an error. That's case 77. Anytime there's an error or we're done, this Goroutine signals by sending data into this buffer here. That will signal us. Or remember, the context has the done method. And what we do immediately here is use the select and start the clock. So here, we start the clock right there for our 50 milliseconds. And guess what? If we time out, if that case happens before this case, then this is the beautiful thing about the transport. Since we have access to the transport here, and the transport has a cancel method, guess what? If we call cancel, that's going to cause failures to happen here. We're basically going to be able to shut down that Goroutine immediately. And I'm waiting to validate that the Goroutine did shut down. You may or may not want to do line 75. We don't necessarily need it, but there it is right there. Ideally, this is what we want. We want the output to happen. But if it doesn't happen, then we can cancel the request, shut this Goroutine down early. In other words, you don't have to waste any more CPU cycles to get that done, and we move on. So let's run this program. Now, right now, the timeout is at 50 milliseconds. I mean, that's not even going to be enough time to do the DNS lookup. But let's watch what happens here. I build it and I run it. Notice that immediately we see timeout, cancel work, and the error we got back was request canceled while waiting for connection. What does that mean? This is what it means. We went ahead and we launched this Goroutine, and we're sitting in this client do call. Now, the client do call has to do a couple things. It's got to do a DNS lookup to find the IP address for that named resource, and then it's got to establish a socket connection. Guess what? We canceled while we were trying to establish the socket connection, which meant that all of this shut down, which meant that basically the client do failed, and we reported back the error. That Goroutine shuts down, and we canceled work. Now, let's do the following. Let's not give us just 50 milliseconds. Let's give ourselves 5 seconds. This should be more than enough to get this work done. Go build. Run it. Look at what just happened now. The output's completely different. We have the RSS feed for the goinggo.net blog. What happened this time? Well, this time we had 5 seconds of time to get this thing done. So the client do call happened in time. We got to the close. We actually copied everything to standard out. And then we executed this case, because all of that happened well within a 5-second window, and our program worked. So we had more than enough time to get the work done. It was great. The first time we ran this, we were at a 50 millisecond timeout. It just wasn't enough. And we could see the cancellation working. What's more beautiful is, here's a scenario where not only do we get to walk away, not only does M get to walk away, we're also able to terminate E early, which is brilliant, because when we can terminate our E Goroutine, our employee Goroutine early, then we're not wasting time on CPU cycles that we know we don't need. This is a great example of when we're dealing with networking related stuff in Go, how we can use these cancellations while networking access is happening and resources, but at the same time our M Goroutine, our manager, can tell the employee, stop what you're doing, don't waste any more CPU cycles, we're done. Let's take everything we've done right now and summarize it in a cool little kind of live coding demo. So you can see how these concurrency patterns, orchestration, buffer channels, how we can leverage this to do some really nice things that we couldn't do in other languages as simple as we can now do in Go when we are maintaining our signaling patterns, right, appropriately, really our signaling semantics appropriately for the problem. So here's the problem. Let's say that we had an application that's writing logs. And this application is using the standard libraries logger, which I use all the time. I honestly use the standard library logger all the time because I don't need logging levels. I really focus on signaling or signal versus noise in my logs. And again, I don't use structured logging. I really don't when I don't have to. So here it is. Here's this app. Let's say it's handling hundreds of thousands of video requests. Let's say that we're streaming video. So we get a socket connection in, we stream video to that device, and we log about that device. So let's simulate maybe a program that's doing this where we're using the standard library logger and we're letting every Goroutine, all 10,000, write to standard out directly. Okay, brilliant. Now, one of the things that I want to show you with this here, let's do it right here. Here's our main. Let's start here. And instead of having 10 or 100,000, we're just going to use 10 Goroutines for a second. And what we're doing here, I got to tell you about this device. So let's back up just a little bit. Because there's a real problem with this program. Remember what we said. We have an application that is streaming data for any particular device. Let's say the World Cup, since the World Cup's happening right now. Right? We've got hundreds of thousands of people on their phone in the park, watching in their office, watching the World Cup. And we got a socket connection in our server, and we're streaming and we're logging as that happens. Now, here's the situation. Since we're letting every Goroutine write to standard out to do their own logs, what happens if standard out suddenly causes blocking? What if every Goroutine, when they attempt to write a log, blocks on standard out? You know what's going to happen? Every Goroutine is going to be stopped in a waiting state. Basically, there is no more video streaming. Literally, 100,000 of our customers on this server no longer can watch the game. And God forbid we're in a shootout situation. They're really going to be upset. I would be upset. So let's simulate this potential problem. Let's simulate a situation where the logging blocks and it causes our entire service to deadlock all at one time. All right, so here it is. In order to simulate this, we've got to mock a device that we can cause blocking on. So I've defined a type called device, and it has a field called problem. And this is a Boolean field, and we're going to flip the bit. When there's no problem, streaming is happening. When there is a problem, we stop all the streaming. The whole server comes to a halt. Remember something. You got to decide for your server and your application, is it okay to stop things when we can't log? When it comes to streaming video, I know the logs are important, but you can't just stop TV because you can't write logs anymore. The TV streaming is much more important than the logging. That being said, we want the logging to start running again as soon as possible. We've got to detect the problem, we've got to identify it, we've got to fix it, we've got to keep moving. I've known some applications where there's so much data in the logs, you literally do have to stop. But when it comes to this video streaming, no way. We cannot halt this program because we can't write logs. So let's simulate the problem again. So there it is. There's the problem. Now, what we're doing on this device is we're implementing the I/O writer interface. Right? This way we can allow this to be really a true device and leverage the I/O package and other aspects of the standard library that allow for writing. And there we are. We implemented the I/O writer interface, and we looked this. And if there's a problem, then we're in an endless loop sleeping at a second at a time. So this is going to simulate that disk problem, right? It's going to simulate some sort of blockage on trying to write to standard out. And if there is no problem, we break out of the loop and we were able to write the data, the log data, to the device. Okay, so we've simulated a mocking device here. So now what do? Here we go. We're going to use 10 Goroutines to run this simulation. We create a value of our device set to its 0 value, and the standard library logger asks as the first parameter any sort of concrete data that implements the I/O writer interface. Our device implements the I/O writer interface, so we're good to go. Then we launch our 10 Goroutines, and each Goroutine here is writing logs to the mock device and waits 10 milliseconds to write to the next log. So we're seeing heavy logging activity across our 10 Goroutines that's streaming the World Cup to those 10 customers. And again, Customers are going to be upset if we're not able to stream. Now, in order to actually run the simulation, I bind this code into the operating system, and I ask to get signaled anytime I hit basically Control-C. So we're in an endless loop here. Every time I hit Control-C, we will receive on the sig channel. Notice we create a signal channel. We pass it to the notify function. Notify function binds it into the operating system. And now every time we hit Control-C, we'll receive. And every time we hit Control-C, I flip the bit on the problem. Now, most of you are going to recognize that I now have a data race here. This is a write, and this is a read. And this read and write is not synchronized. There's no atomic instruction here. There's no mutex. You're absolutely right. This is bad production level code. But I don't want to convolute the code right now with atomics. So let's just appreciate that there's a data race here. That's not really what we're looking at. And we'll be able to flip this bit, and we'll be fine. So here we are. Every time I hit Control-C, we go from no problem to problem, hit Control-C, problem to no problem. We'll flip it back and forth with our data race there, and we'll keep seeing what happens. Okay, great. So I've got my main application to run the simulation. So let's go now into our console. Let's build this program, and let's run it. Okay. So here we are. 10 devices are being streamed the World Cup. Now, I'm going to count to 3 and hit Control-C, set a problem, and see what happens to all of these poor people. 1, 2, 3. Look what just happened. We now simulated a problem with standard out, and the logging has now caused the entire server to deadlock. Nobody's watching the World Cup anymore. Now, let's say we ran out of disk space for the logs, right? We clear up the disk space, 1, 2, 3, and boom, it starts again. But guess what? We run out of disk space again, and you can see that the logging has stopped. This is unacceptable. Unacceptable. We can't stop streaming because we can't write logs. Not in this case. So using this standard library logger and allowing Goroutines to log to the device directly is not a solution we can use anymore. We now have to add some extra complexity to deal with this problem. Basically, we've got to write some code now that lets Goroutines, even up to 10,000, write to the log, but to be able to detect if that log write is going to block. And if it is, don't let the Goroutine block, just bypass or skip the logs. How can we do this? Well, if we use a drop pattern, then I think we could come up with a very simple solution that solves the problem. Let's draw the drop pattern out on the board. So what if we did this? What if we create a Goroutine whose entire job it is to write to the device, whatever that device is, right? That means that if this particular write to the device blocks, if something bad happens like we've simulated, well, we only have to trace or track that on one Goroutine, not 10,000 Goroutines, only on one. That made our life a lot simpler. So if we have just one Goroutine writing to the device, even though there may be a little latency on its logs, it's okay, we can at least detect when there's a problem. But how do we get 10,000 Goroutines, right? 10,000 Goroutines that's streaming data. How do we get these 10,000 Goroutines to feed the one Goroutine the log data that it needs? Well, we could use a channel, right? We could say these Goroutines can signal with data, log data, that there's work for this Goroutine. Now, if we use an unbuffered channel, if we try to get guarantees here, we're going to be in a lot of trouble because then these Goroutines are going to block waiting for the Goroutine here to perform the receive. We can't. Latency is everything here. So we're going to need a buffered channel. The question is, what should the size of the buffer be? We're definitely going to need a buffer channel. The question is, what is the size? Well, we've got to figure that out when we do some running and simulations or load testing. But we could say, let's create a buffer for every Goroutine that we know is going to be existing in the program, maybe 10,000 in this case. It has to be measurable, and we have to also make sure that it's a reasonable number. Now, why does this work for us? Why does the buffer pattern work for us? Again, we use a drop pattern. If we use a drop pattern, life is amazing here. Think about it. While there's room in the buffer, these goroutines can perform their send, and there's no latency latency between the send and the receive. There will be some latency between multiple sends, but that should be quick. And that means that if there's room in the buffer, that means that we are good, right? The system is healthy. Even if we're maintaining a little bit here, this is going to show health and all the logs are going to get done. But what happens if this blocks? If this blocks, then this buffer is going to get full. In fact, it's going to get full very, very quickly. And what the drop pattern is going to say is, attempt to signal with data on this buffer channel. And if you can, great. If not, we are not going to wait. We are not going to block. What we're going to do then is drop. Drop. We're basically going to drop that log line and not log it, but we're not going to stop the video streaming. Think about this. This buffer channel is going to give us the ability to detect when we're not able to write to the device. But once the device is writing again, this buffer will clear pretty quickly, and we'll be able to recover. This is brilliant. So let's use a drop pattern to solve this problem, okay, and get this code back into production quickly without this fear that our customers are going to lose their ability to watch the game. So let's write this package. I've added a folder called logger, and I've got a logger.go, and we've got the package logger in here. Now, what we need is a logger type. So let's go ahead and create a logger type using the struct. And let's go ahead, because my linter is going to complain, we're going to have some comments here. The linter is going to complain because comments on exported things really become part of the Go documentation. I'll show you some of that later on in the class, but I don't want all the squiggly lines right now, so we're just going to add some comments like this. Now there's two core data structures here that we need. We need this goroutine, and we need this buffer. We need the goroutine that can perform writes to the device, and we need a buffer that the rest of the goroutines are going to signal into. So let's start with the channel, and let's just start with a channel of type string right now. Since log data is string data, we can come up with a simple solution here. And since we're going to have a goroutine, I'm also going to need a wait group. And the wait group is going to be important because it's going to let us manage the concurrency, the life cycle of this goroutine. We've got to give the caller the ability to not just start this goroutine, but to terminate it as well. Remember, you can't create a goroutine unless you know how and when it's going to terminate. So that's pretty good. I think that's all we need right now. And anytime we're finished with the type, we're going to need a factory function. So our factory function, as we know, is going to return a logger. We should be using pointer semantics when you can't make copies of loggers anymore because we can't make a copy of the wait group. That would create a different wait group. Plus, there's only one logger. We only want one logger. We're only making copies of logger. So pointer semantics are good. And the very first thing they're going to want to do here is create a logger. But I need some things first. The first thing I need to know is what device we want to write to. So we'll accept the device, the concrete data, through the IO writer interface. And then we need to know what the capacity of our buffer is going to be. And only the caller can tell us because only the caller knows its application. So now we can go ahead and create a logger. There it is. And the wait group's already usable in its zero value state, so we're good there. But we do need to make the channel. So let's go ahead and make that string channel and use the capacity as the buffer. Now we get the squiggly lines because we haven't used the variable yet. So we could return the address of L. Notice again that I'm using value semantics on construction because we're assigning it to a variable. We want to return the address out like that because it's more readable. We now know that we have a potential allocation because of line 20. We're really creating readability around escape analysis here. Great. I've got the logger. That's good. But now we got to go create the goroutine. So we know that we need a goroutine whose entire job it is to perform these writes. OK, great. So how can we do these writes here on the goroutine? Well, we're going to have to receive off the channel. So what if we did the following? What if we received that logging data using our for range, and we'll leverage our closures to keep this code clean. Look at what we've done here now. What we're saying is this goroutine is going to receive off the buffer channel, and then what it has to do is write that to the device that we've asked it to, that we passed in. What's great is the func package has an f print function here, and the fprint function takes as its first parameter, let's see here, let's just write fump, because off the top of my head, I'm missing information about this function, fump dot fprint. Yep, I was right, fprint, that's all we need. And all we can do then is pass it W for the writer or the device, and V is the value. So look at what we've done here. We've said, OK, we're going to write whatever data we receive off the channel to the device that we've passed, and we'll do it through the fumped fprint function. This is pretty cool. I mean, this Go routine now is able to write to device, formatted writes to the device. But we're not done yet. We do not have our full orchestration in place. So let's do the following. L.waitGroup add 1. And when this Go routine is finally terminated, then L.waitGroup done. So look at what we've done here. We've set up that there's going to be one Go routine that this package creates. And once we are able to terminate this Go routine, we'll decrement the wait group to 0. Anytime you create a Go routine, you have to provide a mechanism for being able to terminate it, especially if it's part of an API for the caller. Let them have the ability to manage concurrency all the way down. Which now brings us up to our next method, because this function's done. We've created a logger. We've initialized the buffer channel. We've got our wait group 1. We create the Go routine that knows how to write. We're back here, able to write to the device. Then we defer the done. We range over the channel, getting data, and we write it. OK, brilliant. And then we're using our pointer semantics there to return it back out. OK, great. Now, let's use a method, because we're going to have to be able to try to close this logger. So we'll do this. Maybe we'll just call it close. Again, I don't want my comments. So let's just do this. And what close is going to do is give our API the ability to shut down this Go routine in an order fashion. So in order to shut down the Go routine, what we're going to have to do is close the channel. That will terminate the for loop, which will then call done. So then all we have to do is wait group wait. Look at what we've done. Nothing more than that. Close the channel, causes the for loop to terminate. Then we wait to report on the done, and we're good. Now, the person using this API has to make sure they do not call the close the logger till every Go routine that can potentially log is finished. But guess what? I want a clean shutdown of my software, and we should be able to make that happen. Now, I need one more API to get this finally finished, and that's this call here to print. This is really what was causing us pain before, right? The print call was blocking, which was causing us our pain. We can't let the print call block. So we're going to have to implement this as a method, again, off of our logger. We'll use our pointer semantics. We'll call it print. We'll keep it simple, and we'll just ask for a string right now. We can always make this more complex later. Not important. But at least the print call here can mock the print call here. Now, what does print have to do? It's got to signal with data the data that we want to log, but it's got to be able to identify if this buffer is full to drop the log and not wait. Guess what? We get to use a select statement. And what we can first say is case, okay, case, L.channel, signal with data V. If this signaling with data succeeds, it means it got into the buffer, means this Go routine over here. If on line 41, the signal we're now sending with data succeeds, it got into the buffer, this Go routine will process it. Or we go to the default case. And the default case says if line 41 is going to block, there's no room in the buffer, then we want to drop. In this case, what I'm going to do is write the word drop to the screen so we can see that we're no longer blocking like we did before. We've moved into the default case. We're dropping these logs. We're basically still running and streaming data. Look, after 49 lines of code, I am done with an API that should solve our problem. And the only level of complexity is a buffered channel and one Go routine. So let's bring this logger that we just wrote into the app and see how it works. So we've got to first import it in. So what I'm going to do is I took the path of this, and I'm going to get it to our relative Go path. And another thing I'm going to do, just to keep this really clean, is I'm going to rename the logger namespace to log. And that means that I can just make a small few changes to our application. Okay, brilliant. So there it is. Now, since the logger has the same API, really the only thing we have to do is replace the construction of the logger by using our new function, our new function, right? And we have the device, and that device is the address of D, and then we want the capacity, which will start off with the number of Goroutines. Now, we might find that we need more or less capacity. What we don't want is false positives, where we're really not in trouble, but we filled up the buffer a little too fast, and now we think that we're in trouble. So we've got to find that number. We can only do that during load testing, but starting with at least the number of Goroutines should give us a good starting point. Look what I've done. We're now using our new logger API. I've changed the factory function now to use the same device, the number of Goroutines, and since we've already implemented this same API, we're done. All I had to do is import our logger, reuse the log namespace, use the new factory function, and we're in. Now I'm kind of scared here. Let's see if we actually did this right. So let's run the program now. We're going to switch over to that console window and run it. But I want to double check the code real quick to make sure that everything is going to be perfect when I run this program. And when I come back and I look at the logger, I realize that we're not adding extra line feeds to the output, which is going to make the output look a little silly. So I'm going to change our package real quick to use those line feeds. We're going to come back in here again. We've got the new logger in place. And now I'm going to build this program, and we're going to start running it. Now, we can see, like we saw before, we are logging data. We're logging, we're streaming video. Everybody's watching the World Cup. I'm now going to simulate that disk problem. 1, 2, 3, bop. Look what happened. We got the drop. We're now in the select, right? We're now in here. We are still streaming video, right? Unlike before when we were completely blocked. Now, let's fix the problem. Maybe we ran out of disk space. 1, 2, 3. Guess what? We've identified that the problem has been fixed, and now we're logging again. This is it. This is engineering. This is the beautiful pieces of that idea that channels give us orchestration, signaling semantics that can really help us identify problems quickly and deal with problems and then recover without any extra levels of complexity. Again, 45 lines of code gave us the ability now to detect a problem, recover from that problem, and keep our customers happy because they're still able to stream, or we're still able to stream video to their devices. Welcome to Lesson 12, Testing. This is where we're going to start learning how the testing tool works and the testing framework already built into the language. It's beautiful that Go is given this out of the box. Unit testing, even some integration testing is so important. So I'm going to teach you how to write unit tests and subtests and data-driven tests, and even teach you how to mock HTTP-related stuff in the language, and also documentation and examples. So a great lesson to get your feet wet to be able to start writing your unit tests in Go. All right, we're about to start learning how to write unit tests in Go. I love that unit tests are integrated into the Go programming language and into the tooling. And it's really a minimal solution, which is all you need, right? Minimize, reduce, and simplify. Now, there are third-party packages out there. GoConf is probably my favorite, but I really want to avoid using third-party stuff just because it adds extra dependencies and things to your code. So normally, I'm not really a fan of bringing a third-party package in to provide some maybe stronger testing support, but you don't really need it. I'm going to show you how it all works right now. But Kevin Henney said this, and I really love it. A unit test is a test of behavior whose success or failure is wholly determined by the correctness of the test and the correctness of the unit under test. So one thing we really got to validate and make sure is that our tests are adding value, and also that we're not over unit testing or under unit testing. This stuff's complicated, but we're going to go over really the mechanics today. And I'm going to show you how I write unit tests, which isn't necessarily how you need to write unit tests, but I just want a team to be consistent, because there's nothing more frustrating when everybody's kind of doing things differently, and because you just have a minimal solution here, it's quite possible for that to happen. All right, so we're going to go through a basic unit test here. I'm going to be using VS Code to show all this stuff off, and we're going to start here. Now, there is a front end called Go, and we've been using Go build throughout the class. Today we're going to start using Go test quite a bit. We're also going to be using Go tool pprof, Go tool trace. We're going to start using more of the Go tooling outside of just the compiler. And if you want to write tests, then your files have to be in an underscore test file. Remember, Go is about convention over configuration, and we use this underscore test convention here to denote files that are going to be really isolated just to the testing tool, which means that these files aren't going to be built and compiled into your production level binaries. All right? But Go test will run the compiler. We'll see some of that today. So I've got my underscore test. Now, once you create an underscore test file, ideally that's going to be in the same package as your source code for your production level product, whether it's that API or their binary, whatever you're building. And you're going to have to either put the test inside the same package name, or a lot of times what we do, and I tend to do this more than not, is use the same underscore test convention for the package name. So why would you do one over the other? If you want to be able to write tests that hit the unexported API, you're going to do this. You're going to have just the same package name that the rest of the source code is in. If you want to write unit tests that are more tailored to how your users are going to be using your API, which is what I really believe in, then you're going to want to do this. Go allows these files to kind of exist in their own package, even though they're inside the same folder. And then you have to import your package like anybody else does and work with the API. Now, what happens to me a lot of times is I'm writing a new package, let's say, right? And I'm starting with the unexported API quite a bit. So I might start writing unit tests with this because I want to start testing the unexported API. But eventually when I get to the exported API that's using the unexported API, I can start ripping out the unexported tests and just keep the exported tests, and then eventually end up here. I don't get hung up writing tests that I might throw away later on, because I want to make sure as I'm coding that my code is working all the way through. I don't consider that a waste of time. I actually consider it a way of being more productive. So during the course of my development, I probably have a lot more unexported tests that eventually get thrown out, because the exported tests then give me the same code coverage that I need. You got to find your workflow. That's my workflow right there. And I always want to make sure that those unexported APIs are very, very testable. We want to make sure the exported APIs are very, very usable. Okay, so it's a really interesting balance. These are my philosophies. So let's just start with this very basic unit testing Go. I've got the underscore test file. I got package example, which is the name of the folder. And I'm going to show you again what I do for unit testing. You don't have to do all of this. I'm a little crazy. I like the verbosity of tests, because when they run in the CI, I'd like to have a lot of information. I'm really about not hiding information, right? So I've defined these two constants, which are these Unicode characters for X and check. You'll see how I use those. And the big thing here is having a function named test. So you can see here that this function starts with the word test and it's exported. It is critical that this function is exported, or the testing tool will not find it. It's also critical that whatever you name the test, which is what comes after the word test, okay, starts with a capital letter. If you do this, the testing tool will not find this test function. You will go crazy. Now, some people like using an underscore here. I'm not a big fan of that, because we don't really write functions like that in Go. There is some conventions around examples that I will show you where that might become important. But overall, I don't do that. It doesn't mean it's wrong. If you want to do that, that's fine. That the test tool will still find these test functions, but you're not going to see me doing it. Okay, The other big thing is not only does it have to start with test with a capital T and the next letter has to be capital or underscore, is got to accept a testing T pointer. That's your integration into the testing tool, the T pointer. Now the T pointer has the API that we're going to need to use. And if I just quickly just talk about the API, you can see we've got functions called error and fail and fatal and log and some other things here. And we're going to focus on what this API is doing. But basically, the log function is a way of adding verbosity into your test. Doesn't mean whether tests succeed or fail. It's just extra tracing information. You're going to see me using error. An error is going to mean that we're going to log some information, but the test is now marked as failed, but we keep executing any code left inside that test function. And then you're going to see me using fatal, and what fatal is going to say is, hey, this test has failed, and guess what? We're done. There's no reason to run anything else because we're in such a bad state that anything else is now irrelevant. So you're going to see me use these three functions, error, log, and fatal, and then we'll use some of the other API as we get there. Now, the whole idea of a unit test is to validate that something is working, right? Normally, we're going to validate that some API you've written, whether it's exported or unexported, is behaving. That if I give it this input, it produces this sort of output. And we're trying to unit test the expected behavior of things, right? The semantics of what we expect this API to do. That is what we're trying to unit test all the time. So look at what I'm going to do here. I want to unit test the HTTP GET call. I want to validate that the semantics of the GET call are working. And so what I do is I set up some basic input here. We're going to use this URL, which is the URL to the RSS feed for my blog. And we're going to expect to always get back a 200, right, HTTP code 200 every time I call it. Now, I like the idea of given, when, should when I'm writing unit tests. And given is why we're writing this test to begin with. When is what data we're using for the test. And should is what should happen. And I like to break this given, when, should into three different blocks of code. So you see me use an artificial code block here, right? You see me using the curly brackets. It defines another level of scope. But for me, it's a readability marker that this is the given section. And you could have multiple given sections in a test function if that's how you want to organize it. But given the need to test downloading content, when, so within the next block, when we use this URL expecting this status code back, our inputs and sometimes our expected outputs. You can also see I've labeled the test as test 0. I'm using some tabbing. You'll see the output in a second. And then we start doing the test code. And you want to make sure this code is really as close to how you would write production code. But also more importantly, if a function fails, like there's an error, you got to check your errors here. I don't want to see blank identifiers being used in your test code. You're going to get in trouble when you do that. So you've got to check those errors and make it part of the should. Now, I like consistency in output. So whether it succeeds or fails, I want to really try to see the same exact message. Yes, there's a little duplication here. I told you I'm crazy, okay? There is a little duplication here. Not a lot of people will do this. I like doing it. I like consistency in that final output. It helps with readability when things are going wrong. This is why I like it. So we should be able to make the call without an error, right? We should be able to make the call whether it failed or succeeded. We'll find out. You'll see that that's being placed right there in the beginning of the output. I'll show you that. And if there's an error, we're also going to show what that error was. Now we're using fatal here because if that fails, there's no reason to do anything else. But if it doesn't fail, then we'll defer the close body just like we would do in any normal piece of code calling get. And then we can do our checks. In this case, I'm checking that the status code we got back is the 200 that we expect. And now you're seeing my pattern for when there's an error. This is my pattern for fatal, where, again, we're always going to use that if statement for that negative case. So fatal, we're done, or we can just log. But since with errors we're going to keep going, we have to use the if else in this case. So now I'm testing the positive case here. If it does succeed, then we should get the success. Else, on the failure side, we should see failure. OK, so I've got a test here. So what I'm going to do is I've already moved into this local directory here. I've already moved into this local directory here. You see the test example 1 underscore test. So let's just run the test tool in a couple little different ways so you can get a see how we're using this basic test. So I can just say go test, nothing less, nothing more. And since everything is passing, all it does say is pass. And it shows you that it took almost 900 milliseconds to run the test. But what if I want to see the output of this test, even though it's succeeding? I could use -v. And -v is give me that verbosity. And now you can see why I've kind of structured the output of my test the way I did. Look at that. It says, given the need, test 0 when we use this data. You see the plus, the check marks. I mean, for me, this is really nice, right? And if you were to bring in some third-party packages for this, they'd give you output that's kind of similar. And I'm showing you here how we could do it ourselves with really minimal work. It just takes a little bit of consistency by the whole team. So we've got that right there as well. Now, another thing I can do, let's just cause this test to just fail. This is an artificial failure here, right? Line 32, I'm going to say not equals. And what I'm going to do, or let's not even do that. Let's change. Let's say we were expecting to get a 400 back, okay? We're expecting to get a 400 back. Now what's going to happen? Well, let me clear it. If I just run go test now, notice that when the test fails, it switches into verbosity mode automatically. Didn't have to do the -v. That's really nice because then when things are passing, our output will be very clean. There's no noise there. And then when something fails, we get all of that work we did for the verbosity. And this is exactly what I want you to see. You know, you see how here visually it says X. Hey, this one failed. We were expecting a 400. We got back a 200. So I'm trying to really make sure that the test output gives us a very clear indication of what's going on. It even tells us the line code, line 35, on where that failed. So this is really, really nice stuff. This is our basic testing here. Now Go also has on here, you're going to see me use a -run flag. And what's nice about the -run flag is it uses a regular expression to be able to filter the test functions that you just want to run. So I can just say run anything that starts with down, and you can see that it found test download, which is pretty cool. So how you name your functions too will be able to filter out what functions you want in an entire test suite by using that run function. So this is our basic unit test. I've shown you some of the command line options that we have already. And it's going to be up to you about how consistent and how much verbosity you want. But I love just this basic API. So table tests are a very powerful way of writing unit tests when you have a base code and you want to throw a lot of different input and expected output around it. So you don't have to write a whole bunch of test functions. We can leverage one test function with a table of inputs and outputs and run that test all the way through. So let me show you a basic table test. Again, we've got our underscore test file. We've got our test download function, our testing T pointer. And this time, if you notice, I have a variable here called tests. And it's based on this literal struct or a slice of these literal structs. We do this a lot, right? I don't need a name type here. So I defined my input. I defined my output. We're going to use our URL. I expect a status code. And now I could load this table with different scenarios, right? So here is the call to the RSS feed. We expect a status OK or 200. Here is a call to a CNN RSS feed that I've misspelled, and therefore we expect a status of 404, status not found. And as new test cases arise, as we find bugs, instead of writing a new test function, we just throw more data at the table. And then it's really the same thing. It's given the need to test different content at different statuses, right? And this time, before we get into the when clause, we're going to range over our table, picking out every piece of input and output. And as you can see, we're going to range over tests, index I, TT, and the when clause now is displaying where we are in our data table, including our test number. And then everything else is the same. We got the get call, the close, and we check the status. So now if I want to check a 500, if I want to check a 403, I want to check a 203, whatever all the codes are, right? I could just keep adding data and not just adding test functions. So let's run this because this is going to run through two pieces of data here. I've already navigated into this folder, and so now what I can do is say go test. I'll use the -v because we know it's going to succeed, and I want you to see the output. And again, what's nice about the output that I have here is you can see the run for the first piece of data and what we're using here on test 0. You can see the run for the next piece of data and what we're doing. You see all the check boxes right there, and it's great, right? We got all the verbosity. So these table tests, even though this took a little bit longer now, right? It took almost a full second to run these two tests. These tests are running in series here. They're running in series. But at the end of the day, I didn't have to write an extra test function. I just use this table, and there's no formality on what your table can look like. We tend to use it as a collection, right? Because it's a collection of data. We tend to do this where we are just defining our literal type, whatever that struct is for inputs and outputs. We make a slice of that, and that's what we're arranging over historically. But these are table tests in Go, and you'll hear a lot of Go developers love writing table tests. Now, the last two tests we created, that basic unit test and the table test, they were fantastic, right? We're testing the get call. But here's the problem with those two tests. They require a connection to the outside world. We were hitting a live server. We normally aren't that lucky in our CI environments where we have access to the outside world. Now, I always want to be very careful about mocking. I don't want to mock databases. I want to use Docker for that. Certain systems where it's critical that we know that we're talking to live systems or binary protocols, everything is working. I'd rather use Docker for that. Again, the database don't mock databases. But a lot of things can be mocked, and these tests that we did run could be mocked, right? Like, I don't particularly care. I know that web servers work, so I don't care about the HTTP protocols here. What I care about is that if I send this request and I get back the response, that I can process it. And so what I want to show you is how you can mock a get call already built into Go's standard library in the language. And what's nice is Go gives us this package called HTTP test. We're going to use this to mock these get calls, and we'll use them again later to be able to mock some of our internal stuff. So look at what we do here in this code. Since we're going to be making a get call to the GoingToGo.net web server for that RSS feed, which is nothing more than an XML document, what I've done here is I've created a raw string right there. It's called feed. It's raw. You see the use of those tick marks here. And what those tick marks are doing is respecting even the carriage return line feeds and the tabs or anything I put into that space. So this is a RSS document that represents at least a portion of what we expect to get back when I hit the GoingToGo.net web server. Great. Now, I've created some structs here and with the XML tags so we can pull this data. When we mock the call and get this raw string back, we can unmarshal it into our real data structures here and do some actual testing. But the whole key to the mock is this function right here called mock server. I want you to notice that mock server is using the pointer semantics for the server type inside HTTP test. The server type allows us during unit testing to stand up a web service on some random port that we'll be able to get back and write code that we know executes on the call. Bottom line is this. When we call new server right here on the return, then new server is going to stand up a web service on a port that it will tell us. And when we hit the endpoint that it gives us, any endpoint that it gives us, it's going to execute this function that I'm defining right here on line 63. I like when I define literal functions to assign them to a variable and then pass them into what I'm doing. I just find that the code is more readable. A lot of people like to kind of define that function in the calls. I'm looking for readability. So look at this. A basic handler function in Go uses this signature, the response writer, which is an interface, and the request, which is a concrete type. There's a concrete type. This is an interface type. And what's going to happen is when we hit our mock server, we're going to write 200 into the response. We're going to set our application XML just like the Go web server would do. And then we're going to use this fprintLine function to take our raw string and to send it or stream it through the response writer. Brilliant. So no matter what we hit on this mock server, this function gets called. It means we can mock any HTTP GET call that we want, and from our code perspective, or it did go out. I mean, it didn't really leave the machine, but it did actually go out and do what it had to do. Okay, so watch what we do now with our mock server. We're going to check that our status is okay. We call the mock server function. We get back our server pointer. Now we have stood up a actual web service, and anytime we hit it, it's going to execute this function here. We have to defer the close because we've always got to be clean. So given the need to test downloading content like we have, when we check this URL, look at the field .url off of our server pointer. So whatever this endpoint is, that's what we're going to hit. We're not going to hit the actual goandgo.net server. We're going to hit our mock server. This is going to be localhost on some random port. And if you extend that localhost some random port with any sort of URL you want, that's okay. It's still going to hit this function. And you can look at the request and put some maybe conditional logic in here for the different, actual endpoints beyond the port that you might want to test. Great, and we expect the status code. So now we call get like we always have using this localhost URL, and then the rest of the code goes ahead and checks the status on marshals into our document, and we just validate some things like we've got the right number of items. So remember that this test before took about 800 milliseconds on the network that I'm on. Let's see how fast it is to run this test now that we're mocking it and not leaving my machine. So I'm already in the folder that we need to be in there. There's the example 3_test. And I'm going to run go test with the -v. What I want you to see is how fast this test ran. This is 14 milliseconds, not 800 milliseconds. 14 milliseconds. We didn't leave my machine. And you can see this is the endpoint that we hit that was given to us by our mock server. This 49897 is that port. So we hit that. When we hit that URL, that local host and port, we ended up executing this code right in here, and we mocked out the call, and we got back what we expected, which was a valid document on the 200. And look at this, a test that would have ran for 900 milliseconds that we've had to worry about having access to from a server, we now mocked. And I feel very confident that this get call works because our mock is pretty much as real as you can get hitting a server. And now what's even better from my perspective is it's not just about the happy case. I can start doing some really nasty things around what happens if this fails and that fails, and things I wouldn't be able to really cause my external server to do. I can mock a bunch of failure here and validate that we're handling everything that could possibly happen. So a lot of us are building web APIs, right, using the HTTP, HTTPS protocols. And the last thing you want to be able to do, the last thing you want to have to do if you want to test that stuff is stand up your own server. And you don't have to. The HTTP test package gives us the ability basically to test all of our endpoints from the router, from the MUX on, and bypass all the network piece. So I want to show you how all that works. And to be able to do that, we had to kind of build a web API. So here in example 4, I'm going to use a very basic piece of code to build a web API. This is not production level code, okay? We'll look at some of that hopefully around some profiling, but this is not production level web service code. It's just so I can show you how to mock those endpoints. So I want you to look here in main. I've got a handlers package that we're adding in here that has all of the routes. We're going to be using the default server MUX to do this, and we're going to listen on port 4000 localhost. Now, if I open up our handlers package here, what we're going to see is the handlers.go file, and now you see the routes function that we talked about. We're binding a route called sendJSON into the sendJSON route. There it is. And here is the sendJSON function. Notice the signature again, response writer, request, just like we saw with our mock. That's how we write handlers in Go. And what we've now done is bound this function to this route on our port 4000. and listen and serve will just run. Now all we do here is define a literal type. We do our literal construction, giving it my name and my email address, and then we send that over the wire as JSON. So this new encoder encode is using the response writer and then sending it down the wire. So if I go into our example 4 folder right there, I do a build and I run it. I'm now listening on localhost 4000. I can come here, say localhost 4000 /send JSON, and we'll make this big. I just hit my little endpoint. I mean, just a few lines of code, and I've got a web service going. Again, this isn't production level. It's not handling anything like load shedding and it's just where we need to be right now to show you how to use this unit tests. Okay, so there it is. I've got my endpoint. Now I want to test this endpoint. I want to validate that it works without having to build and deploy this code. I want to be able to test it right here at my desk. I want to be able to test it from the route on. So how do I do that? All right, let's go back and come into our code. So since these routes exist in our handlers package, I've written a _test file right here under the handlers package. There it is. You can see it at the top of my VS Code window, handlers _test. And you can see that I have a test send JSON function here. Now notice the init function. This is really important. You gotta make sure that you initialize your MUX, right, with all of the routes before you do this, because you're gonna go through the MUX. I can't tell you how many times I've written tests and didn't bind the routes. So you're gonna always want to encapsulate the binding of your routes, so not only your app can bind them, but your tests can bind them as well. All right, great. So we've got the test send JSON function, testing T. The URL we're going to hit is send JSON, okay? And we expect a 200. So how do we do this? Great. So given the need to test this endpoint, right, and we're going to be mocking this out, really, we go back and use the HTTP test package. Now there's two special functions here. New request is the first one. That returns a concrete pointer to that request type. There it is. And we're going to set up our get call. We're going to set up our send JSON route. There's no post data, it's a get call. Then HTTP test also gives us a function called new recorder. Now new recorder also returns a pointer to a concrete value called response recorder. And response recorder already implements the response writer interface. Yeah, so life is good. We've got our two concrete types that we need to run this test. And then we go to our MUX. If you're using a third-party MUX, they all implement serve HTTP because it's based on an interface. So I'm using the default server MUX from the HTTP package. If you were using a third-party MUX, you'd have the serve HTTP call. After data comes over the wire, this is what's going to get called. So we're going to take our concrete recorder, our concrete request pointers, we're going to pass them into serve HTTP, and boom, the entire route and the API is executed. And once that returns, everything that we need to check is in our recorder. So testing for this, we do that. Now we use our recorder, our concrete type pointer. We could test, did we get back at 200? We can decode that data into our literal struct value here, and we can test that it says bill and then it says addressing. So the HTTP test package is brilliant. We were able to use it before to test a get call, right, to mock an external server. We're now using it to be able to mock our routes, right, to test through all of our routes and to test all of our endpoints. I'm going to run this code. And then we can also do a lot of error handling here. We could check certain inputs, right, that could cause problems all through all of this code that you see here. So let's do the following. Let's move to the handlers package here. Again, this is where we are. And now I could do is go test, right? I'm going to filter, just so we can show you this again. Filter, just run the test send JSON function here, and give me some verbosity. Now, look how fast that ran, 13 milliseconds. Look, 13 milliseconds that ran in. Again, everything checked out. We were able to actually execute this endpoint. We got Bill back. We got Bill with the email back, right? That was our output right there. You see it? Same thing. But we didn't have to worry about standing anything up. We literally just bound our routes, used the MUX, gave it our concrete recorder type thanks to the HTTP test package, and we ran through all of the code. This is a great integration type of test we would see at the command level or our application level. So Go is really taking care of us here in terms of our ability to test these networking activities, mocking these things and validating, at least from the routes in this case, that life is good. So there's another kind of test in Go that a lot of people don't know about, and they're called example tests. In fact, examples serve two purposes. They help with providing examples in the Go documentation that your code is producing and for a test. So what I'm going to show you here is I've added another file, another underscore test file to this project called handlers example test. And in here, I've written a function called example. Now, what's really interesting here on this example is that there is no parameter being passed into it. We just start with the word example, and then again, what we're going to have here is something that we want to test. And because this is an example, what's going to happen is we've got to bind our example to an actual exported function in this package. So notice that I have a function here called sendJSON. This is now example sendJSON. You know, if I give this some other name, notice I've got some squiggly lines here. The Go linters identified that this example doesn't refer to some known exported thing inside the package. You see that? GoLint is really trying to make sure that we do this. And this is because if it doesn't bind to something that's exported, it's not going to show up in the Go docs. I'm going to show you the Go docs in a second. Now, if you're talking about a method, something like a method off of a type, then there's a naming convention where you're going to be using a type name and an underscore for the method. So if this was a method off of some type, we'd be using the type name, and then we'd be using underscore to denote the method. GoLint will help you find your way there. OK, so notice it says example sendJSON. What I'd like to do before we run this code and look at it is look at something that's a little bit more maybe real world. And I've moved over to the Kit project that I have under Arden Labs, and specifically looking at the log package. Now notice that in log, I did do log examples underscore test. This is my naming convention for examples when I want to split them. All you really need to do is have it in a test underscore test file. And you can see that this example is showing the user how to use the log API. Now, what I want to do is a couple things here. Let's go ahead and run GoDoc. Now, to run GoDoc, I just type GoDoc, and I tell it what port I want it to listen on for HTTP. By the way, this is great, because what GoDoc does is able to read your Go path and all of the source code on your machine and give you documentation. So look at what I've done here. I've said godoc-http:3000. And if I come into my browser now and do localhost 3000, this might look familiar to you. In fact, if I go to golang.org right here, which is where we get documentation when we're online, it looks pretty similar, doesn't it? Yeah, because golang.org is really built around GoDoc, just with some modifications. OK, and what's nice is I can click on packages. So a lot of times I'm too cheap to buy internet on the airplanes, and I'm on airplanes all the time, right? So when I need documentation, guess what I do? GoDoc on the command line, and I don't need to worry about golang.org not being available to me. Now, what's also cool here is I've got a list of all of the packages, not just in the standard library, but also inside my Go path. Look at that, in my Go path. Now, the thing that stinks is they didn't give us a search feature. So if I want to find that log package under Kit, I'm going to have to start searching So there's Arden Labs right there. And I got a lot of stuff under Arden Labs, right? That's all the Go training stuff here. This is the only thing that stinks about our Go doc here, is trying to find what you want, because I got to use the browser search feature. But here's Kit, and here is Log. Now, you might find this interesting that there's some really nice looking documentation here. Look at that, package log. Where did all this documentation come from? Where did all this overview come from? Look, the code you are writing is also documentation. And anything that's exported is coming out in the index. And any comments you put above anything that's exported is going to be comments in the documentation. Look at this. And look what you see here. Example. And what do you see? All the code I wrote inside the example function. So here's some rules that I'm going to put in, and what Golang does as well. Every comment you write is code. Not only is every comment code, it's documentation. And so comments must be proper sentences, grammar, punctuation, everything. And in a code review, I am looking for that, because every comment you write, especially those above, anything that's exported, show up here. Remember, your code is also documentation. Write clear, concise sentences, grammar, punctuation, the whole 9 yards. And you can see how the example code that I wrote inside this function showed up in the Go documentation. And if we look at part of the API, you see this is why I write clear, concise, complete grammar type sentences. Now, I have a lot of overview in this documentation. When you're going to have a lot of overview, the best thing to do is to add a doc.go file. And what you're going to do is put all of that overview documentation there above the package log. Any comments you put above package log becomes overview. And when you're going to have a lot of it, like 40 lines of it, don't put it into your normal source code files. Just do a doc.go. It all has to be above package log. And how you space things and indent things will show up as code blocks or sometimes even section headers. Okay, brilliant. So look at that. That is some really cool. So these examples also become part of your documentation. And Golang will also try to help you make sure that your comments are there and they're going to be useful from a documentation standpoint. But I started this with the idea that an example is also a test. And I want to show you that. Notice how this example has at the bottom this output directive using a comment. What this means is that any comment you now put below, and you can have multiple lines of comment here, is now what we expect to see from standard out. So anything this example writes to standard out, we can now validate. Think about this. You have example code in your documentation. If somebody comes to you and says, I don't know how to use it, you can say, dude, I've added examples to the Go doc. Just read it. But you've also validated that your examples work with every build of your source code. So if anybody copies and pastes that, you don't have to worry about them coming back and saying, hey, it's not working. No, 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 no. I know it's working because that example produced this standard out, this output out of standard out, and I tested it. So look at this. We're saying that examples send JSON should always produce this JSON document. Now, let's go ahead and test that, right? Let's go and test that. So let's come in here. Let's kill our Go doc for a second. We're still in handlers. I've got my example test. And what I want to do is say go test, but this time I'm going to tell it to just run this example send JSON. And when I do that, it's just going to say pass, okay, because the output's the same. So let me do the following. Let's pretend that this was the expected output. Just Bill Arden Labs dot. We know it isn't. Let's say that's what it was expected. Now watch what happens when I run just example. It says, hey, Bill, you know, you got this. This is what you got, but you wanted this. Hey, this test fails. How brilliant is that? So I've got examples that show up in Go documentation with the idea that I can also validate that these examples work by testing what this example code outputs. So we can just fix this output now. There it is. Run it again. Brilliant. My examples are now passing. So examples are really powerful. Now, you can't have an example as a test. Examples don't have to be tests, by the way. When we were looking at my log, there was no output directive here. I was purely using it for documentation. But if you decide you want it to be a test, just remember that the output has to be consistent. So if you've got output that changes based on what time it is and where you are and things like that, you can't do this. We're not going to change code to make sure that this test can do that. That's bad, right? Code is for the users. We've got to really focus on usability first. I don't want to add things to an API just to make it testable, but we can create APIs that are testable by focusing on the inputs and the outputs. But here we are. Here's an example that will show up both in the Go documentation and we can run it as a test. Now, something that the language team added in Go 1.7 was the concept of subtests. And Marcel, who works for Google in the Switzerland office, did all of this work, and he did an amazing job with this. So I want to show you subtests in Go. And they really, really help when we start looking at table tests, because one of the things that we have with table tests is the ability to do like this data-driven testing, right? But if we want to just filter out one piece of data over the other, historically we had to comment out the data, which meant we had to go into and do some code changes. So what our subtests are going to let us do is filter a piece of data at the command line level, and I'm going to also show you how we can run that table test in parallel as well. So let's start with our test download function here. Our standard test download function using our standard table tests that we learned before. But I added a new field to the table. It's called name. This is going to give us the ability to name each piece of data and then filter things on the command line. So I've called this the status OK test. This is the status not found subtest, right? Two subtests, same as before, but we've just added a name to it. So now we're going to say, given the need to test download content, we're going to range over our table. But here's another change that I made here. Here's another change. Notice that I've defined a literal function, assigning it to the variable tf. Subtests run with the idea that every piece of data is bound to its own literal function. That's how we can execute these the way filter and execute in parallel. So I've got my own literal testing function. See, it takes a testing t-pointer, and I run the rest of the test, or define the rest of the test, in the literal function. So when we use this data input, that expected data output, we do the get, we do the close, we check the status. We now have this literal test function tf. We range over that, right? But here's the key, is we now call t.run. We give t.run the name for this subtest and the function to execute. Then we iterate again and we do the next piece of data. Iterate again and we do the next piece of data. So how cool is this, right? I can now give each piece of data in my table test a name, also define it within its own path of execution, really, right? Its own function, and then tell run to execute each individual literal function one at a time. So let's run this download test now. I'm already in our folder here, so go test, run, just test download, -v, give me some verbosity. You can see that it found the subtest status OK, status not found, and you can also see that it executed status OK, status not found. It executed it in series, one after the other. It took a full second to run this test, but guess what? How cool is that? Now let's say I just wanted to run status OK. I can just come back over to run, say no, just run status OK. This is the cool part, right? Just run test download / status OK. Now I didn't have to go into my code and comment out any particular line in my table. The testing tool now knows just run that piece of data from the table test. Come on, this is really brilliant stuff. Marcel's a brilliant engineer over at Google. We're so lucky to have him on the engineering team. He works on some really powerful stuff for us, and this is something he spent a lot of time designing and building for us, and it's really great, brilliant stuff. Now, I want to show you how now we can run all of this data in parallel when it's reasonable and practical to do so. What I've done is I've added another test function here called test parallelize. And really it's structured almost identical. Here's our table. here is our name, here's our data bound to these names. Given the need to do this, we range over our table, and we still have our function. We pass it to run. But look, this time the very first thing I do inside this literal function is called t.parallel. What this tells the testing tool is run this as a separate or independent path of execution. Literally run this on its own Go routine. Don't run it on the Go routine you're using right now. Run it on an independent Go routine. So now watch what happens when we run test.parallelize. Remember, the first time we ran this test, it took a full second to run. Let's run test.parallelize and show me V. Boom. Look how fast it ran. It wasn't a second anymore. It's 113 milliseconds. Why? Because it ran these tests or this data in parallel against all the different cores that I have. Come on, this is really cool stuff. Very cool stuff. So subtests are fantastic when we've got these data-driven tests, because it's going to allow us to not just be able to isolate on the command line one given piece of data over the other, but run all of this stuff in parallel, which means our unit tests can run faster in our CI servers. I want to show you how the built-in code coverage tooling works in Go. This is really brilliant stuff. In one of the earlier sections, I told you, how do you know when you're done with a piece of code? And one of the things we said was code coverage. And I believe that you need to be somewhere between 70 and 80% of code coverage overall before you tell me that you're done. I do want to see 100% on the happy path, but I want that 70 to 80%. But how can I check that? Let me show you how it works. Now I'm back into my Kit project here, and I'm using my TCP package here to show you how we can do code coverage. Notice I've got two files here for _test that's allowing me to test this API, and the API is over 3 files here. It's client.go, tcp.go, and tcp-config. So we could do some basic code coverage by just moving into that folder. There I am already. I'm in our TCP folder. And I could do some very basic code coverage by just saying go test and just adding the word -cover. So using the cover flag off the tool. Now, if you notice, this is saying I'm only using 58.3% right of code coverage, which is bad because I already told you that if you're not at 70%, you can't tell me that you're done. So maybe you shouldn't listen to me anymore because I've got this code out there that doesn't have the proper code coverage. This stuff happens because sometimes you're moving fast to add feature functionality, and you say you're going to go back and add the test code coverage later. This is why we need those checks and balances. OK, that's great, 58%. But we don't really know where that 58% is. What we need is a cover profile. If we generate a cover profile, we'll know where that information is. So instead of just saying cover, I'm going to say, give me a cover profile, and let's write that cover profile, let's say, to c.out. What I've now done is I've generated a c.out file with the profiling information for the cover report. But how do I look at this coverage? Well, Go tool cover. There's lots of Go tools. We're going to see pprof and tracing soon, but this is Go tool cover. Now, I want to get an HTML representation in the browser. So I'm going to say use HTML, and here is the cover profile c.out. That's all I got to do, HTML c.out. Look at what happens. Yep, a browser window opens up, and I'm starting to see the code against the coverage. And I've got a drop down here that shows me at the file level what we're looking at. Now, what I'm looking at is client.go, which is giving me right now 93% code coverage, right? I can look at TCP-go, that's giving me 52%, and 53% on config. Let's look on TCP-go. This is horrible. This should be at least 70%. Let's see why we're not at 70%. And I can do is scroll down, and immediately I see this. This is the implementation of the error interface for this client error type. I have no tests that validate this code. Not good. Now, I've got some really nice code coverage for new. Everything is green. And remember, I want to test that I have 100% code coverage on the happy path. This is how I can do that, by looking at the green. These are edge cases I'll probably never run. That's OK. look at all of this code here. These are kind of edge cases that I might never be able to run because they're dealing with socket failures. Here we go. And this is completely unacceptable. If I'm a manager and you came to me with this and you said you were done, I'm going to send you back to your desk, right? You've got an entire API here called done, and you haven't written a single test for it. Not good. But guess what? There it is. And this almost becomes a game now because we can add tests and just watch the stuff go green, go green, go green, go green, and keep running it. So it's really nice that Go gives us the ability to look at code coverage using the -cover command, or we can come back and use this cover profile flag and then use the Go tool cover with the HTML to view all of our code coverage here. And I really want you to make sure you're at that 70 to 80% code coverage. Use this tooling to validate what is really missing and what you could add that you should be adding before you go and tell everybody that you're done. Welcome to Lesson 13, Benchmarking. Here I'm going to start teaching you the basics of benchmarking and how important it is to validate any benchmark that you perform. And we're going to focus on CPU and memory benchmarking, which is really the bulk of where you should be when we're looking to improve the performance of our software. This is where we're going, or we're trying to make decisions on what is better. But remember, we're always going to optimize for correctness first. And once we get a running program, we can use these benchmarking tools to get a sense that we're running fast enough. And if we're not, then I'm going to show you how we can leverage the output of this tooling to make our code run better. So benchmarking in Go is incredibly powerful. I'm going to show you some aspects of basic benchmarking now, and then when we get into profiling, I'm going to show you some more. But let's just start with a basic benchmark here. Let's look at the mechanics and look at how we can write these and run a couple of them right there on the command line. So what I'm starting out with is on line 17. In fact, look at line 17 and line 28. The idea of this benchmark is to do a CPU profile of how fast the sprint or sprintf function run. And one thing about benchmarking is that we've got to really make sure that we're not guessing. We've got to make sure that the benchmark we're writing is accurate. And one of the things I worry about is since this code is going to be compiled and the compiler is capable of throwing dead code away, with the SSA backend, it is capable of identifying like this scenario, right? You call a function like sprint, right? And sprint doesn't really mutate state. It's using value semantics. It gets its own copy of the string, returns a new string. So if you don't capture the new string coming out of sprint or sprintf, technically the compiler can identify that. Let's not waste any CPU cycles making this function call. And suddenly you're trying to do a benchmark like this to figure out what's faster, sprint or sprintf. And it's blazing fast for both because you didn't capture the output. So what we're doing in this test is also making sure that the code is not getting thrown away, but also that we're using code the same way as accurately as we can, like we do in production. Now here's the test. I want to know what's faster, sprint or sprintf for the string hello. My guess is that sprint is going to be faster because we're not doing any formatting. And remember, anytime you guess about something, you've got a good chance you're going to be wrong. But this one's going to be obvious, right? I'm just showing you a basic test, sprint versus sprintf. Now look at the structure of the test. We've got a function named benchmark. This time it takes a testing B pointer, not a testing T, a testing B pointer. It's the word benchmark. We have the same rules. That has to be exported, sprint. Okay, sprintf, that also becomes the name for that particular test benchmark function. And the big thing here is the loop. Now, the way the loop works is the first time the testing framework calls this benchmark function, b.n is going to be 1. And then it's going to increase b.n over time. The idea is we want enough iterations of the loop to feel confident of the results. Now, by default, the test will run for about 1 second, which means it runs for a few seconds. We're going to up it to about 3 seconds just to make sure we get enough iterations. You got to figure out what enough iterations are, 1 million, 100 million. That's up to you. So you can increase the bench time to get more iterations to feel more confident, but again, it's going to take longer to run. So look at this benchmark function, sprint. We've got our loop b.n. We are calling sprint. I'm assigning the string coming back out to s, which is a local variable. We know that if we don't use the local variable, Go's compiler is going to complain. I don't want to add extra CPU cycles here. So we assign it to a global variable just so the compiler won't throw it away. That's all we're doing here with GS, is to validate that we don't throw anything away. That's not going to give us any extra cost on this benchmark, because the real cost that we're looking at here is inside the loop. Okay, so we got sprint and we got sprintf. So I want you to make a guess on which one's going to be faster. I'm guessing sprint because we're not doing any formatting. Again, this isn't an underscore test file. So if I move back over to our terminal, there it is, basic underscore test. And we're going to use go test like we did before. But since there are no functions that start with test, I don't really want to waste the tool's time looking for them. And if there were functions that started with test, the last thing I want is them to run. By default, go test will always look for and run test functions. So if we only want to run the benchmarks, then we got to give it a regular expression where it won't find anything. That's why I like using none. None isn't special. It's just a string that I know there are no test functions around. So we'll filter out all those test functions even though there are none. It doesn't matter. I still like just saying none as practice. Then we're going to use the bench flag, and I'm going to use dot for everything. Remember, it's regular expression. So run none tests, but all the benchmarks. Let's increase the bench time to 3 seconds. So that uses basic time formatting that we would get out of like the time package, 3s. You know, you can do your hours, you can do your minutes. There it is, 3 seconds. So we're going to go from 1 second to 3 seconds. And I'm just looking at CPU right now. But you know what? Let me show you else what we can do. I can also tell it to look at memory allocations just by saying bench mem. So if I do bench mem, I'm also going to tell it report allocations. Remember, an allocation is anytime a value escapes the stack and goes into the heap. So I think we're good here. Go test run none, bench dot, bench time 3 seconds, bench the memory. Okay, brilliant. So I'm running this now, and it knows that we're on Darwin. We know we're on an AMD 64 architecture. Sprint. Now, the first number here as it runs is showing us how many times we executed that code inside the loop. That was 50 million times over that 3 seconds. If you really notice, the whole test took almost 9 seconds. Okay, at least 3 seconds for each. It looks like, you know, almost 4 seconds for each. So we ran this 50,000 times. We identified that sprint ran at 68 nanoseconds per operation with 5 bytes allocated over one object. So there's one object on the heap worth 5 bytes of memory. Notice, however, that we were able to run sprintf 100 million times because it ran faster at 53 nanoseconds per op with the same memory allocation. In other words, our guess was wrong. Sprintf is actually faster than sprint by almost what? In this particular run, we're looking at about 15 nanoseconds per op. I mean, we're talking small, but this is why I'm always going to tell you we cannot guess. Do not guess about performance. Do not guess. When you are writing code, we optimize for correctness, readability, simplicity, integrity, because that's all you can really know about at the time you're writing the code. If you write code for performance, especially if it's new code, you are guessing, you're going to be wrong. Get something working. We can use these benchmarks to validate. So now we know that we probably would have used sprint in our code when, from a performance standpoint, sprintf would have been better. I mean, 15 nanoseconds per op. But that's my point, is we don't want to guess about performance. So we've just seen how we can create a basic benchmark and run that on the command line. So the cool thing here also in benchmarks is we're also able to create sub-benchmarks. If you remember in the testing section, which I hope you saw, that we had the concept of sub-tests. We were able to take data-driven tests, give them names, run them individually, run them in parallel. We've got the same concept here in Go with our benchmark. So I want to show you a really quick sub-benchmark and how we can leverage that as well. So I've got that global variable, again, GS. Remember, I want that code to be thrown out. We're going to be using our sprint and our sprintfs again. But notice what I'm doing here in the benchmark sprint here. I've actually created an unexported function on line 26 for our benchmarks. Okay, line 26 now is the unexported bench sprint, the unexported bench sprintf taking our testing B pointer, and we're going to use the named functions, not literal functions here, on the call to b.run. It's the same exact API using the B instead of the T, and we've given it a name. So this isn't necessarily data driven like our tests, but what we're going to be able to do now is filter, okay, filter based on this subname, none or format, what we want to do. So there's our sprint none. We're not going to do any formatting, and then we give it the name format. There we are. So I can run these benchmarks here as well. I'm already in this command line. There we are. And I can do the go test again. Hey, don't run anything that might be called test something. Get all that out of our way. Let's do bench dot. Let's change the bench time to like 3 seconds, and we can still look at memory for this test. There we go. And throwing an extra little keys in there, no big deal, you'll get it. And we can see again that we've got that same output, that same 68 nanoseconds per op. It ran 50 million times, 100 million times. There it is, all right there. Let's run it again, just so we can see it a little bit cleaner again. And you can see here how the subname is now part of that output, much cleaner output this way, same as before. And the format, and because now I've got the subnames, remember now what I can do here is say, okay, let's run sprint, there it is, and let's just focus on none. And now it just comes in and just runs sprint/none. So I just were able to focus now on one of those tests instead of both, again at the sub-testing level. Now I would be very careful of running sub-benchmarks in parallel, only because you got to make sure your machine is idle when we're doing all of this. I'm going to come back very soon. We're going to start talking about profiling. I'm going to be very focused around what state your machine should be in. But just as a note right now, that when you're running these types of performance benchmarks, okay, especially CPU-based benchmarks, I mean, your machine has to be idle. You can't be browsing the internet and doing things, because that machine now is eating up CPU cycles, you know, on the hardware. So you don't necessarily want to be running benchmarks in parallel, right? We still want to run them in series, but this gives us a little extra granularity for the benchmarks that we're creating. One of the most important things you must do when benchmarking is validate that the results are accurate. I cannot stress this enough. Use your gut if you have to, but you can't just blindly trust what you're seeing. Remember, we were just talking about that your machine must be idle, and there's lots of reasons why your machine might not be idle. I mean, I'm on my MacBook, and even though I've got most of the things turned off, there's still background programs running, there's still network being used, and then a lot of times you've got your CPUs, if they have thermal scaling, right? Or if they do things where they don't go full throttle all the time. All these little things are going to matter when you're running benchmarks, and you've got to validate your results at all time. Now, there was this article I read one time that was using merge sort. Now, merge sort is like the worst sorting algorithm you could use in Go, because the way merge sort works is you take this list of, let's say, like 1,000,000 integers, you cut it in half, you cut it in half, you cut it in half, you're cutting every half in half till you get to the bottom, then you do your compares, you might swap, but on that swapping, after that, you're merging lists back, merging lists back, merging. It's really an allocation hell type of algorithm, and really one of these algorithms that you don't want to be using in Go unless you're going to write some very, very clever code. Okay, so the author said, we want to use merge sort, and what I wanted to see, the author is like, what I want to see is that if I do a merge sort over 1,000,000 integers, and I use one Go routine, how fast is that? If I use a Go routine, every time I split that list in half, I throw a different Go routine at each half, right? So an unlimited number of goroutines, depending on the size of the number of things that we're sorting, is that faster? Or if I use just enough goroutines that I have cores, so I have an 8-core machine, never use more than 8 goroutines, is that the fastest? The author wanted to know what was the fastest way to go. And the conclusion of the post was that, at least when it came to the merge sort, that only one goroutine was the fastest way to do sorting. Now, I love the messaging, because the message is, just because you throw more goroutines at a problem doesn't necessarily mean it's going to run faster, especially if you're not leveraging mechanical sympathy, some of the things that we talked about before. But it hurt my brain because I could not fathom how one goroutine could be faster than 8 goroutines on my machine. It's just, in my brain said, there's no way. Some level of parallel processing for what is really going to be CPU-bound work had to be faster, right? So I said, you know what, I don't get it. So I went ahead and I wrote merge sort. Now, I'm not going to go through the merge sort code here. That's not important. What's important is I have an implementation of merge sort, just like the author's implementation. And what I did is I went over, and we're going to start with that million integers, but I wrote 3 benchmarks, okay? Single, unlimited, and num-CPU. So 1 goroutine, unlimited number of goroutines, a goroutine for every split, and then just a number of goroutines for the number of cores that I have. And so I reconstructed everything that the author did, and I'm going to go ahead and run this benchmark just like the author did in the article. Okay, so I am in the right place. Okay, go test. We're going to run no functions, run all the benchmarks, increase the bench time to 3 seconds, and we're not looking at allocations because that's going to be nasty. We're looking at CPU performance here. Okay, there I am. So we got a single goroutine sorting a million integers, and every 3 is that millisecond. So this is 82 milliseconds it took. We were only able to do this 50 times. 82 milliseconds on a single goroutine to sort those million integers. This was 635 milliseconds to do the same sort with an unlimited number of goroutines. So look, when I just kept throwing goroutines at the problem, it ran significantly slower. And then when I gave it 8 goroutines, right, -8, we've got 8 cores. When I gave it 8 goroutines, it actually took longer than just using 1. This was the conclusion that the author had as well in the post. So I guess we should just walk away. My gut is wrong. I guess truly when it comes to merge sort, that those allocations are causing so much pain that running it even in parallel is worse than running single goroutine. Okay, we're done. No, we're not done. I still don't believe it. This is what I'm talking about with validate. You must validate your results, and this is killing me. This has killed me for like 2 hours at this point, and I won't let it go. I've done enough multi-threaded software development. I've written the algorithms. I know I've got the mechanical sympathies to the extent I can in place. This is impossible for me. I'm not willing to let this go. And then I do the following. Let's just isolate running num CPU by itself. And look at the result we get. Suddenly we went from 95 milliseconds to 55 milliseconds. Look, num CPU is now faster, from my perspective, 30 milliseconds, significantly faster than a single goroutine, which is exactly what I expected to see. So what happened here? Why is num CPU suddenly faster? Because we're going to go back to the idea that your machine must be idle when you're running these benchmarks. Think about it. We ran single on my machine while it was as idle as it could be. Then we ran unlimited on my machine when it was as idle as it could be. But when we started running num CPU in this batch, the runtime and the machine was still busy cleaning up the mess we made with the unlimited test. In other words, we had created so many goroutines that hadn't died yet. The scheduler was still, and the runtime was still dealing with all that when we started the num CPU profiling. So suddenly now, the cost of the cleanup is affecting our performance numbers with num CPU. when I bring our machine back to an idle state and I just run num CPU, suddenly we get a much more accurate result. So I like the idea that that throwing Go routines at a problem doesn't mean makes it necessarily run any faster. But when we can run things in parallel efficiently with mechanical sympathies, it really should be faster than just using a single Go routine on one core. Now we've really proven that. And so my point here is that we must always validate our results. We should have some kind of understanding or be able to predict in some way what we expect to see. And when we don't see it, we've got to make sure that we understand it and that it's not us doing something wrong, but it's really accurate. Welcome to lesson 14, profiling and tracing. Probably one of the most fun lessons in the entire training, but I'm going to stress again, please, I'm praying that you've looked through everything else before you get here, because I'm going to be going into some lower level details on implementation, and I'm going to really try to show you how these tools work in a way that's practical. And what's brilliant is I've done this entire lesson on 1.11, beta 1. By the time you see this, you'll already be on 1.11, maybe 1.12. And we've got a real advantage here to be able to start looking at the serious and significant changes that have come to profiling and tracing. I'm very excited about this lesson to be able to show you how powerful this tooling is in Go and why I think it separates Go from many other languages out there. So we're about to enter the section of Go tooling that's going to be around tracing and profiling. This is cool stuff. And we're going to probably have some longer videos here because I'm going to be doing a lot of some live coding, and we're going to be looking at the tooling. Okay, so you're going to be able to stop and pause this stuff and look at what I'm doing. I'm running on 1.11 beta 1, and there's some new things in beta 1 around tracing that unfortunately I haven't been able to get to yet, but I want you to come back to this training material over time, and you'll see new stuff. Plus, go find me, right? I'm at every conference. I'm out there writing. So it's okay. We're going to update this stuff as we go. But I love this comment from Voltaire: those who can make you believe absurdities can make you commit atrocities. And it's going back to the idea that you have to validate your results with the profiling and the tracing. Don't get fooled and then make the wrong engineering choices. And plus, we're now focusing not necessarily on optimizing for correctness, but now performance, right? That's the idea here. Is we've got a piece of software and we feel like it's not running fast enough at this point. We want to understand why and try to make some changes to the code. Now, there's two things. There's profiling and there's tracing. And the way the profiling works, and I'm only going to focus on two types of profiling here. I'm going to focus on the CPU level of profiling and memory. I'm not going to talk about blocking profiling and mutex profiling. I don't think they really add a lot of value to you. It's very hard to deal with profiling that's isolated in one small part of your program as it relates to kind of like blocking latency. It really is. I've stopped teaching it pretty much. Tracing will come in and help us look at what's not happening. I'll show you that. But the way the profiler works is that we're going to be hooking into the operating system, and on these regular intervals, the OS is going to stop your program and restart it. And then when the program is stopped, basically every thread is brought to a halt. We're going to be collecting these program counters, okay? So when we start using the profiler, our program will run a little bit slower. That's okay. We're looking for the hot paths, right? On a CPU perspective, we're looking for the hot paths. Which functions are we spending the most time in? And on the memory side, we should be looking for two things. We're looking for the number of values that we're throwing in the heap. That's garbage. That's, a lot of maybe, and how short-lived are they? That's our garbage. Number of objects, how short-lived, how transient they are. That requires more GC time. And then we might want to look at overall heap size. How much memory do we need that we're storing, and can we reduce that? This is when performance is critical, right? If you're writing databases, then both aspects of this are critical, like how much memory do we actually need to store this amount of data, and then how many objects are we creating in the processing of that that's causing the GC to run and maybe slow us down. And when we're looking for performance improvements at a macro level, then we're really going to be looking at allocations first. At a micro level is usually where we're going to start focusing on that CPU performance. That's just historically the way I've worked, okay? And we're going to go through macro and micro level types of optimizations before we're done. So a couple of things here, some do's and don'ts. I've said some of this already in the benchmarking, okay? Your machine must be idle, it must be idle, it must be idle. If you're doing profiling on a shared hardware, understand that it's relative to that hardware. Like I'm doing all this stuff on my Mac. It's a noisy machine. It's relative to what I'm seeing. You could see completely different results on a different machine and in your production hardware. Okay, and don't be browsing and looking at kitty, right, cat videos online when you're doing all this stuff. The power saving and the thermal scaling will cause fluctuations. So if you could turn that stuff off, if you really care about historical benchmarks over a long period of time, then you do want to try to get your own testing hardware if you can. You want to run that on bare metal, and you can't update the operating system ever again if you care about historical results. Okay, we're going to do everything relative to my Mac, and hopefully that's going to be relative to our production systems. As I said, there's many types of, there's CPU, there's memory, there's blocking, profiling you can do. We're going to focus on just CPU and memory profiling. I think it's going to give us the best bang for our buck, but you could use the same techniques I'm going to use to get into the blocking profiling. Now, I kind of showed you this already when we were talking about validation, right? We really need to do one profile at a time and make sure the machine is idle and validate those results. Now, there are things we're going to be looking for when we start going through the profiling. We're going to look for malloc GC calls. That means we're allocating memory on the heap. We might see some mutex calls, which means that we're going to have some blocking latencies there. We might see system calls around read and writing. That's going to be I/O latency, context switch latency, you know, all these things. Remember, I told you that there's 4 things that are going to cause us pain in terms of performance. The first one is latency on the outside, networking latency, disk latency, device latencies, right? Those are going to really kill us. You also could have internal latencies like around mutexes and synchronization. These latencies are usually death, so we want to reduce them to the fullest extent. After that, then we're looking at allocations in the heap, right? Those allocations are going to cause us performance issues. Even though the GC will run at 100 microseconds, the less work the GC has to do and the slower the pace at that point, the better. Third is how we access data, how we iterate over data, right? How efficiently do we get data into the processor? That's number 3. We've talked about all those things. And then we have our algorithm efficiencies, which our CPU profiles will show us, right? And those memory profiles will show us the allocations. All right, so just remember, large objects can affect memory consumption, could affect some GC time, but a large number of small allocations, that's gonna really affect how much work the GC has to do. And there's lots of little optimizations we can do around that. Now, there are some rules about performance. I've already said this over and over again. I know I'm reiterating myself. I just want you to listen to this before we get into some code here. We never guess about performance. We make sure those measurements are relevant. You profile, only profile if you decide something truly is performance critical. If it is fast enough, don't waste your time here. Okay, and you got to make sure that they're accurate. Now, I'm going to be using a tool called Hey, which is written by JBD or Yana, I call her Yana, over in Google. She's doing amazing work over there. She spent a lot of time on the Go team. She's now dealing with She's helping the community, every community, with observability. And if you're not following Yana, JBD, then you should be following her because she has amazing things to say. And she built this console-based tool called Hey that we're going to use to put load on some of the projects we're working on. But I do want to stress that there's an amazing tool out there called ngrok. ngrok, I'm going to bring that up for you, ngrok, ngrok.com. And if you're not using ngrok today to help with load testing, to capture traffic, you really, please, you need to look at this tool. It's a fantastic tool to help you be able to put that load and measure load. For, you know, I can't say enough about it. So definitely look at this tool. But we're going to be using Hey at this point. Just a little bit simpler on the command line. It's going to get us where we need to go. Now, Dave Cheney, if you don't know Dave Cheney, look him up. Dave Cheney's done a tremendous amount of work in this space. I've learned a ton from Dave, and you got to look at some of the talks that he's given. And if you can get a chance to get into a workshop with Dave, which I never get to do because I'm usually doing a workshop at the same time, but one day maybe I'll get lucky enough. If you can get into a workshop with Dave, do that, please. You're going to learn so much. Dave's like in the trenches and dealing with this stuff day in and day out. Plus, he's a Go contributor, and he knows the internals very, very well. But here's a bunch of videos or blog posts that I've read that are going to help. All this stuff is in the training material, and other things that are going to help you as we go. Now, there's a couple of operating system tools. We're going to use the time command here. It works in Linux, it works on the Mac. I don't believe it's part of the Windows operating system. But time is a pretty powerful command. It's going to let us see how much time our programs are taking. That way we don't have to kind of build that ourselves inside of our software. And since 1.7, we now have the ability to use perf. Perf is only a Linux tool. But because we now have frame pointers built into our applications, perf is good. Perf gives you this low-level view of how this program, this Go program, is running on the machine. You can see, we can see contexts, context switches, and page faults, and instructions, and branch misses, and all of these kind of mechanical sympathy things that we've talked about throughout the class. They're all here. Again, this only works with Linux, but your Go programs support it. Okay, great. So these are the things that we're going to need to be, that we're going to be looking at, and things we're going to remember now as we go through. And what I'm going to be showing you is how to work with those stack traces. Stack traces are very powerful. I'll show you how to get some core dumps. Hopefully you never need them. I'm going to show you micro-level optimizations, where we're going to be using benchmarks to do that. I'm going to show you some macro-level optimizations, where we're going to take a real-world program and start looking at a macro level if we can find places where we can improve. And then finally, I'm going to show you how the tracing tool works and some of the aspects of that, again, in 1.11 that you can use to help you see not just what's happening in software, but what's not happening. And Go is really making this better and better and better as we go on. And this is just and easier to work with. And I think this is the one thing that cements everybody into the language, is that all of this tooling is here. So I'm going to do my best over this section to teach you as much as I can and show you how to use these tools effectively. So one of the things I want to do first is show you how to read a stack trace. Some of you may have already been reading these, but there's a lot more information in here than you probably know. And then I'm just going to briefly show you some documentation around how you could get some core dumps if you need it, and I pray you never do. So let's start with your basic stack trace. I'm going to be using the Go Playground for this, and it's really amazing stuff. So there we are on line 7 with the function main, and main calls a function named example. And example is passing 3 things into, our main is calling example passing 3 values, right? Our slice value, a string value, and then an integer, right? You see all of that. And we're going to be on the whiteboard in a second. I'm going to show you how this stuff gets laid out on the whiteboard so we can get a better, clear picture of this. But for now, I just want you to look at how we're passing a slice value, a string value, and an integer. And when we call example, I'm forcing example to panic, which is going to produce a stack trace. And this is the stack trace that it produces, okay? And you probably already know how to read it because it's already telling you, like, we were on line 8, and then we were on line 12. And when we were on line 12, we called panic, which is line 464. So we were on line 12, there it is, and then we were on line 8. So most people can pretty much figure out very quickly that this call stack, this trace, the stack trace, is giving us where we were in the call stack when it all blew up. But what you don't realize also is all of the data that you passed into these functions are also in this stack trace. It all looks like these odd hexadecimal numbers, but it's all there, and I want to show it to you. And this is why I go back and always say write precise APIs. Write precise APIs. Don't hide information going in. Don't hide information going out, because if you don't, you've got code that's more readable, code that's more testable, code that's more maintainable, the ability for the compiler to find bugs for you before it happens in runtime. And it gives these stack traces even more power. So let's start with this. We called example with a slice. Well, what is a slice? This slice with the make call says the following. A slice is a 3-word data structure, remember? It's got a pointer, a length, and a capacity. And in this case, our length is 2, and our capacity is 4. There it is. So there's the slice that we're making on the fly, pointer to 4. Now, the next parameter is a string. What is a string in Go? We learned that a string is a 2-word data structure, pointer and a length. And the length of this is 5 because there's 5 bytes. And finally, we've got one more word of data here, which is an integer that we've put the value of 10 in. 1, 2, 3, 4, 5, 6 words of data I've drawn on the board because we're passing 6 words of data into example. Let's go back to the stack trace. What I want you to do is tell me how many hexadecimal numbers do you see that I've highlighted? Guess what? 1, 2, 3, 4, 5, 6. Bah, there it is. Now, if there were values being returned out of this function, you would see more values here. So the very first ones are the input words. The other ones are the output words. Now, let's read these 6 words, and I think you're going to be a little shocked. The first 3 represent the slice. Look at that. Address, 2, and 4, just like I had on the board. Address, 2, and 4. I've highlighted address 2, 4. The next 2 represent the string. I've highlighted it. Address and the number 5. Address and the number 5. And finally, A in hexadecimal is 10. There it is. We know every value that was passed into example before the panic. So the more precise you are, the more information you have about what's going on. This is why we don't want to write APIs that are generic. APIs that are precise, new semantic levels. Be very precise with the data, be clean, and our stack trace tells you everything. Between the logs, the code, and the stack trace, we could debug a lot of great code in Go. Now I want to show you another one of these, which is a little different. Notice on this piece of code here, we call example again, example panics, but this time we're passing 4 bytes of data, or a half a word of data on our 64-bit platforms into example, a half a word. These stack traces show full words at a time, and this time we're only passing a half a word. True, false, true, 25. Bools are 1 byte each. That's 3 bytes. uint8 is 1 byte. There's 4 bytes out of an 8-byte word. Okay, when that happens, we get this stack trace right here. We get a single value. This is all we get, a single value. But if you know your system, we know this is little endian, we can read this data. Because since we're showing words at a time, all of these bytes get compacted into a single word in this output. And since we use little endian, we're going to read this from right to left. Every 2 digits in this address represent a single byte. So watch what happens here. This was the value that showed up. Now, if we read this from right to left, 0, 1, that's true. 0, 0, that's false. 0, 1, that's true. Hexadecimal 19, hey, that's 25. 8 is garbage because we only filled up a half a word. Look at this. How amazing is this? We are able to take every 2 digits, which represents 1 byte, we read it from right to left, and I know every value I passed into this function when it panicked. This is incredible, incredible, really powerful stuff that Go's given us on the stack traces. And I don't want you to walk away from this. I don't want you walking away from it. It's too important. Now, one other thing that Go does also give you is the ability to generate core dumps. Core dumps are really powerful. And you could get to these core dumps literally just by sending a signal quit to your running Go application. If you think your Go application is deadlocked, if you need to inspect what's going on, you send a signal quit to it. On your Mac keyboard, that's literally Control and backslash. And when that happens, you're going to get a dump of every Go routine, and you'll be able to get what the registers are for that thread there that's running the Go routine. And what's even more amazing is if you use this environmental variable called Go traceback and set it to crash, then what happens is you'll get a full dump of not just your Go routines, but of the entire Go runtime and everything that's happening there. Now there's something else that's very, very cool about these core dumps. On Linux, there's a tool called gcore, and we can use gcore to get a dump of a running Go program. And when you do that, it's going to produce that kind of profile file, right? It's going to write that dump of a running Go program to, like what I'm showing you here, gcore-o write at to core.txt for whatever PID is running. And the Delve debugger, if you're looking for a debugger, Delve is it. Delve, the Delve team works very closely with the language team to make sure that there's support for this. But the Delve debugger knows how to read gcore dumps. And you can now take a running Go program, gcore dump, go into Delve, tell Delve, hey, this is the binary that we did it from. Here's the dump. You need the binary when you do it. And boom, you're now able to look at what was happening at that moment in time you took the dump. Amazing things. Thank God I've never needed any of these dumps between the stack trace, my code, and logs, because I maintain really strong mental models. I've always been really okay with all of this. But it's all there for you if you need it, the stack traces and the core dumps. It's very, very powerful stuff in Go. So I want to show you how to leverage benchmarks to do micro-level optimizations. And I call this micro-level because we're going to be focusing on like a single function, trying to make it run faster, either by looking at CPU changes or by trying to leverage memory. All right, so here's the basic idea. One day I decided that I wanted to learn more about the I/O package. I don't get to do streaming data, and everybody talks about how great the I/O package is. So I just said, I want to learn the I/O package. So I came up with this crazy scenario. I said, let's pretend that a stream of bytes is coming over the wire, and that stream has the name Elvis inside of it. And the idea is that Elvis's name should always be capital. I mean, he's the king, damn it. We can't have his name on the internet without a capital E. So this program is going to scour the internet byte by byte and fix anything that doesn't have the king's name as a capital E. So I've created this data table of input and output. And here's the input, or the stream. We'll put this into a single stream where Elvis's name can show up with a lowercase e. And if it does, like in this case here, then it should be changed to this. This is the idea. Find his name, regardless of spaces, and make it capital. OK, so I've got some functions here that can take the input and the output stream and create a single stream from it. And then in main, we're going to have a little main program that will run that we can validate some of our results with. And here is my algorithm. So let's take a look at what I do. So I start with my new buffer from the bytes package. I have my input in here. I find the length of what we're looking for should be 5. We're looking for Elvis. And then I came up with this crazy idea that I'll create a buffer of that size, 5, right, in this case. And what I'll do is I'll try to read in the first 4 bytes. If I can't, obviously there's no Elvis. And once I can, once I got at least the first 4 bytes inside my buffer, then I endless loop, reading 1 byte at a time using the I/O package again. And once I get 5 bytes, I compare it. There it is. And if there's a match, I write out the replacement, which is Elvis's name in capital E. And I read in the next 4 bytes. And then if it's no match, no big deal. We just kind of keep going, and we keep moving bytes, through the slice collection. Whatever, I had no idea what I'm doing, man. I wrote this in like 20 minutes. I'm just trying to play with the I/O API, and this piece of code worked. I was pretty happy about it. So then I reach out to the Go community and I say, hey, how else would other people solve this same problem? Now my friend Tyler, who's out there in Salt Lake City, hey Tyler, brilliant Go software developer, said, Bill, you know what? I've got some time. I'm going to give you a solution. Tyler came up with this solution. Now, Tyler didn't use a new buffer. He used a new reader, instead of a buffer from the bytes package. He also identified the number of bytes we're looking for. But then he did something really clever. He creates an index position, okay? And he reads 1 byte at a time from the input. There it is. Then he compares that byte he just read with the find index. And then he increments the index on 154. So basically, if he finds 5 matches at a time, just by incrementing the index, if he finds 5 matches at a time, then he writes out the replacement. Really nice. And if at any given time that we don't get a match, no problem. He just writes that byte out and he unreads it and he starts over. It was really, really nice. So when I take his solution and my solution here, we're here, and I just build this program and I run it, we see that my algorithm works and his algorithm works. I've got 2 distinct solutions to the same problem, right? There's lots of ways to solve problems. I've got 2 different ways to do it. So I asked Tyler, dude, did you benchmark your algorithm at all? Because I'd like to see whose algorithm runs fastest and maybe who's allocating more. He said, no, Bill, I didn't do that. I just wrote it and I gave it to you. I said, OK, I'm going to write some benchmarks. So I go ahead in my _test file, and I wrote 2 benchmark functions, algorithm 1 and algorithm 2. Algorithm 1 is mine, algorithm 2 is Tyler's. And we do all of this, assembly before we get to the for loop. So I've got to call reset timer. Critically important that you call reset timer before the loop if you're doing any significant amount of work to get to the loop. It just resets all of the program counters for your CPU and your memory and everything. So it's OK to have a bunch of stuff you have to do. We reset the timer. OK, brilliant. So algorithm 1, algorithm 2. Let's see what happens when I run the benchmark. OK, go test. Run no tests. Run both benchmarks. Change the bench time to 3 seconds. Let's also look at memory. And I think that's all we need to do. Let's do it. Now, algorithm 1 is mine, and it's running. And then we see very soon that we ran my algorithm 2 million times. It took 2453 nanoseconds per op. We had 2 values end up on the heap worth 117 bytes. When we look at Tyler's algorithm, we were able to run it 1 million times. Actually, what is that? 10 million times. Look at that. 10 million times. And he ran almost 5 times faster than I did, 525 nanoseconds per op. And he wrote a 0 allocation algorithm. I was like blown away. So I called Tyler. I'm in Miami. Tyler's in Salt Lake. I called Tyler. I go, dude, do you know you wrote a 0 allocation algorithm out of the box? And he said, no, Bill, I had no idea. I mean, that's how badass Tyler is, OK? So he's dancing in his office. I'm dancing in my office. We're really happy. This doesn't happen all the time. I hang up the phone and I go, whoa, wait a second. All of my happiness just fell into like depression. I teach this stuff every week. I didn't write a 0 allocation algorithm. I want to know where these allocations are coming from. I want to know if I can make my algorithm go faster, yet keep the spirit of the algorithm in place. OK, so I want to see what's going on. I want to know where these allocations are going. We always go after allocations first for performance. Then we can look at algorithm efficiencies for the CPU side. But I need a profile now. I need a running profile, a memory profile of this particular benchmark. Now, I can do that on the command line here by just using memprofile switch and then give it a file name. Let's say m.out. So I want to now also run a memory profile while we run this and write it to mem.out. Brilliant. Here we are. So we're going to run the benchmark again, but this time when we run it, we'll have that m.out file, and that's going to be our memory profile. So there we are. So still consistency in the run. OK, brilliant. I now have an m.out file. OK, now how do we use this m.out file? Well, we're now going to go in and use the pprof tool. Pprof tool is going to let us look at CPU, memory, and blocking profiles. We've got a memory profile. Now, the default view of a memory profile is called in use space. We don't even have to type this option. This is the default. But the problem with the in use space is it only shows you what's in the heap at the time that we generated the memory profile, right? What's in the live heap. I don't care about live heaps right now. I want to know every allocation that's ever occurred, whether it's still in the heap or not. And to get to that, we need to look at alloc space. Now there's also alloc objects if you want to look at counts of things, but I'm going to use space. So I've got to override the in-use space for alloc space, and now I can do mem.out. Okay, great. Now, the profile has the symbols in it today, so even though you're seeing main binary file name not available, it doesn't matter. All the symbols we need is already in m.out. Okay, so we're doing alloc space against this m.out file, which was our memory profile that the benchmark produced. Now, we already know that Tyler's algorithm doesn't allocate. Mine allocates. And I want to look at where those allocations are coming from. So guess what we're going to do here? We're going to use the list command, and we're going to ask the profiler to find any function that has alg1 in its name and list that out. And sure enough, we find the function that I wrote called algorithm1. Now, because the symbols are already in the m.out file, we get a full view of our source code file, and we're looking at those areas of the source that there were allocations in. Now, there's two columns here. There's the flat column, and there's the cumulative column. Now, the flat column shows you, in this case, allocations that happened on that line of code. That line of code was directly responsible for the allocation, or in a CPU profile, for the CPU performance hit. Cumulative says, let's take this line and sum up from this line of code all the way down the call stack from this point, sum everything up. So what we're looking at is the following. Out of the 328 megs of allocation that we had, 318 of it came from inside of new buffer. Okay, 10 meg came in on the flat time, 10 meg came directly from this line of code. And also, this was the only allocation that there's nothing below this that caused allocation. So we know that there's something here causing memory allocations that are flat here. And there's something inside of new buffer causing the bulk of our allocations. And we can get rid of these allocations. We're definitely going to get some better performance. But here's the problem with a profile. It only shows you what is allocating. It can't show you why. We need to not just see what's allocating. We need to understand why. So what we need is the escape analysis report in line with this profile information that we're seeing. So you know what I'm going to do? I'm going to clear out of this window right here. And you know what happens anytime you're trying to do a live demo, right? I can't hit Control-C on this. It's not dying. So what we're going to do is I'm going to kill this browser tab. We're going to keep going here. And we're going to just come back in here and run it again. You know, this stuff happens. No big deal. We're going to come back into our project here, hit copy and paste, get back into our location here. No big deal. This is where we were before. This is our mem.out. And what I really want to do right now is run the benchmark again. Okay, I want to run this benchmark again. Here it is with the mem profile. But this time when I run it, I'm going to add right from the beginning, since this has to be compiled, I'm going to do the gc flags command with the two m's. I showed you this when we were talking about how pointers work and stacks and memories and all of that. What this is going to do is ask the compiler before it runs the test to produce an escape analysis report. So let me clear the window and let's run it again. So you just saw the escape analysis get dumped to the console window first, and now we're running the benchmark again. I want all of this cleared in my one window. We're going to leverage it all. And now I'm going to go back in and do the go tool pprof alloc space m.out, enter into my profile here, list alg1, there it is, and now I'm back to where we were before. The numbers are a little different just because it ran again, but it's still very consistent in terms of that the bulk of our allocations right now are happening inside of new buffer. Okay, now this new buffer call is in the stream.go file, line 83. So watch what I'm going to do. I'm going to hit Control F on my window, type stream.go:83. I'm going to scroll to the top of the screen, which is the beginning of the escape analysis report. And what I'm going to do is look for where this line shows up in the escape analysis, because this is going to tell me why things allocate. Remember, this only tells me, down here, this tells me what allocates. We know something's allocating inside of new buffer, doesn't tell me why. Now, when I start at the beginning, we get this line from the escape analysis report. And what it's saying is that the call to new buffer is inlining. Now, whoa. This has nothing to do with allocations. It's saying inlining. What is inlining, and why is this in the report, and why is it important? So inlining is an optimization that gets rid of function calls by taking the code inside the function call and just replacing it right there in line. I'm going to show you this. Why is this part of the escape analysis report? Because this is a really important and critical optimization. Let's go back to our lessons when we were talking about allocations and go back when we were talking about pointers. I'm going to come back into our code for a second because this is very interesting. I told you that there are a few ways for a value to end up allocating or escaping off of the stack and onto the heap. The first way is how something is shared. When something is shared up the call stack, it's no longer safe to keep it on the frame. If something was shared across program boundaries, like up the call stack or across Goroutines, then it has to escape off of frames and onto the heap. Also, if the compiler doesn't know the size of something at compile time, it also has to end up on the heap. Now look at this call to new buffer. If I were to peek at the definition, look at what we're doing. Look at the return of this factory function. It is using pointer semantics. We're going to have to go back and learn. Remember, look, if you didn't go through the pointer section, you're going to be lost here. If you didn't go through the pointer section and take the time to learn about how your stack memory works and your heap memory works and the escape analysis stuff because you thought you knew about pointers, I do need you to stop for a second and go back there. I'm assuming you've looked at that material. Now, notice we're using pointer semantics on the new buffer call here. That means that we're going to be constructing a value of type buffer and sharing it up the call stack. And we know that when you share up the call stack, that's an automatic allocation. And we see it right here. Here's the construction, and here is the address of. So if I go back here for a second, this cumulative allocation makes a ton of sense. New buffer is constructing a value, sharing it up the call stack. That's an immediate allocation. And the profiler is telling you, new buffer, the semantics of new buffer, because it uses pointer semantics, means allocation. Except I am now confused. The escape analysis report is saying that there is no function call, that the function has been inlined, which means that how can there be a cumulative allocation when there is no function call? What is happening right now is the compiler is telling us that it took this line of code and said the following. Whoa, we're not going to make this function call. There's a cost to this function call. What we're going to do is inline this code directly right here and get rid of the function call altogether. Do you see how powerful inlining is in terms of allocation? If there is no function call, there can't be any allocation when that function shares up the call stack because it never happened. Technically, this data that we're constructing is being constructed here on line 83, not inside of new buffer. This is a brilliant optimization because what it means is we can create factory functions that are leaf functions and never worry about the automatic allocation. When a function can be inlined, then it can share up the call stack without the fear of allocation because it's never called. Now, how do you become a leaf function? A leaf function means that you are at the end of a call chain, that function doesn't call any other functions. That's a leaf, right? We're at the end. And the function has to be small, okay? Like 40 lines of code or less, at least, has to be small. This is small. This is one line of code. So what's brilliant here is we're able to create factory functions that use pointer semantics that share up the call stack without the fear of allocation because they can be inlined. Now, what's confusing is the report is telling us that it's being inlined, but the output of the profiler is still showing an allocation, a cumulative allocation. This is confusing because there is nothing cumulative here. Really, input should be a flat allocation if there's an allocation at all. There must absolutely still be an allocation or it wouldn't show up. I wish it showed as a flat allocation because technically this buffer wasn't really allocated inside of new buffer. It's being created here. But a profiler in this case can't show you potential optimizations. So when we look at the pprof here, it's ignoring the potential optimizations like an inline, still showing the allocation is cumulative, even though we're smart enough right now to really understand that it's really a flat allocation because of the inline optimization. Okay, so what do we know? We know that the call to bytes buffer didn't happen, or bytes new buffer didn't happen. We know that this now is inputted, but we still know there's an allocation and we don't know why. Let's go back to our report. So let's keep scrolling down. And I see some more yellow. And now we get into this section right here. Now what this is saying is that our literal bytes buffer, this now makes sense since we have a literal bytes buffer now being constructed right there for input on line 83, right? There's our line 83 again. We know that now input is a literal because of the inlining optimization. It says right here that that's escaping because, not because of the new buffer call, right? That's gone away, because of this interface conversion on line 93. Pass to call argument escapes. Let's take a look at line 93. When I look at line 93, I get here. I get the call to read full. Interface conversion. Let's take a look at the parameters. There it is. There it is, clear as day. What does read full take as its first parameter? The reader interface. We are passing our concrete data inside the reader interface. What did I tell you over and over again in this class? Decoupling comes with a cost. Indirection and allocation. So when we pass input into read full and it gets stored in that reader interface, it's an automatic allocation. Brilliant. We now know why input is allocating because we're passing it into io.readfull, which also means that if it hadn't already allocated, this call would cause problems in this call. Why doesn't Tyler have an allocation? Let's take a look at what Tyler did real quick. He called new reader. He got his concrete pointer type, but he only ever calls against the method set. The method set of his concrete data. He's not passing input into a IO function, which stores it in a decoupled state. He's using the method set for his reader, and therefore there is no allocation. He's staying in the concrete. He's not taking the decoupling cost. Okay, this is cool. And if we looked on the escape analysis report, we would see that on line 134, new reader is also being inlined. And I'm sure if we look for that, we're going to see that new reader is being inlined. Oh, there it is. Doesn't escape to the heap. And I'm sure that we'll find the inlining for that right there as well. Let's see again, what is that on line 134? Let's have this just go 134. What do you see right there? Inlining call to new reader. There it is again. Inlining call to new reader. So it's the same thing, and that's why Tyler was able to write a zero allocation algorithm thanks to the inlining optimization right there. Okay, so now we know what our problem is. We know that when we take our input variable, pass it into read full, we get the allocation. Yay for the escape analysis report. But let's fix it. Not tied to the I/O package. I'm sure input has a method set. Oh, yes it does, just like that reader does. And in fact, that read function is really identical to the I/O read call. So look at what we can do. I can pull out I/O read full and use the method set for input to pretty much do the same thing. So we can do that, and I can replace this one again down here. I've gotten rid of 2 of the 3. Now this one reads 1 byte at a time, so I can do input.read byte. There it is. Now input read byte returns the byte itself and or an error. So I'm going to do some fancy things here that I just know how to do. And what I'm going to do is tell this to place it right there. And we do this. I'm basically saying that we're going to maintain the spirit of the algorithm. It's so important for me that we maintain the spirit of this algorithm. And what I've done is I've just said, let's keep adding that byte there to the end of the buffer. And we're going to check our error. And if we get an error, then it's still not nil. And what I've basically done now is I've gotten rid of all of the calls to I/O, which would cause our allocation because of the use of interface. And I'm using the concrete method set, right, off of input. Now, just this change alone, we should get rid of one of those allocations. So let's do something. I've made a code change based on this. OK, I'm going to exit this right here. And what we're going to do is run it again. So let's do it. Go test GC flags, will run the escape analysis report anyway. Run none, bench dot, 3 seconds, memory profile, beautiful. Run it. We've got our escape analysis report again. But this is the key. We should be down to 1 allocation, 1 allocation. Let's see. There it is for 5 bytes. And we've shaved about 1,000 nanoseconds per op off of our algorithm. We're now 3 times slower instead of 5 times slower. Whew. Do you see how this 1 allocation could save you so much performance? This is why we go after these allocations first. OK, we still want to understand that last allocation. So let's go ahead now and run this again. Go tool pprof alex space m. Let's list alg1. There it is. And we're down to the 1 allocation, which is the slice. That's on line 88. So why don't we go search for stream.go line 88. And we end up here. And this says, OK, absolutely, we're escaping to the heap. The make call is causing escape to the heap. And look at what it says. Non-constant size. And this is a new message we're getting in 1.11 today. It used to say not large enough for the heap. If you're in 1.10 or less, the message there is going to say that it's not, it's too large for the heap. Sorry. If you're in 1.10 or less, it's going to say too large for the heap, which really was a bad message. This is a much better message. Non-constant size. So remember I told you, an allocation occurs when the compiler doesn't know the size of something at compile time. What is the report telling us? It does not know the size of the backing array because we're using a variable named size. Non-constant size. Brilliant. Now, that would mean that if I just hard code this to 5, I can't leave it like this. I'm going to have to live with this allocation. But if I hard code it to 5, then what? Then what it means is that I can go ahead probably and get rid of this last allocation. Let's see. Let's exit out of here for a second. Let's run this one more time. And I should have my allocation now completely gone. Let's see. Oh, there it is. 0 allocations. And now I'm a little less than 3 times slower. Do you notice how those 2 allocations were causing almost like, what is that, 1600 nanoseconds per op? Amazing. Now, real quick, we've done with our allocations, though I can't leave the hard-coded 5. I'm going to leave it right now, but I can't. Let's do a quick CPU profile just to get a sense of what we could be doing here. So what I'm going to do again is go test, and I don't need the escape analysis report again. So run none, run all the benchmarks again. Give me a bench time of 3 seconds. I don't care about memory anymore, but this time I want a CPU profile, not a memory profile. We'll write that to c.out. Now I'm asking it to generate a CPU profile of this benchmark. We've done everything we can with memory. I want to keep the spirit of my algorithm. And now I want to see, are there algorithm efficiencies that I can make to help us speed up? I now have a c.out file. So we're going to go tool pprof. There it is. I don't need any extra switches for a CPU profile. So c.out. There I am. I'm going to type CPU. And what I can do is list algorithm 1. And I can now look at, out of the almost 4 seconds of cumulative time, I can look for the largest bulk of that. Here it is in the compare. So what this is telling me now is, if I want to speed up my algorithm anymore and yet keep the spirit of it, that I got to get rid of this compare code. Really spending time anywhere else is going to not necessarily bring me the best fruit. Right? We're looking for, where do we spend our time? So this is it right here. I've got to reduce the compare. If you remember, Tyler's not using compare, he's using index at a byte level comparison. It's really why he's running so fast. So this is micro level optimizations using benchmarks. If you do some macro level optimization and you find functions that you really care about optimizing away, then what you're going to do is take those functions, put them in a benchmark, and then use everything I've shown you to get memory and CPU profiles from the command line to get everything going. I do want to show you one thing about your pprof profiler, and we'll look at it with this. There is a new switch. It's ever since 1.10. They're improving it all the time. I don't use it because I'm so efficient on the command line today, and I love bringing the escape analysis report in with the profile. You can see how efficient I was. But if you use the HTTP, I put that in the wrong place, sorry. Go to pprof, HTTP, and you give it a port. What this is going to do is open up now a UI-based view of your profile. You can see here that it gave you an initial view of a calls trace. We're going to look at this again very soon. And what's kind of nice about this UI, you're looking at the 1.11 UI. It's going to also give you these commands that we haven't run yet here, top graph. You'll see some of this very soon. But it's a really nice, and it's getting better with every version of Go. And so it could be a good place for you to start in terms of learning how to use profiling with this UI. I'm going to be spending most of my time on the command line here. But you can see, and we'll do this on the command line. I'm just so fast with the command line. But you can see here that the UI is coming along really nicely. And again, I can do alg1. This is some very cool stuff that's coming. It's going to make it more accessible to you and everybody else that wants to use the tooling. Just wanted to show this really quick. And this is just getting better and better. But moving on for the rest of the class, I'm going to be on the command line. I'm just a little bit faster with it. And you can experiment with this UI on your own. So this is micro optimizations using benchmarks. So now I want to show you how to do macro level optimizations, where we're looking for the low-hanging fruit. And we're looking for something maybe in an application that we've already written. And what I've done here is I've got a project already, okay, which is a web application that has a whole browser-based front end. I'm going to show you this to start. So I'm in this project folder here. Go build, there it is. And if I just run this project for a second, I'm listening on localhost 5000. So I'm going to come over here, open up a browser tab, go to 5000/search, okay, that's the endpoint for this web application. And you can see here that I'm ready to compete against Google to search for anything. Now, what this does is it uploads or downloads some RSS feeds, stores them in memory for like 5 minutes, and we just search against it, okay? Every 5 minutes it will recache that search. And what we can do is anytime we need something, we want to search for something, want to make sure that it works, I always ask for what my friend is doing because he's going to be all over the news. And sure enough, our friend is all over the news. There he is. We've got CNN reports, and we're going to have BBC reports and New York Times reports. He's all over the news. This is good. It means we're going to have guarantees on search. Now, I'm ready to put this out. You can see here on the output that we've been caching these feeds. Now, here's the idea. This is ready to go in production, but we want to get a general understanding if this is healthy and if there's anything that we maybe can fix in terms of allocations or CPU performance. So we're going to want to run this server under load, and then we're going to want to be able to eventually take some profiling. But even if we don't want profiling right now, I want to at least be able to get a sense of the health of this, both from the scheduling side and from the memory side. So why don't we start with the scheduling side. Let's just see how this server on my 8-core machine is handling some basic load with the scheduler to make sure that we're not leaking Goroutines, that we're handling stuff in a responsible amount of time. And I can do that by using the GODEBUG variable. And I can do this. GODEBUG equals schedtrace. And I can say generate a scheduler trace every 1 second, 1,000 milliseconds. Now, I'm setting this variable in front of running the project. We can do these types of things in our shell. You could export this first. But I need to make sure that anything writing to standard out kind of disappears. I don't want the standard out to interfere with our traces. The GODEBUG writes traces to standard error. So what I want to do is write standard out to the dev null device. This is important. I want to write it to the dev null device. So I've now started my project again. I've started it. Let's just double check that it works. I'm going to come back into the browser, hit search, got these results back. Everything's good. And what you're seeing is every second I'm getting scheduler stats. Now this is only going to show Goroutines that are executing or in a runnable state. Goroutines that are waiting disappear. Let's go through this real quick. You're seeing what time it was when we ran this trace. Let me see if I can pause it for a second. Number of procs or threads that we're using. The number of procs that are idle. All of them are idle because I haven't put any load on this yet. Total number of operating systems we have right now as part of this. Spinning threads. Remember we talked about spinning. What that meant was that there's a proc that has no work to do and it's looking to steal work, or it's just trying to keep that thread busy so it doesn't context switch off the core. And this is our global run queue. I've got no Goroutines right now to do anything with. And then this is the local run queue per P. So I've got those 8 Ps going right there. Remember, we're only going to see Goroutines that are executing or in a runnable state. OK, great. So this is running every second. What I want to do now is put some load on the system. I've already set up the Hey tool to do a post call over 100 concurrent connections. Let's run maybe a 100,000. Oh, we can run 10,000. Let's run 100,000. Maybe I'll just run 1,000,000 right now, just so we can. Let's do 100,000. Let's run 100,000 so we can get this load done over this. And we're making this call to trump on. We're going to do that. So when I hit enter on this, we're now putting load on the system. And we're going to start seeing some numbers change. And you can see here, if I just kind of stop this for a second, you can see here that in this particular case, all of the procs, I'm looking at this one right now, all of the procs are idle. Nothing is spinning, so they're all busy. Okay, and you can see we had 59 Goroutines in the global run queue that weren't taken yet for work. And you can see the distribution of Goroutines in a runnable state that are waiting. So the scheduler is trying to distribute this work as cleanly as possible, but some things get done faster than others. Okay, let's see what happened here. We're still running through this load, and you can see a couple of things that I'm kind of happy with. I mean, we've got a bulk of work coming in. It's getting piled up, but then it's getting done. You can see right in here for a second, you know, a bunch of work came in. We had all this work, but we got it all done fairly efficiently. It's still going through. That's kind of cool. And we see that I don't see any Goroutines leaking. Now, we really wouldn't see Goroutine leaks here, because a Goroutine leak, honestly, would mean that a Goroutine is in a waiting state usually, and that means that it wouldn't show up. But if you have Goroutines that are leaking that kind of move into waiting and running states, you might see that our run queues and these local queues just start to grow over time. We could tell now that the work is done, because immediately when this work is done, all of these Goroutines went back down to 0. This also shows a huge amount of health in the system, that we're not leaking anything, everything is running and everything is getting done fairly efficiently. So This is pretty cool. This makes me feel pretty good about the health of the system in terms of the scheduler. Okay, let's kill this for a second. We know that workload is done. That's great. Okay. But now I want to look at a CPU or memory profile. I'm going to knock this down to just 10,000 requests. And I'm going to change this up a little bit now. Instead of using sched_trace, let's use gctrace. And here we just say equals 1 to get it set. So now what I'm going to ask for is a garbage collection trace every time a garbage collection starts. We don't see a trace yet because I haven't run anything. So why don't we just do the following here. Let's just run one search again. I just finished running one search. And you can kind of see how, let's make this a little bit larger, how 2 garbage collections occurred now just on that one browser search. Now let's go through what these numbers mean so you can get a sense of the health of what we're looking at. So what we see here is GC1, GC2, that's the first and the second garbage collection. You can see how many seconds in we were when the trace happened. We can see how much CPU, what percent of CPU the GC had to use to get this run done. 0%. It was very, very fast. This is the wall clock. And the wall clock shows 3 aspects of the GC. This is stop the world time, trying to bring those P's to a safe point. This is concurrent time. This hopefully is the bulk of it. And then this is stop the world time as it relates to the cleanup. So the number on the left and the right of the plus is our stop the world time. That should really never add up to be more than 100 microseconds. It might happen a few times when we're growing the heap, but overall it shouldn't. And we see that pretty good here, right? That was 78 microseconds. This one was like 98. It got pretty close. And that's that concurrent time. So the wall clock is something I'm going to look at as we inspect the GC trace. This is the CPU clock. It's the same thing, stop the world time on the plus side, but the concurrent time is broken into the 3 phases. As in case, we have one time here on the wall clock. This is broken into the 3 phases. There's documentation in the repo to teach you what these numbers mean, but we're really just looking at the 3 phases of that concurrent time. So we're going to look at this and make sure that we're healthy in terms of stop the world latency. Now this is the heap information. If you think you have a memory leak, this is the only place that you can go. This is the size of the heap before GC. This is the size of the heap after GC. And then this is the size of the live heap. So you can see here that we have a 4 meg heap beginning and ending with nothing in the live heap. All of that was kind of transient, I guess, and it went away. This is the goal for the next run, and this is how many logical processors we have. Now, something you just saw happen was a forced GC. If the program is idle enough, then the GC will force itself to run, and you can see that we've knocked the heap down from 4 to 3 meg. And the heap is in megs. If you think you have a memory leak, I'm going to ask you to run this GC trace, because this is the only way to really know if we're leaking memory in the heap. What you also seen, which is cool, is now the scavenger. And the scavenger runs in the background trying to release memory back to the operating system. Okay? We haven't released anything back because our heap is very, very small, but the scavenger is there to release memory back. So let's run a quick load of 10,000 requests, and we'll take a look at what that heap looks like when it's running. So I've just started putting load again. And you can see that there's a lot of garbage collection going on, but you shouldn't panic about this. A busy Go program is probably going to have a GC pace of a millisecond or 2. We can look at what the pace was, because we're trying to maintain the smallest heap possible, running at a reasonable pace where our GC latency times are 100 microseconds or less. So if we look at this right now, we can see that we ran about 2,190 garbage collections to get through that whole GC trace, right? 2192 to get through the whole GC trace. And if I look at a few things here, we could start with the pace. If I look at any 2 lines, we can see that was a 2 millisecond pace, 2 millisecond pace, 1 millisecond pace. So I'm seeing a 2 to 1 millisecond pace. I'm okay with that, especially if we got stop the world times that are 100 microseconds or less. I mean, that's pushing 100 microseconds, right? 31 and 70 were kind of over. That's a very large GC latency run right there. We can see that we grew the heap from 5 to 10. We doubled it in this case, so probably not surprising. And overall, though, I think we're looking at, actually, I start looking at this, I'm seeing a lot of stop the world times that are very close or over 100 microseconds. That's starting to bother me a little bit here, right? We see a lot of heap growth. It's almost like we've got a lot of Goroutines that are getting created, and then they're running in these large bursts, and we've got a lot of stack or heap growth going on. This actually is scaring the heck out of me when we kind of look at this. I don't like what we're seeing here. It almost makes me feel like maybe we're over allocating somewhere where we shouldn't. So we're still running at a nice pace, but seeing a lot of fluctuations on the heap, which could be an indication that we might be allocating a little erratically as this program runs. So what this heap profile is telling me is I want to investigate this piece of software more. And the only way to investigate this more now is to try to get a memory profile out of the app. So the next step now is to get a memory and then eventually a CPU profile out of this app to see if we can improve its performance. So Go makes it very easy for us to get a memory profile out of a running Go program. We just got to set up a few things ahead of time, and then we can do that. And I'm going to show you that with a kind of a production level project. And I've done these things already in the sample code we're running, but it looks a little bit more polished if we look at that. So in my service repo, I've got this service code here. And every one of my services do this. And if your service is going to be able to run behind the firewall, you want to do this. It doesn't cost you anything until you hit it. If it's something that's running in front of the firewall, don't do this because you're giving up a lot of information to somebody who knows it's there. Now, I'm going to go into my main.go here for this service. And I do this with all of my production software. I'm going to look right here, and this says, start the debug service. And what we're going to do is bind the default server mux to a local host port. Okay, so I'm using the server value here, binding the default server mux over some local port that's configured, and then I'm using listen and serve to host the default server mux on that port. And what's going to happen is this. Now that this is bound, right, on some port, all I've got to do is import pprof. Look at this. This is kind of cool. I'm going to import net http pprof. And by using the blank identifier, what this means is, hey, there's an init function in here that is binding a route to the default server mux. So when I come back here and bind it, guess what? I'm going to have some routes that give me back CPU and memory profiles. How cool is this? And this is all I have to do. This is all I have to do. And I've done this already in my other project. And you know what that means, that I've done this in my other project already? It means that this endpoint now exists. Debug pprof. This endpoint now exists. And what we can see here is my project's not running, right? I hit Control C. So what we're going to do again is run this. So let's go back and run this project again. GC trace project greater than dev. Let's put that load again of 10,000 through the server. Let's do it again. We'll see how many GCs that we end up running. Actually, I just realized that we're going to take a small hit on this run with our cache. So what I'm going to do is run this again. I'm going to run this again. Let's do the following because I want to make sure this is good. And we're going to run it. I'm going to come back into the browser, just hit our endpoint real quick, localhost 5000 search. I'm going to ask for our favorite friend here. Here we go, just so we get some news. I'm guaranteed news with him. We do this. I hit search. We got to run. There it is. And we know our stuff is cached. We've got 2 GCs in. Now let me run this load again. Over 10,000 requests, over 100 connections. We see the GC is running again. And what we can see here is this time we had 2,300 and let's just call it 81. 2,380 garbage collections on this run for this. Let's look at our performance. You know, I forgot to look at our performance before. So 1526. So what do we know? We know that right now we're running at 1,526 requests a second, okay, which took us a total of 2,383 garbage collections to make that happen. So 2,380 over 1526. Okay, let's remember that. Now, great. Now, what's nice is I've already got a memory profile. So if I come back now and say debug pprof on my endpoint, how cool is this? There it is. I got this endpoint for free, all because, I'm going to remind you again, all because I bound the default server mux to my local host and port. This is the code that you need to do that. And we went ahead and just imported with the blank identifier the HTTP pprof package. Boom. I just do that, and guess what? I get this all for free. Like, you're looking at the 1.11 output, which is really nice. There's more and more stuff happening here on every release of Go. And you can even see it's telling us what all of these things are. A sampling of all past memory allocations. If we click on that, I want you to look here. We've got debug pprof Alex, and this is raw heap data, pprof Alex right there. That's our raw heap. We've got our blocking, stack traces that led to blocking, command line invocation, the number of goroutines. This is telling us exactly how many goroutines we have in our current program from the last time that I refreshed it. Remember, it said 14 before. Now it has just 8. So we could see that this program started to release some of the goroutines that it needed. Now, this is our heap profile right here, actually, right? A sampling of memory allocations and live objects. You can specify the get. We can do that. We're seeing all of that. We've got our mutex. Look at all the stuff that's here. It's really amazing. Now, a sampling of all past memory allocations. Interesting here. If you were using 1.10, all you would see is this heap URL. And this is our alloc URL. So it looks like here a sampling of memory allocations on live objects. So we're going to do a couple of things here now. What I want to do is use this, these URLs, because these URLs give us, you see debug pprof heap, debug pprof alloc. These URLs give us access to our heap profile. So let's do some experimentation here. I want to look at the heap profiles now of this running program. It's already ran, so we already have this history of Alex here, sampling of all past memory allocations. I kind of care about the past memory allocations. So let's see if we can use this endpoint here, Alex, to give us a nice view of history in this program. I don't have to run any more load here anymore. All I have to do is go tool pprof, go tool pprof. Again, I'm saying I want to look at Alex space, and I can give it this endpoint without the debug stuff. And what this should do now is give us a profile over HTTP of our running program. And if I just say maybe give me the top 40 functions cumulative, look at what we have here. I now have summed up at the cumulative level the top functions that are allocating in my program. Again, remember, I used the alloc endpoint here because that's showing us the past allocations. If you're in 1.10, you're going to use pprof heap to do this. But you're noticing here in 1.11, you're noticing in 1.11 now, they've separated, it looks like, the sampling of memory allocations of live objects. That's what's currently in the heap, with a sampling of all past memory allocations. And I want it, when I'm looking for low-hanging fruit, I'm looking for the past. So here we are here. And if we look at this sort, it's not surprising we're starting at the socket connection, and we're looking at the mux. That should float to the top. We know we're rendering HTML, so that's coming up. But this is what gets interesting to me, this line right here. This is the first time I see a piece of code that I wrote, and it's RSS search. Brilliant. And you can see out of the almost over 8 meg of cumulative allocations we've had so far, more than half of them are coming from RSS search. So That's a clear indication that maybe we're over allocating here in RSS search. Okay, no problem. Let's go ahead now and look at RSS search. So remember, what I can do is our list command. So list RSS search. And here we go, and we get that list again, and we're able to look at our flat and cumulative allocations. And it's showing that we have 4.7 gig of total allocations here. And if I scroll down and look for the big ones, oh my goodness, look at this. The bulk of the allocations are coming from line 119. If we look at line 19, I see this call to string contains and strings lower. It's all cumulative, so it's happening in one of these two functions. Now, I don't want to guess which function it's coming out of. So look at what I can do. I can use the web command to get a call graph, a visual call graph, and I can filter it just on this function here, which is RSS search. Because if I just do web in this program, it's going to be a very, very large call graph. I want to isolate anything that touches RSS search. When I do that, I have a nice isolated call graph right here. Let me just show you why I use the list command for this. If I just say web, this is just much bigger, right? I've got to search through this for what I'm looking for. Much bigger call graph. I don't care about all of this. What I care about is just this. And when I look at this, I see RSS search right here. I see the almost 5 gig of cumulative allocations. And look what comes next. To lower. So to lower is my culprit here. And it's because to lower is doing something with strings.map. OK, to lower is my culprit. So here we are. We've got to figure out what's going on with to lower. I know what to look at to deal with these allocations. So let's go back and look at our source code now. When I come back to our source code for our project, we've got to look at the Go training here. And I know that, because I have a mental model of this code, I know that that function is right here in RSS search. If we look at line 119, here it is, I start to understand why we have so many rogue allocations. Look at what this code is doing. When it's searching the RSS feeds for this description, right, it's trying to find the topic in this description, it is converting the description to lowercase. That's going to be an allocation because strings are immutable. Every time we do this, we're causing an allocation, and descriptions are large. So these are not only a lot of allocations, they're large allocations. I mean, heck, I'm also doing it on term. This is crazy stuff. What a waste of time. And I really wrote this code, by the way. I wrote this code for some other things. When I first profiled it like this, I couldn't believe what was happening. I couldn't believe I wrote this code. So let's fix this, because here's the reality. We are caching these results after we download them off the internet. This is the call to the cache on line 197. So couldn't we do the following and get rid of all of these allocations? I could use my pointer semantics here, just because we're going to do some mutations. And what I could say is, let's go ahead and already turn the descriptions to lowercase before we put it in the cache. Now, I will tell you this. We really should have a separate field for this. I just don't have time to do that. So we should really keep the description the way it is and have a second field for the search. But let's do all of this. Let's make everything to lower before it gets into the cache. That means that all these extra allocations on the loop go away. And it's really silly to be causing allocations on term when we can do it just once and get rid of all these allocations. Look at what I just did. The profiler showed me that we allocated almost 5 gig of memory because of these two lower calls, when it wasn't necessary, because we can do these two lower calls one time. We've got to fix out what's happening here. We could do this one time and then reset the descriptions appropriately. So I've got a syntax error here, and that's because the package is called strings, not string. Good. So we're going to come in, we're going to do these allocations just once before the cache. We won't feel them. We'll do this allocation just once before the loop. And now we're not over allocating inside the loop. And it's all thanks to the profiler telling us about these extra allocations. OK, this is pretty cool. So let me exit the profiler for a second. Now, let's remember where we were at. We're at 2381 allocations versus 1526 requests per second, right? OK, So what we're going to do here is I'm going to hit Control C. So we've got this line in the sand here. I'm going to run project again. Actually, I'm sorry, I got to build it again anyway. So let's build it. And we've built it again. We've got our new version of the code. I'm going to do this just so we draw a line in the sand. That's fine. And we're going to run it again. There it is with our tracing. And now I'm going to come in here, and we've got this. I'll draw this line in the sand again, just so we know where we were last time. And here we go. I'm going to run some load through our project again. There it is, 10,000. Boom, I'm running it. We see that it's running again. This is with the new changes because we did a build. Notice that we're now down to 1,326 because we had 2 before, 26. We just cut about 1,000. Where we're at 1,328. And if we could find the beginning of this, I mean, we were at what? Where is that? Come on, come on. There we go. We were at 2381 down to 1328. Oh my God, I mean, we cut 1,000 garbage collections out of this just through that fix that we made. I want you to notice that the pace hasn't changed. We're still running at the 1 to 2 millisecond pace, but we should be seeing some much better things in terms of memory here. All right, and again, we don't have any leaks going on, which is great. And let's go back and look at our performance. So we're now at 2,066 requests a second as opposed to 1,500. We added, what, like another 500 requests a second just by clearing up this memory allocation. I mean, that is absolutely amazing. We did very little work to do it. And I was able to pull the profile already out of the running Go program. So look at what we just did by having those endpoints in place and being able to use that alloc endpoint like we did because it's showing us history, right? It's showing us history. That's how we ran the profile. I was able to find some low-hanging fruit and clear this up. And now I'm feeling pretty good about my memory situation. We had an extra 500 requests a second, even with all of the work we're doing with templating. What's nice to do now would be to get a look at the CPU profile so we can see if there's anything we can do from an algorithm efficiency standpoint with the profiling that we've already done. So we just went through the exercise of looking at a memory profile for that running Go program because we had the debug pprof endpoints bound into the server. Now I'm running on 1.11 beta 1. By the time you see this, 1.11 will well have been out, and 1.12 is coming. I'm really excited to have been running on 1.11 because you're starting to see some of the really big changes that are coming. And as I was doing this last section, I'm just going to be honest with you, I started seeing some things that were brand new to me, and I feel like it's very important that I kind of lay this out for you now when I have the opportunity. So if you're still running on 1.10, you're not going to be necessarily confused. And now that we're on 1.11, some of the things that it looks like they're making easier, plus probably imagine a lot of this also is for some of the UI tooling that's coming. Now this was the debug pprof view endpoint on its own. This is new, and it's got profile descriptions. We didn't have this in 1.10. And one of the things that started to confuse me a little bit was this endpoint called Alex. You see, you've got an endpoint called Alex, and you've got an endpoint called heap. Now, we've always had the heap endpoint, okay? We've always used the heap endpoint to get both our in-use and our in-use space and our in-use allocations, but the Alex space for both, I'm sorry. So we've always used the heap URL to get our in-use and our Alex space. So we always used it to do our in-use space and our Alex space, which is why you saw me use the Alex space switch on the command line like you just did. And that's when we were using heap. So I'm in 1.11 and I want to show you something. I'm going to go back and use the traditional heap URL with the Alex space flag. In fact, let's not do that. Let's start here without any flags. I want to show you this because I think it's going to be really important. I don't want you to get confused later on. So look at what I do. Go to pprof using the heap URL. And when I do that, I want you to look at the default type. The default type is in use space. Remember, that's just going to show us what's currently in the live heap. If I do top 40 cumulative, I don't see anything because the heap is empty, right? If we go back to our browser, remember what this says. The heap is a sampling of memory allocations of live objects. Now, what that means is that when you use the heap URL, you're defaulting into in-use space, okay, which is also the default for the profiler anytime you're looking at a memory profile from files and stuff. But watch what happens when I use Alex without any switches whatsoever, pprof Alex. Notice now that this URL is able to default the profiler into Alex space, not in-use space, Alex space. So one of the things I'm learning here is that the new Alex URL is defaulting the tool into the Alex space, and I didn't have to manually switch from in-use to Alex. If I do top 40 cumulative, I'm now seeing what we saw before. So in that last video when I was running this, I had manually put Alex space on the Alex URL that was redundant because it was already going to use that. But what's kind of interesting is that if we can still maintain the heap URL and say Alex space, and what will happen is it will then switch to Alex space and we'll get the same top 40 cumulative. So the heap URL, or both URLs, are basically giving us access to that same memory profile. So I don't want to get confused that this is a different memory profile than this one. It really isn't. We can see the counts are the same. It's just what the default mode is that we're getting into. So if you use heap, the default mode is going to be what it's saying here. It's going to be the live objects. It's going to be in use space. If you use Alex now, you have the ability to default into Alex space, which is cool because you don't have to then remember what flags to use. So that's kind of cool. I mean, we could start using that, but because it's the same memory profile, you are able to override all of that like you just saw. You're able to override all of that. So I can do now, I can say alloc objects. Let's see, I haven't run that in a while. Now we're in alloc objects mode, top 40 cumulative on the sort, and now we're going to see a % of objects that are going there. I like looking at space better than objects, but again, it really kind of shows what it is you're really looking at. So just to sum up right now, at least in 1.11, you now have two distinct endpoints for looking at memory allocations. You have the traditional heap endpoint, and you have the traditional, now the new Alex. So the heap is the traditional one, Alex is the new. The only difference is what default mode the tool profile goes into. If you go ahead and use heap, your default mode is in use space. You can override it on the command line. If you use Alex instead, what's kind of cool is your default mode is now Alex space. Obviously, that could be also overridden from the command line. So this is all kind of new stuff that we have in Go 1.11. Now let me show you how to get a CPU profile from your running Go program. This is a little different than the heap profiles because the heap data is historically there. When we're going to get a CPU profile, we actually have to be running load over it. Now the default amount of time a CPU profile wants to take to gather statistics on the running program is 30 seconds. Now you got to worry about whatever timeouts you have on your endpoints. If you have endpoints, like if you configure your server to time out in less than 30 seconds, your profiling is going to start bugging out. But we can adjust the seconds. I'm going to do that. So I've got my program already running because we're where we are when we're doing the heap profiles. And what I'm going to do is put load on that server again. But I wanted this to run for at least maybe 10 seconds. So what I'm going to do is just tell it to run about a million requests. We'll kill that later. but I'm going to run like 1,000,000 requests on this so we can get enough time to generate our CPU profile. And in this tab here, we're going to use the Go tool pprof again. Remember, I need no switches for CPU profiles. And again, we have the endpoint called profile. So if I come back to our browser window, you now see there's a link called profile. This is the raw, so what's happening? Oh, you're going to do this all the time. I've got to hit X. By default, this profile, again, this endpoint wants to run for 30 seconds. So I hit it, and it was trying to run for 30 seconds. The only way to do this in the browser properly is to already say seconds equals, let's just say 5. And now it should only run for 5 seconds. And hopefully it comes back here on the browser window. But I didn't say equals debug equals 1. Right? Like, look at what I did here. Alex, and then it does debug equals 1, so it actually writes it out. So let's just try that again just for fun here. I'll bring this up like this. Profile, we want to run seconds equals, let's just say 2, and then debug equals 1. Maybe we'll get some output this way. Let's see. Nope, it didn't give it to me. Anyway, it downloaded it. If I look down here, it still downloaded it even with the debug equals 1. So that's something I'm going to have to play with. But this is the profile link that we're going to use. So this is what we're going to do. We're going to put some load on our server, and then I'm going to hit this, and I'm going to say take a 10 seconds. I think it's S for seconds. We can double check here. Profile you can use, I believe it's seconds. So we're going to say take a 10 seconds of profile data, and we'll go from there. So here we go. Let's put on some load. OK, we know it's running. There it is. Now I'm going to say gather 10 seconds of profile data, which it didn't like, so we'll try it again here. Debug pprof profile. If it doesn't work, we will, there it goes. OK, fetching for 10 seconds. I hope it's plural. If not, we'll do it again. Hey, I'm learning some of this stuff as you are, especially because we're in 1.11 beta. And look, I'm not going to sit here and try to look perfect here. Life isn't perfect. So you're looking at this stuff as well. Obviously, I think we've gone beyond 10 seconds already. So it's doing a full 30-second search. So I probably should have used a lowercase s on that parameter for 30 seconds. But it's running, so let's finish it. So it did. It ran for 30 seconds. It didn't respect this. That should have been a lowercase s after seconds. No big deal. I had enough load going through this where we were able to run it. My fan just kicked in. So let me just kill this stuff because I got the profile that I need. So look at what I just did. I said go to pprof, gave it the profile endpoint. Wish I had said lowercase s under seconds. I didn't. That's OK. We got a full 30-second profile. And now I can do the same things I did before. Give me the top 40 cumulative functions that are taking the longest to run. Not surprising, again, we've got connection and HTTP server up there because everything kind of starts there. And I don't really see anything other than standard library stuff because this program looks like it's running pretty efficiently. But again, I'm able to get my top, which means I can now even look at things like execute template. Remember, we could always say list, execute template. We should be able to find that. You can see where that 37 seconds. This is standard library stuff, so I don't particularly care about that. But the idea is that this profile endpoint is giving you the ability to take a running CPU snapshot of your server while it's running, and we can start seeing maybe where are we running the longest. And if you're having production problems, this is a cool way of starting to see where we're having problems in the code and where should we go to maybe try to fix that. And it's all right here. And again, this is the only place as well you're always going to be able to see the number of goroutines that you currently have in your Go program. And all of this data is raw data that the profilers and the tooling that you're seeing uses to do all of this stuff. All right, so we've seen now how to do a CPU profile of a running like Go program as long as you're binding the debug pprof endpoints into your server. What I want to now show you is also how to use the execution tracer to be able to help identify maybe potential performance problems, because a profiler is great. It can show you what's happening, but sometimes what you need to see is not what's happening, but what's not happening, and the tracer can give us both. But let's start with this basic program, and we'll walk through how all this could be used. So what I wanted to do one day is write a function. That entire purpose was to search n number of documents of RSS feed documents, and find how many times this topic shows up in every document. So it's a simple find function, right? It's got that global variable 55 is found. We range over all of the documents. We don't know how many we're going to get. It could be 1,000, it could be 1,000,000. And then we do these 4 steps. We open up a file. We read the entire contents in because it's XML. We need the whole thing. We unmarshal it into a local variable document. And then we search that document, the RSS feed, and we increment a local counter. Not a very complicated. There's 4 stages, and we're able to get some counts. So I wrote a main program. What the main program does is it searches 1,000 documents right now. We're going to pretend this is a unique number of documents. We have to think about scale. We've got to imagine what happens if there's 1,000,000 documents. But let's just pretend right now we've got 1,000. We're going to look for the term president. We're going to call our find function, get back a number, and write it out to standard out. Okay. So I'm already in this directory. Let's build it. And then what I'm going to do is use the time function to tell us how long it takes. Now, when I run this, it took 821 milliseconds to find the term president 7,000 times in those 1,000 documents. We know it's going to take more time for more docs, but this is where we're at. Now, let's say that we know this isn't going to be fast enough, and we want to make this run faster. Now what we have to do is start leveraging our tooling again, our profiling. Let's start with profiling. Let's see if the profiler can help us figure out a way to make this program run faster. Now, another way you can use the profiler, which I haven't shown you yet, is by using the standard library. The standard library has a pprof package. That pprof package is part of the runtime folder. Now, the pprof package here, we're going to say start CPU profile. I'm going to make it simple on myself and write it to standard out. We'll redirect the profile on the command line, and we've got to make sure we call stop to be able to flush and finalize everything that we're storing in memory. So start CPU, stop CPU profile, brilliant. Let's save this. Let's build it. There we are. We build it. And let's run it again. But this time, remember, I got a profile coming out of standard out. Let's redirect it. Brilliant. Now, I want you to notice that it took longer to run the program this time when we're running a profile. That makes sense. Remember what we talked about earlier. A profile means that the program is hooked into the operating system. The operating system at regular intervals will interrupt it or stop the program, collect those program counters, and start it all over again. So this is going to run slower because it's just being stopped. I don't care about that. What I care about now is I have my p.out file. And what can we do with profiles? Well, we can run go tool pprof like we've been doing and give it p.out since this is a CPU profile. Brilliant. There I am now in my type CPU. Now, what do I want to do? Well, I already know about find. This is almost like a micro level optimization like we were doing with the benchmark. So I'm just going to say list find. And you can see there are a couple functions that were found that were named find. That's OK. And I'm going to come in here, and I can see our find function that I want to optimize. And what we see is that out of the 760 milliseconds of cumulative time this function took, the bulk of it, almost all of it, happened right here on the open file call. So if we want to spend any time speeding up this program and this algorithm, the way it's written, we've got to focus on open file. Now, if I get a call graph here, here's that red section of the call graph. I could have kind of isolated it by saying web list find, but I didn't. We could see that that open file is coming right down. And at the end of the day, what we're going to learn, unfortunately, is that if I want to make my program run any faster, I need a new operating system. The syscalls are killing me. Well, we're not about to replace our operating system anytime soon, are we? No. So here's a situation finally where the profiler is not helping us figure out a way of optimizing or making this program run any faster. I'm not replacing my operating system, and to focus on anything else here would be a total waste of time. Okay, so this is not helping me. Let's clear this out. Let's try the following then. Let's say profiles in this case are not my friend. Let's go ahead and run a trace. Now there's lots of ways of running traces. You can do it on the command line like we did before. You saw me doing that with the profiling. You can use the -trace commands on benchmarks. All of that stuff is there. But what we're going to do is use the standard library here. And I'm going to say start a trace, write it to standard out, and stop it. So let's run this program again. Let's build it. Great. Let's use our time trace, but this time it's going to be t.out. There we are. Now, notice that our performance came back. And that's because a trace doesn't have to stop the program. What it's doing, it's tracing every single function call in and out down to the microsecond. So there is a tremendous amount of data that's collected, but it's not slowing our program down significantly. OK, great. Let's take a look at this trace. Now, go tool trace t.out. Remember, I'm running 1.11 beta, so this is all the new stuff that's coming. And there's cool aspects of the tracing package now, which we're not going to be able to play with, unfortunately, which allow you to do tagging and regions and tasks and annotate this stuff, which is going to make this even more powerful in the future. Now, let's take a look at this trace. I'm going to click on that first link. There's all of these links here that give you information. One of the more powerful ones really is this Goroutine trace. You can see right now we only had one Goroutine, but we're able to get a lot of information about the Goroutine in terms of how many microseconds of GC sweeping, how many, in this case we had GC pause times of 12 milliseconds over the full 838 milliseconds. Look at all this information that we got about this one Goroutine. But we can come back to that when we're ready to kind of look at a Goroutine at a very individual level. Let's look at the larger trace first. Now, what we see here, I'm going to bring this down, is a view of the trace from beginning to end. We have the ability to kind of look at a block of it and see how long it took. That was 844 milliseconds. We kind of knew that already. And we have the ability to kind of look at things. Now, let's take a look here. This is the number of Goroutines that we're running. You already know that we're a single-threaded Goroutine program, yet it looks like at some point we've had some more Goroutines. Let's kind of maybe open that up a little bit. Now, what you're seeing me do is hold down the Alt key and scroll my mouse down. I'm holding down the Alt key and scrolling my mouse down or up to open this up. And I want to open this up just a little bit here. And you could see that we had some extra Goroutines that came in. What you're also looking at on the next line is the heap. Now you can see there are two colors, and they tend to change these colors with almost every version of Go. We're now using these kind of like Pascal colors. It is what it is. But you can see here this like maybe brownish color and then the light green color. So the light green color is the heap. That is the size of our heap. And if I click in this right here, then I should be able to get a sense of how large the heap is. And it looks like we're probably there at around 4 meg, which makes sense. This is the live heap. And what you're seeing between the live heap and the regular heap is the live heap is growing. And then it looks like it drops down. And then it grows again. And it drops down. And this kind of makes sense because this line right here in the light blue is garbage collection. And if you really look at this now a little deeper, we start to see some interesting things. Notice how the live heap drops all the way down once the GC is completely done. So we now know what's kind of happening here. We know that the live heap is growing to the top of the heap, and then the garbage collector runs, brings the live heap down, it gets to the top again, garbage collection runs. And this is also why we see more Goroutine. Since the garbage collector uses Goroutines, then we can also see that there are more Goroutines in play here. Let's see if I can click on one of these right there. There it is. We know that there were 3 Goroutines running at that point. When the GC is over, those Go routines go away. They're no longer in that runnable or executing state. Really interesting stuff. What we're also seeing then is how much CPU the GC is using. I mean, I can look at the total amount of time it ran, but we can also see that it's using a lot more of my CPU. We can see these lines going all the way down. We can also see the different phases of the GC if I open this up a little bit more. Now, our algorithm is running on G1. There's our G1. You can see that our G1 kind of stopped for a little bit of time and then started again. We can kind of look at what this amount of latency was. So for about almost 35 milliseconds, we didn't do any of our work. This is kind of like possibly kind of stop the world time as relates to our work because we're not getting any work done. Interesting stuff. But you could see that at some point the marking work, right? The garbage collection marking work is happening on P1 during that time. Any lines that you see underneath like G1, these are system calls that are being made. And sometimes when you see that a Go routine has been context switched or it's been paused, you can see these blocks of system calls going on here. You can also see there was this slight pause between this Go routine. We can also come in and see the stack trace for where that Go routine was right before that pause. So all that information is right here. We're going to kind of go a little smaller so we can see the full stack trace there. We're on find line 74. Okay, so just from this view alone, we can see that we started our trace right here, and another Go routine got started right there. There's also this cool little flow events option where you can see where Go routines are being created and then running again. That's kind of cool. But overall, what's interesting to me here is the following. If we look at this at a more macro level, we see that our Go routine started on P0. There was a garbage collection that happened. If I dig into the garbage collection, we will see G1 bouncing a little bit. It's bouncing down here. Now it's on proc 2, proc 1, back on proc 0, whatever. It ends up back on proc 0. But then after the next garbage collection, it's running on proc 2. Then after a couple more, it's running on proc 0. You could kind of see how garbage collection can create a lot of chaos in your program. But here's the thing that I really want you to take notice of. Notice that we can see where our performance problems are coming from, where the profiler couldn't tell us. Where's our performance problems coming from? It's coming from the fact that we're only using one P at a time. Look, I'm tracing it with my mouse. We're using only one P at a time. It looks like that we're leveraging a large amount of time. Remember, we didn't have a lot of stop the world time here. But if we could use the entire number of CPUs, all 8, I mean, this has to be able to run faster. I mean, that's got to be our goal, to use the full CPU capacity for this problem. I'm only using one Go routine. We see that right now on this view. Okay, so let's make some coding changes and try to go after getting more of our CPU capacity involved and not just have it being used for garbage collection. Now, one of the first things we can do is take a look at what our algorithm does and find a simple solution to getting work done. Now, notice that for every document we have, we got to open it, read it in memory, unmarshal it, and then search it. I love trying to solve problems with one Go routine first because it helps us understand what the workflow is, and then from there we should be able to understand how to distribute the work. And this is a distribution problem, right? Technically, what we could try first is a fan-out pattern. Think about this. Since we've got all these individual documents, couldn't we give a Go routine their own document to work on and throw all the work at the scheduler and tell the scheduler, you handle the concurrency here. I don't want to deal with it. You do this as efficiently as possible. Since you know what Go routines are doing anyway, you're going to be smarter than I am. So why don't we try a fan-out pattern first, at least over these 1,000 documents, see if we get any extra performance improvements, and then from there, let's see if there's other optimizations we want to make. So we've got our found. The first thing we've got to do is figure out how many Goroutines we want to create. So what I could do right away is say, well, we want to create a Goroutine per length docs. And we've got to be able to do orchestration here. So we're going to use our wait group here. And what I'm going to do, setting to its 0 value state. And what we're going to do is add those Goroutines. We can't allow find to return until all of the Goroutines sum up their found counts all in one place. We've got an orchestration problem here. We're going to use the wait group to deal with orchestration. So we've got our Goroutines, we've got our wait group, we're add G. I'm going to come down here now and hold this hostage by saying wait for all of the Goroutines that we're going to create to report that they're done before we return found. Brilliant, brilliant. Now, what we have to do next is the last piece of that, but I need a Goroutine for every file. So why don't we do the following? Let's go ahead and use a literal function to go ahead and create those Goroutines. So immediately I just say go literal function, and now I have a Goroutine for every document. But I do have some nasty issues here. I have these returns that don't work anymore because these literal functions can't return anything. That's OK, we'll just clean that up. And now my GoLinter's complaining because we've got a closure bug with the document. If I keep it like this, then all the Goroutines are going to process the same document. So I've got to pass the document in to each Goroutine to get rid of my closure bugs. So I've now done that. I've got a very clean solution here now for every Goroutine. We're not done with our orchestration, though. We are going to have to call done to make sure that each one reports that they're done. So I've got my orchestration in place. I've got my Goroutines in place. I do have another problem, though. My problem is found. From my perspective, found is a global variable. And I've got every Goroutine calling found plus plus. That means that with 8 cores, I'm going to have a data race here. I have 8 potential Goroutines calling plus plus on the same memory location at the same time. What I want to do is whiteboard for you a little bit of what this data race looks like, because I want to make sure you're clear on how we're going to fix this data race in code and some other interesting things that are going to happen as we continue to look at this. Code readability reviews are so important. So this is what's happening. I'm creating a Goroutine for every document. Right now, that's 1,000 Goroutines. But I know that I'm on an 8-core processor. So what's happening now is here's our found variable. And every time this Goroutine finally gets to line 89 or 94, it wants to do a read, modify, write against this local variable, which is really like a global variable. And since there's no synchronization for these to get in line, their writes could overwrite each other. This is a nasty data race. So what we could do to fix the data race is use the atomic package and use the add int, let's say 32. We don't need necessarily a large count right now. And we could say add 1. Now we can do this, and what we've just done is fixed our data race. Now we've got to use a precision-based integer that matches the call we're making, so 32. That's also going to force me to have to do a conversion back to int. But at least I've gotten rid of my data race, and it's at the hardware level. So now what's going to happen is, as these Goroutines want to write to found, this is the old way, right? This is what was happening before. This is the old. Now what's going to happen is, here's our found, right? It starts at 0. Now what happens is, as these Goroutines want to increment found, they're going to have to get in line at the hardware level, and only one gets to operate against that at a time. That's what the atomic instructions are doing. OK, great. So we now have our, really this program should be able to run because we don't have our data races. We've got a Goroutine per file. That's good. But I'm already thinking scale, and something is really, really scaring me. Even though this is now going to get in line and we're going to be synchronized, we need to think about the cache coherency problem here. Because the cache coherency, with the way the caching systems work, we're really going to be thrashing through memory. What do I mean? Let's go back to our lessons back when we were talking about data structures and arrays. Remember, we are working on hardware that is built on a caching system. So core 1, core 2, core 3, core 4, and also remember we have L1 and L2 caches with an L3 cache right here. Now we've got Goroutines running against their own core. In fact, I'm doing this over 8 cores, right? I'm just showing you 4 out of the 8. And we have our global variable found. Well, guess what? This variable is going to be sitting on some sort of cache line, correct? Yes, it is. Which means that when this Goroutine is running on core 1, which it will, it's got to load that cache line. And this has got to load the cache line. This has got to load the cache line. That's got to load the cache line. Think about it. On all 8 cores, every Goroutine has their own copy of the cache line. Remember, at the hardware level, we're working with value semantics. So what does that mean? It means that even though the writes, the operation, is going to be atomic, and we're going to get the right answer, what it means is that when this Goroutine increments the value from 0 to 1, it's going to mark this cache line dirty and all these other cache lines, which now means that we do the modification, right? That's going to then get written back out here, OK? And what now is going to happen is when this Goroutine wants to now do its modifications, it's going to go, oh my God, that's dirty. Shoot. What we now have to do is get rid of this cache line, throw it away, and come back into main memory and bring in a new cache line. Remember, we're going to be thrashing through memory here because all these Goroutines are trying to read, modify, write the same memory location at this, right? And even though it's synchronized and we'll get the right answer, we're going to be thrashing through memory. What we've got to do is find a way to minimize the thrashing. And the best way to minimize thrashing is to be using local variables. Think about this for a second. We don't know how many times this add is going to happen. We know right now we're going to have 1,000 files, but we also know already that it's found 7,000 times. That's just over 1,000 files. But what would happen if we did this? What if I used a local variable to do the plus plus? Think about this for a second. If I use a local variable to do the plus plus, then the stack for this Goroutine is not going to be the same memory location for any other Goroutine, which means now we're not incrementing this global variable as we run through this code. What we're doing now is every Goroutine has its own copy of its own cache line, and the increments no longer thrash each other because these cache lines are sitting on their own stack frame. So we've just reduced a large amount of pain around the mechanical sympathy of our cache coherency problem. We didn't get rid of it completely, though, because look at what I'm going to do. I'm going to move this local variable up here. We still have to write back to our global kind of variable here, right, our found variable. We still got to write back to found the result of L found, but right now we only have to do that per file. So atomic.addIn32, address of found, L found. So what we've done at least is we don't have to do this thrashing 7,000 times. We only have to thrash this 1,000 times. It's going to be a lot better, at least length number of docs. And at least we're going to leverage some mechanical sympathy to make this algorithm run faster. OK, let's see if these coding changes work. Let's see what we did again. We still have our global variable found. We're using the number of documents as the number of Goroutines. We got our wait group for orchestration. We add the number of Goroutines we're going to be creating. At the bottom, we wait for all of those to report that they're done, convert the precision-based int back to a regular int there, and then we have our Goroutine per document that we pass in. We have our local variable to deal with the cache coherency problems. We defer the final counts. We report we're done. And we still do the open, read, unmarshal, and contains. OK, let's see what happens if we build this program. We should still see 7,000 times. But more importantly, I want to make sure that we're running faster. And we are. We were at about almost 900 milliseconds before. and now we're a little over 300 milliseconds. Look how much faster this program ran. Let's take a look at the trace. Go, tool, trace, t dot out, view trace. Oh, look at that. We're now using the full CPU capacity of my machine. Here is the old trace. Here is the new trace. Look at that. We're leveraging it. We now see it. And I want to show you something special about Go Scheduler and the garbage collector and how all this runtime stuff works. Look, when the program starts off, we see these long time slices again like we should. These goroutines are being allowed to do all 4 steps on their own. They're able to do all 4 steps, right? Long time slices. And then the garbage collection kicks in. And what do you see inside of garbage collection? Lots of short little time slices. Why? I don't know. Let's inspect. Why do we suddenly see short time slices when garbage collection is running, but long time slices when it's not? Let's look at the stack trace for Goroutine 185. What do you see? This is interesting. Notice that this goroutine was running and then asked to make an allocation on the heap. malloc GC. That's a heap allocation call. And what did the scheduler say? It said, whoa, 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 stop. I've got other goroutines that don't need the heap. So guess what? Don't get in my way right now. I'm going to context switch you and stop you from running. And I'm going to give this P to somebody else. And when we click on the next goroutine, what happens? It gets to run until it gets to a malloc GC. And it's told to stop. And then this goroutine gets to run. And it's told to stop. And this goroutine gets to run. And it's told to stop, all because it's trying to make changes to the heap while GC is running. How amazing is this? This isn't anything that we could have coded ourselves. We're getting these types of mechanical sympathies and this knowledge for free because the scheduler knows what these goroutines are doing, and during garbage collection it can find other goroutines that don't need the heap, and therefore we can get that GC done faster. Okay, this is pretty cool. We ran really fast. And the fan out pattern worked, and it wasn't a lot of code. It wasn't complicated. But that being said, I'm still very much afraid. What if I want to process 1,000,000 documents? That's 1,000,000 goroutines. So I don't think our algorithm is going to scale beyond a certain number of goroutines here. It's going to be too much for the system and the scheduler. So we need to find a way of using less goroutines to do this work, and maybe we'll get some better performance out of it as well, because less is always more. Well, couldn't we do the following? Couldn't we say, well, since we only have 8 cores on the machine, let's only use 8 goroutines, and we'll feed those 8 goroutines all of the work as they get it done, and we'll see now if we can get work done even faster, because if this works, it doesn't matter if it's 1,000 documents or 1,000,000, the cost is the same. It's 8 goroutines. Let's make these changes to the program. Okay, so this time G is not length docs. What it's going to be is the runtime.num CPU. It's going to be, in our case, 8 goroutines. So all this code is good, but we've got to be able to feed these 8 goroutines the work. This is where we could start using a buffered channel. So look at what we can do. Make a chan of strings, since the documents are string-based, right, the names of the files. And let's use, in this case, length docs. Let's create a buffer for every document that we're going to process. Let's use this loop now to go ahead and feed ahead of time, fill the buffer with every document that we care about, and we'll close the channel. Look at what I'm doing here. We're not going to have any real latency costs here. We're going to fill the entire buffered channel with every document we want to process. We can do 1,000,000. That's no big deal. I close the channel because what that means is once the channel is flushed, it will report or signal without data that it's done, and these goroutines can terminate once there's no more work left. How beautiful is this? Push work into the buffer. Once it's all done, it will report that there's nothing else, and we can terminate the orchestration. Brilliant. So now we have that, which now means that this loop now needs to be based on the number of goroutines. So for I colon 0. Well, I is less than G, I plus plus. Now what do we have here? We're going to be able to create our 8 goroutines. Okay, now we can't be passing doc in anymore. Everything's going to be coming off of a channel. So we get rid of that. And we've got to feed this stuff off a channel. So what if we did this for doc range, and we can use our closures for the channel. Look what I'm doing. I'm using the for range in order to be able to receive on the channel, which means all 8 goroutines now just come back into this receive, get the next document. Order doesn't really matter. Can do its 4 steps, come back to this, get the next document, and the goroutines can flush this out as fast as possible. Once there's no more documents in the channel, guess what? It's already closed. They terminate. When they terminate, we get into here. Think about this as well. We are now using a local found variable much longer. We only have 8 goroutines. That means that we're using this cache line much longer. The only thrashing we're going to get now is at the very end, and it's only 8 goroutines. We're not even going to feel that. So not only is this algorithm more efficient from the goroutine side on the scheduler, and not only can we scale to 1,000,000, we've got much better mechanical sympathy now because we're not trashing any of this memory. And we're not even using the atomic instructions to do the count, which is also going to help speed us up. We only do it at the end 8 times right there in the defer. I am super excited about this algorithm. Now, over 1,000 documents, let's see what happens here. We ran at 322 before, right? OK, go build. Look at that. We shaved another like almost 40 milliseconds over 1,000 documents. Imagine the time we would save over 1,000,000. Let's take a look at our trace again. Boom, there we are. Trace looks pretty cool, and it looks just as nice as this one. And what's even better is if I open it up, it's even going to be cleaner because we're only really having to analyze those 8 goroutines. And now with the new tracing around regions and tasks, we could actually break down what any one of these goroutines are doing. I mean, if I go back to the view where we threw a goroutine at every document, actually that's not running. It would have been nice. We could have, on the other one, it would have been a little easier to look at, come in and done a goroutine analysis. Notice it says n equals 8. You can now see the 8 goroutines and how they executed over the entire course of the work. You could see how well we distributed that execution time. You could see the GC pause times. We can also dig into any given one of these and look at a trace just for that like kind of goroutine there. And we can start to isolate, even though we're seeing these, we can start to isolate what's happening at an individual goroutine level. And then with the new tracing APIs for regions and tasks, it gets even better. So this tooling is just getting ridiculously better and better with every version of Go. And I'm so happy that I was able to share with you what's happening here on the 1.11 version, even though we're in beta right now. Because by the time you see this video, we're already going to be full-fledged 1.11. 1.12 is going to be around the corner. And these have been significant changes since 1.10 to the UIs. So I've just shown you now how we can do some micro-level optimization, not just using a profiler, but also using the tracing tool. And we've done some live coding to show you how all of these concurrency primitives around even orchestration with channels and wait groups simplify a code base. And I think one of the nicest things is we almost don't even have to worry about how the work gets done. That's the beauty of the Go scheduler. We throw work at it as efficiently as possible. Then we wash our hands of it, and we let the runtime do the rest. So this is tracing in Go. Thanks for spending all of those hours watching the Ultimate Go Programming Live Lessons 2nd edition. I really appreciate your time. being here. Look, you're going to have questions. All of the material you've just looked at is out there on a public repo in github.com/Arden, A-R-D-A-N, labs/Go Training. github.com/Arden labs/Go Training. It's all there. We're always improving it, but it's there. And look, find me, okay? I'm on Twitter at goinggo.net. I'm on our Go for Slack channel, William Kennedy. DM me there. Email is bill@Arden, A-R-D-A-N, labs.com. You can't find something in the training, in the material, you've got questions, I will do my best to give you my time. I travel all over the place, but I will get back to you. I just want you to have the right experience and learn the right things so all of us in the Go community are writing the best code that we can. So thank you again for spending all of that time, and don't feel like you can't reach out to me. I'm here to help you.